ऑडियो सेटिंग पे क्लिक करो
आप लाइव स्ट्रीम कर दीजिए फिर मैं
कट कर
Welcome to the second day of this conference. In the first half, there are two sessions on AGNs. This will be the first AGN session. There are 3 talks in this session by Ritaban, Stalin, and Shivangi Pandey. So let's begin with the first talk, and I will welcome Ritaban Chatterjee from Presidency. Ritaban is going to talk about moderate correlation between accretion disk and jet power in large samples of Fermi blazars. Ritaban? Mike.
Hi, so you can all hear me, and where's the pointer? Okay. And
क्लिक करो स्लाइड पे क्लिक करो
okay, so thanks to the organizers for inviting me to this conference and giving me the opportunity to speak. And in return, I have a gift. So the gift is that this talk will be shorter than half an hour. So you will have some time so that there will be no, at least this session should not exceed the time. I give you the gift of time. Okay, so let's move on. So all that I'm going to talk about today, this work is done by a former MSc student at Presidency University. She is a PhD student at Clemson now, and this work is a little old. So it was published in PhysRev D. So I just heard Sudipta talking about PhysRev. So PhysRev D now has a bigger astro editorial board, and they invite more astro-like papers.
But isn't it more like relativity related?
It was, but yeah, but it has become a little more towards astro now, and that's a big help for us because I cannot publish in MNRAS or FJ anymore. So in September, I spent a lot of time submitting whatever papers I had in MNRAS. That was the non-charge deadline. Okay. I am, and another paper that I would like to mention is by Vaidehi. So we have used a lot of information from that paper. So I'm just acknowledging that right here. And also various kinds of supports from various agencies in India. Okay, so the reason this talk is shorter is, so I'll tell you the summary of the talk right away. Okay. Many times I give a talk or I write a paper where the summary is not really a one-line, precise, pithy summary. It's more like a bunch of results. But here, I really have a one-line summary. So you know how in Spider-Man they say that great power comes with great responsibility. So the summary of this work is that the great disk luminosity sometimes comes with great disk luminosity, sometimes comes great power. So it's not always true. So essentially, a powerful disk is a necessary but not sufficient condition to produce a powerful jet. Why we are talking about this? So as has been clear from many of the talks yesterday, jets are launched from the sort of the accretion flow, or at least from near the accretion flow. And so some connection between the disk and jet is expected. On the other hand, whenever we see jet, there is always underlying accretion. Even if it's a star forming region, there is accretion and we see some weaker jets. However, the opposite is not true. So there are many cases where we see accretion, but there is no jet. So there is always this question in sort of high energy astrophysics that what causes a jet to form, and we are all sort of focusing on that. A lot of the questions, a lot of the answers that were discussed yesterday and will be discussed throughout this conference actually points towards that question. Now, so that's why it's kind of important to study the connection between disk and jet, because that can provide some clues about what actually launches a jet from a disk. The problem, the challenge, so that is the context. The challenge is that there are no one suitable indicator for jet power. Whatever indicator you decide, that has some cons, some pros and some cons. For example, gamma rays are very nice. Gamma rays come only from the jet, and the gamma ray luminosity can give you some idea of the jet power. But the gamma rays that we see mostly are relativistically beamed, because the jet is pointed towards us in most of these sources. So then you have to correct for beaming, and then correcting for beaming is not easy. On the other hand, if you decide to take some indicator which is not beamed, such as the low frequency radioluminosity, which is from the extended jet, which is not beamed, but then sometimes people argue that since these are hundreds of kiloparsec scale, so they are not exactly simultaneous with the disk, and AGNs are variable. So whether that comparison is suitable is not clear. Another problem is that you want to study the disk and the jet in the same object, but for AGN, in many cases, they are not visible in the same object. If you want to study the disk well, you study radio quiet objects like Seyfert galaxies. And if you want to study the jet well, you study blazars or radio galaxies. So in case of blazars, it's difficult to see the disk. In case of Seyfert galaxies, the jet is usually very weak. In case of X-ray binaries, if there is a jet, the microquasar, then they're not simultaneous. In many cases, the disk is bright and then it becomes a little weaker, and then the jet becomes brighter, etc. So that's another way to go about that, but that challenge remains. So this is just an example where you have a blazar ACD, and so these are your synchrotron optical emission, but then the disk is here. So the disk is overwhelmed by the jet emission in many cases. So this is just one example to elaborate the point. Notice how the disk is sort of increasing towards blue and the synchrotron is decreasing towards blue, like they should. So that's one of the challenges. So despite of all these challenges, people have obviously looked at this problem. And so this is the famous...
This is inferred from, because if it is masking, then how do you see it?
Yeah. So in some cases, the disk is seen in some really quiescent state of the jet. So the jet is really weak. So this is one of those examples, but in some cases, it's really just implications from other observations instead. So this is the famous fundamental plane. This was done in 2003. It essentially is a relation between the radioluminosity, the X-ray luminosity, and the black hole mass. So this is a sort of a cross section of the plane, and all it shows is that it's a line, and they're not scattered all over the plane. So in a three-dimensional space, this is a plane. So that's why it's a fundamental plane. So this is interesting because this shows you some connection between if you assume that the radio is an indicator of the jet, and this is an indicator, the X-ray is an indicator of the disk. So that gives you a relation. So that's one result that you should keep in mind. There has been other samples. So more recent papers have shown they have taken SDSS observations along with cross-correlated with NVSS samples, large samples, and you see relation between jet power and bolometric disk luminosity. However, when they tried to see if there is a fundamental plane, including the black hole mass, they did not find any fundamental plane. This is somewhere in time. This is somewhere in between. So 2012, this is Giesel in his group. So they essentially just took Fermi blazars, plotted the BLR luminosity and the gamma ray luminosity, no beaming correction. They see some correlation, and I'll come back to this. So this is about 100 sources. Finally, there are other theoretical complications. For example, this is from Saha Chekhovskoy's paper. I'm sure there are other results like this. Some of the work was shown yesterday. So this essentially shows that. So this is from simulation. So this is GRMHD simulation of launching of jet. So this is the m dot c square. So this is the proxy for accretion. And then this is the magnetic field. And this is the jet launching sort of efficiency. So it turns out that the jet launching efficiency is very, so the jet power, you can say, is well correlated with the magnetic flux, but not very well correlated with the disk. So that comes from simulation. More recently, more recent than this, there's a Nature paper by this author, which so they calculate the magnetic flux near the accretion disk. So there's a lot of inference in this y-axis, but that's what they do. And turns out that in this sample of 70 or so radio loud AGN, there is a correlation between the magnetic flux near the disk versus the accretion luminosity times the magnetic flux. So all these sort of various different kinds of result tells us that we need to really look at other samples, increase the sample size, and that's what we actually wanted to do. So we wanted to look at blazars, and if we can find some connection between the disk luminosity and the disk power and the jet power. And that's where Vaidei's paper was really useful, because in that paper, they actually give you the disk luminosity inferred from mostly emission line and absorption line luminosities for a large sample of the Fermi blazar, something like 1,000 blazars. So then our question, the question that we had is which measure of jet power we should use. For jet power, we're using using Vaidei's paper to get the disk luminosity. For jet power, what should we use? So since there is no unique one, so we essentially said all of the above. So we said, okay, we'll try all of these things and see what happens. So so this one is the gamma ray luminosity without any beaming correction. These yellow ones are upper limits, the blue ones are actual detections. So this is just gamma ray luminosity from the Fermi catalog. Then we also did beaming correction. So beaming correction is very difficult to do. If you actually do VLBA observations, and from there, if you do beaming correction, that will take you many, many observations. So there are like 10 or 15 sources for which we have more precise Doppler factors. We did that, but that's only 10, 15 sources. So here we are using Liodakis paper, where they found the Doppler factor for large number of sources using something called the variability Doppler factor. So they essentially, okay, so if you are interested, you can look at the paper or ask me at the end. But they use something called the variability Doppler factor, and that's what they use. So you can apply that to large sample of Fermi blazars, and you get this. So as you can see in the previous one and in this one, that apparently the correlation is very good. And I'm not showing the correlation coefficients, but those are pretty high as well.
Ritavan,
Yes.
by jet power, you mean the jet kinetic power or the jet radiative?
So yeah, so I am essentially doing just jet luminosity, and I'm assuming that there is some constant factor. But that's a very important question, whether all jets may not have the same factor. So then that correlation will be messed up.
So you just mentioned about getting the gamma from this variability.
Yes.
But then there are some common pulsars where VLBI, especially, might have provided you the gamma. So did you check whether?
Yeah. So there are about 15 sources for which there is very detailed VLBI data, and Doppler factor is calculated from that. But if you want to do this for a large sample, there isn't, and it's actually not.
Right?
Yeah. Consistency with those 10 sources. So if you go back to the Liodakis paper, they have sort of compared their result with various different results, and that's among the different methods, they prefer this method. So that's why we are following this. So this is another one. This is a different one. So this is not a luminosity. Here, what we are doing is, again, remember, x-axis is always the disk luminosity. The y-axis here is the maximum jet speed. So it's the beta that you measured from VLBA or from VLBA observations. And this is an apparent value, obviously, because this is greater than C and all. But this gives you, statistically, this will give you an idea of the jet power. And here, this is really, it could be something related to actual jet kinetic power as opposed to the radiative. So again, here you see some hint of correlation, not clear whether it's a moderate sort of correlation. And then finally, we also looked at the low frequency radioluminosity from the extended jets. And there you again see similar type of correlation. So this low frequency radio emission is from the Keenan et al. Work. And they have actually very large sample. They have used various methods to actually pin down the low frequency radioluminosity. The point is that in these correlations that I'm showing you now, and some of the ones that I showed you before, there is a factor that all of these, how in astronomy it's very common that two luminosities will be correlated, even if they are actually not correlated, because if you take a bunch of sources and extend that. So essentially, this is a common distance dependence, a common redshift dependence. So a lot of the correlation that I showed you actually is because both the disk luminosity and the jet luminosity are redshift dependent. So there is a way to bypass that, which is to calculate the partial correlation coefficient. So if you do that, then what we found was that the correlation remains, but it's not very high. So there are two ways to get rid of common dependence. One is to actually calculate the partial coefficient. The other is you can divide the sample into small subsamples in small redshift bins. Then in a small redshift bin, there is no correlation, because this common redshift bin is driven by the fact that we only see very bright objects in the high redshift. And in low redshift, we only see low luminosity objects because there are many low luminosity objects than there are high luminosity objects. So it's driven by the higher end and the lower end. So this is the correlation coefficient and the partial correlation coefficient. Turns out that in small redshift bins, they are similar, but the values are 0.4 or less. So that's why the term moderate. So it's not zero, but it's not very high either. If you look at these data in small redshift bins, yes.
What about the errors on the correlation coefficient?
Yeah, so Pearson correlation coefficient doesn't come with an error. What we did was we did some simulations and showed that what fraction can be what. I don't have the plot because I am anyway not claiming a very strong coefficient, but I can show you. This is actually a question that the referee asked and we sort of answered that. These are in small redshift bins, and you can see that there is not much correlation, but there is a trend that you can see in some of these, that if you take high jet power, that is usually on the top right corner, which means only for high disk luminosity. But for different values of disk luminosities, you can have, I mean, in the high disk luminosity also, you can have different values of jet power. It is more apparent in this one. So now we have actually also sort of normalized by the mass. And so you can see that there is a sort of all the points are on this side of the diagram, which essentially means that if you have a very high disk luminosity, you can have a range of jet power. But to have high jet power, you need to have high luminosity. So that is essentially the summary that I told you. So the question remains is what is driving this? Turns out that the powerful disk is a necessary condition, but not sufficient. So what makes it sufficient? So the possible candidates, and this was discussed in some of yesterday's talks as well. It could be the spin of the black hole. It could be the magnetic flux present. It could also be the environment. At least for AGN, often people have claimed that if you have a relatively less dense environment, then jets can have the ability to gather more power, more collimated sometimes. So, so that's my message. Okay, that with great disk luminosity sometimes comes great power.
Thank you, President, for the talk. I think it's perfectly. We have so many time for questions.
Yeah, you showed a correlation of the magnetic field versus the disk luminosity.
Yes.
Has anything been done regarding magnetic field versus radio luminosity?
In observation,
in continuing on that, how did they estimate the magnetic field close to the source?
Yeah, so let me go back there. So this is actually a result I recently saw, so I'm not fully sure about it, just because it was a Nature paper and seemed like a related thing, so I quoted this. So these are all radio loud sources, so obviously there are radio luminosities available, but I don't have the correlation on me. And what was the second thing that you asked?
Second question was, how did they estimate the magnetic field? Like,
yeah. So that's interesting. You did read the paper.
Okay.
In the sense that no, I'll tell you because it's really like sort of a third level inference that they're drawing. So they calculate the they do VLBA observations, and they try to measure the opening angle sort of the jet, and then they estimate the magnetic field from the VLBA flux. And then they say, okay, the magnetic flux should be conserved. So then they extrapolate that very close to the equation. So it's not the most rigorous work, but just something that's related.
yeah. Is there a similar correlation in microquasars?
So microquasars, the only case where microquasars are included is this. Okay. So here you have 8 microquasars. There are many observations of 8 microquasars. And that's why this fundamental plane was very important when it came out, because it spans a range of sort of 10⁸ solar masses. So this is on that line. But by the way, I should mention that there was a lot of controversy whether the fundamental plane itself is a distance-driven effect. But then they wrote another paper saying that why it is not distance-driven, and they have other one. So this part is about microquasars. So they are on the same line.
Okay, in the MSD simulations you showed, in the bottom panel, it was jet launching efficiency.
That's right.
It was 200%, 300%.
Yes. So that means they're getting power from the black hole spin.
More than 100%.
So they are getting additional power from the spin of the black hole, and then there is accretion power. That's why they are normalizing by the accretion.
So when you say a disk luminosity or disk power from AGN, so what are you considering? Because you will have one multicolored black body, right?
Yes.
That is generally associated with the Sakura-Tsunami phase.
Yes.
But the disk also gives a lot of, will emit lot in X-rays, in radios, etc. Right? So that there is a problem here, because an accretion is a convergent flow, and jet is a divergent flow. And as of now, as far as I know, nobody has been able to distinguish between a radiation coming from a convergent flow and a divergent flow. Okay. So there is a dichotomy right there. I mean, you don't know, you cannot decipher it. So how do you decide what is the disk power?
Yeah, so the standard thing to do in AGN to estimate disk power is to look at the emission lines. So you look at the emission lines and you assume that emission lines are basically because of photoionization of the emission line cloud. So then people have done scalings between emission line luminosity and estimate of disk luminosity, you can say, or disk power, and that's what has been used here. Now, on the other hand, in the fundamental plane for Mardoni, they used X-rays. So X-rays means they are not really used. I mean, ideally they should use optical UV, but they don't have that. So X-rays, again, there is some inference. So maybe some combination of the X-rays and the emission lines would be nice.
Now, for example,
Boydei can comment.
For example, like M87, it doesn't show any multicolored.
That's right.
Right.
Yes.
For example, Shomir had wrote a paper a long time back. He considered almost everything is coming from the disk. Okay,
So,
but there is a legion of observers, theoreticians who said that everything is coming from the jet, nothing from the disk.
So,
I mean,
the
this
good
is the-
thing about emission line measures is that you don't care how the photoionization source is working. You just look at its effect on the emission lines, emission line clouds, and you are using that. So it doesn't care about the process. But you are right in the sense that exactly what fraction of the disk power is being used for the generating the emission lines, that's not exactly clear. Just like the ambiguity about the jet power as well. But Vaidai has other comments. No, sorry, I don't want to put you.
Okay, next, Amit?
Yes.
So,
Just a minute.
Amit.
It's not important, right?
So,
So, like,
we have used radio Doppler factors to correct for a gamma luminosity, sleeping boosting.
Yes.
Yeah, but that produces a very systematic effect. Because the emission from radio is coming much downstream, and then probably the gamma ray is coming from very close to the core.
Well, there are multiple things I can say about that. One thing is you can understand that Doppler factors are not available, right? So whatever can give me some level of consistent Doppler factor value so that I can do dimming correction, then that's that's something that that is useful. In fact, I didn't show one plot. Maybe I should have kept it. That once I debeam, the redshift dependence is also sort of mitigated in some sense. So that's one thing. The other thing is, it's not yet clear whether the radio and the gamma ray come really from very far away or they're close enough. But yeah, if that is right, then the Doppler factors will vary a little bit. But this is the best that we can have. That's for a larger family. That's the only reason.
Monica?
I just have a question about the last cognitive regarding the other factors that can be important. One is spin. So I was just wondering whether any dependencies on spin of the agents have been checked. I don't know how many.
Yeah,
dependencies
so
there are.
when you know how spin is measured from two things. For AGN, mostly the iron line, and for X-ray binaries from the X-ray spectrum, assuming that based on different values of spin, X-rays will come from closer to the black hole or farther away. And in some AGN, that same method has been applied, but it's very difficult because in AGN, the X-rays are not from the disk at all. So there are like 10 cases where you have spin measurement, but they have very large uncertainty. Irrespective of that, people have tried to plot the spin and the jet power or radioluminosity. It's inconclusive. We don't really, observationally, we don't know whether there is a good correlation or not between the spin and the radial outputs or some measure of it.
In fact, the Trinidad group already said that they did not find anything.
Actually, that was also said for the X-ray binary. That's presently why I asked the question, because they show they try to see the
Spin measurements are really not at that level where you can make such comments. It's just not there. Maybe with
Blazars you forget.
Yeah, sure.
Blazar, any blazar, microquasar, anything.
So essentially, you need a very high resolution X-ray spectroscopy mission. The Athena will probably not do that, but maybe something Athena will do better than the previous ones.
Hi. It's a curious question. For neutron star systems, we found in some sample of sources that it's not really a function of admission geometry in X-ray binary systems. But it's a function of the critical luminosity above which the jet power or you observe jets. So I'm just wondering if similar thing has been observed in
So
agents.
you mean so it's not a function of accretion luminosity, actually geometry, but
the
just
critical luminosity above which your jet power is being. So
okay.
I was just
So yeah, so in AGN, there has been a lot of studies about how the radio loudness depends on other observables, and there is no correlation. The only thing there is that actually in terms of luminosity there isn't much. In terms of black hole mass, there is a thing where there is a threshold black hole mass. All radio loud sources are above that mass, but once you get above that mass, there is no correlation. In terms of luminosity, I mean, other than the ones that I sort of showed and related things, I don't know of anything else.
yeah, this question came after looking at your thoughts. Thanks.
Great. So later on, maybe if there are no further questions. If there are no further questions, let's thanks Ritaban again for a wonderful talk on jet power and disk luminosity. And now let's move on to the next talk by Stalin from IIA, who's going to talk about the central regions of AGN, giving us clues from X-ray polarimetry. So that is something new stuff, IXP. Let's hear more about this.
So, thanks for the invitation. And coming to Nainital is like a homecoming for me. And so, I'll be talking about the central regions of AGN, clues from X-ray polarimetry. And this is the work done by two people who are listed here. Okay. So this is the broadband spectrology distribution of both jetted and non-jetted AGN put together. So when people normally talk of AGN, people talk about radio loud and radio quiet. This is a problem for the last 60 years. And this radio loudness is mainly dictated by the ratio of the flux density at 5 GHz to the optical B-band flux density. And they found a bimodality around R equal to 10. So sources which are having R less than 10 are considered radio quiet, and sources which are having R more than 10 are considered radio loud. But that scenario has gradually changed, and now people are advocating the use of jetted and non-jetted AGN. Jetted AGN are those having jets, non-jetted do not have jets. And if you see, they are intrinsically different objects. In the case of non-jetted AGN, you have SED which is dominated by thermal emission, either directly or indirectly related to the accretion disk. In the case of jetted emission, AGN, the emission is dominated by non-thermal process. And here I show the broadband SED of both jetted and non-jetted AGN. For non-jetted, it is the thick solid line. And for jetted, it is the dotted lines. And if you see, there is a striking difference in the broadband SED. And this difference is mostly noticed in the radio band, X-ray, and the gamma ray bands. But what are the important observables to study this SCD? We have imaging, spectroscopy, timing, and recently spectroscopy has been added, sorry, polarimetry has been added to infer the physical properties of the sources. So now moving on further, so here I just show the zoomed in version of what are the various components which can contribute to the broadband STD of a radio quiet agent. So this is a solid line. So we have contributions from the accretion disk, we have contributions from the hard corona, there is soft X's as well as the dusty torus. So we'll move on to the non-jetted agent. So when you talk of X-rays, we have the black hole system, we have the corona, and the X-rays are produced mostly by the inverse condensation of the optical UV photons coming from the accretion disk. And this condensation, as you know, produces a power law emission with a cutoff. And this cutoff is related to the temperature of the corona. And part of the emission from the corona will fall on that, it will get reprocessed with the accretion disk, the broad line region of the torus. And this gives rise to what is called the reflection features. And we have a prominent component from between 20 to 30 keV and a T line at 6.4 keV. So this is how the typical spectrum look like. So we have a power law continuum with an exponential cutoff. And then from analysis of these kind of X-ray observations, it is possible for us to infer the properties of the corona. So what we know about corona, this is not new, it's a 3 decades old field. And people have tried to infer the properties of corona from various space missions, such as Compton Gamma Ray Observatory, the Bose, from
No, the small one.
this one. Okay. So they have tried to infer the properties of the corona from observation from Compton Gamma Ray Observatory, the Bose, as well as integral. But these informations were mainly based on fitting some phenomenological models to the observed spectrum, try to get the cutoff in the spectrum, and then indirectly infer the temperature of the corona. And a large transformation in this whole field happened after the launch of New Star in 2012, mainly because of the broad coverage of New Star from 3 to 17 keV, and particularly its sensitivity beyond 10 keV. So the launch of New Star has revolutionized the field of the X-ray coronal temperature determination. And so we also tried to do some work on that line. So what we did, we went into New Star archives and looked for the availability of New Star observation from all ciphers. And in this exercise, we concentrated from August 2013 to May 2022. May 2022. So we ended up with a number of 112 ciphers. And for all these 112 ciphers, of course, we put some cutoff of the total count rate. After putting all these cutoff, we landed up with a sample of 112 ciphers having reasonable signal to noise ratio. And we initially fitted some simple phenomenological models to all these sources and tried to estimate ECAT. Once this cutoff in the temperature was determined, we move on to physical models to try to see what is the temperature of the corona. And we could reasonably estimate the temperature of corona in about 42 sources. And this is the distribution of the temperature of the corona in these.
So in all these, whatever you have done, I mean, you have classified them. In all these, if you look at the spectra of all these objects, they are thermally dominated. I mean, thermal, multicolored dominated, or it is power law dominated.
It's power law dominated.
But it is not jetted.
No, it's not jetted. So these all are clearly look for only sequence. So they're not determinants. So we could determine the temperature for 42 sources, and what is shown here is the distribution of the KT. So having done this, so we tried to ask the question whether the temperature of the corona, what we found, is stable, or is there a change in the temperature of the corona? And if such change happens, what is the physical process to create the change in the temperature of the corona? So here, among the 42 sources, we again looked for sources with multiple epochs of observations, because these things are needed to try to see temperature of corona is changing. So we found around 6 sources having multiple epochs of observation like this. We again did the same analysis, and what is plotted here is the variation in the temperature of the corona with the observational epochs. So here I show the example of two sources. Clearly, as you see, we can clearly see the variation in the temperature of the corona in these systems. And now, having done this, one of the important the limitations of this X-ray analysis is that when you fit models to the spectra, you'll be able to infer all these photon index, temperature, everything. But the problem here is we will not be able to know what is the shape of the corona, what is the geometry of the corona, and what is the location of the corona, and whether the shape changes with time, the geometry changes with time, or the location changes with time. So these things are completely not deliverables based on the available observing techniques like spectrum, timing, or what imaging. So we need other clues. So one such clue. Okay, so X-ray spectral analysis can constrain the physical parameters of the corona. However, X-ray spectral analysis is insensitive to the shape and the location of the corona. So what is the other absorption parameter which can constrain this is one of things X-ray polarization. So X-ray polarization is one key which can provide some information about the geometry of the corona. So we try to use that information. So recently, about a year ago, this group has done some theoretical simulation, and they tried to they considered three geometries of the corona, and then they try to infer what is the expected polarization and what is the expected angle. And this is the paper, and they gave the value for three geometries. For slab geometry, the degree of polarization is of the order of 12%. The degree is of the order of positional is of the order of 180. For sphere, it is very low, of the order of 1 to 3%, and degrees of the order of 90. And for a cone geometry, it's of the order of 7%. So what we did, so we want to test some of these models. So what we did, we again went into the archives of IXP and tried to see if there are any data which is not published, because this IXP team is very quick in publishing, and there is very little window available to.
Steven, I had a question regarding your previous plot where you showed KT evolution over different epochs. So KT almost remains constant within error bars, or is it?
It's beyond error bar. So what is shown in the dotted line is the mean value of all these observations. Okay. So if you see, many epochs are beyond the error bar above the mean value. So there is clear detection of change in temperature. Yes.
And also along with the shape of the spectrum, because even E cut is
showing. So we found change in the temperature corona. We also found change in the photon index, and we also found change in the optical depth.
So then it may be a very complex interplay between the.
It is not really very complex. See, it's a blob of plasma, right? Mm-hmm. Why should it have a single temperature?
No, it won't have a single temperature, but the shape of the spectrum, E cut is also evolving, which means contribution from different.
So of course, so let's say you have a corona or whatever. Okay, anyway.
Apart from this, I didn't show. We try to look for correlation between this change in temperature corona and the brightness of the source. So we found a positive correlation between the temperature and the brightness change. So there is always a hotter when brighter trend. When the source is becoming brighter, the temperature is increasing. So it is possible that the corona is closer to the disk. So at that time it is hot. At that time, so the photon index is also softer. So we found a correlation among all these parameters also. So it is
brightness is the X-ray brightness?
Yes, X-ray brightness. Okay, so then the exercise we want to look into IXP to try to see if there's any source which is not published. So in that exercise, we found one source which is called IC4329A. It was observed on 05 January 2023. So in this source, we did two analyses. One is a model independent analysis using the procedure outlined by IXP team. And we also try to fit the spectra of the simple model and try to infer what is the photon index and all those parameters. And these are the results here. So in the ISP operates in 2 to 8 kV band. So in the 2 to 8 kV band, we found the polarization of the order of 3.7 to minus 1.5, and the degrees of the order of 61. This is from a model independent analysis. So what is shown on the left is the model fits. From model fit, we found a value of around what? From model fit, we found a value of around 4.8 into plus or minus 2.2. So we compared these estimates with whatever theoretical predictions given by Husseini, and from these predictions, what we found, our observations tend to favor it ruled out the spherical lamppost geometry of the corona, and it favors a corona with a conical geometry. This is what the observation on 4329A says. Then what we did, I also summarized what is the current trend of the X-ray coronal properties from ISP observations. As of now, ISP has observed only 4 sources, and the details are given here. And if you see, in the case of MCG, lamppost and cone geometry are favored. In the case of MGC 4151, lamppost geometry is not favored, whereas it supports a slab geometry. In the case of IC 4329A, so we submitted around in about 2-3 months ago. Within 5 days of our submission, IXP team also submitted the same paper, of course, with more detailed analysis, XML, etc. So they also arrived at a similar conclusion. So for IC 4329, we also rule out the spherical geometry, and we also favor a conical geometry. So the question is, we have observations on 4 sources, and the results on all these 4 sources are different. Some is favoring one geometry, some is favoring other geometry. So that if you ask a summary as of now, based on these limited observations, we will not be able to come to any conclusion about the shape or geometry of the corona. This is what I feel. So from non-jetted, I will move on to jetted AGN. So as I told you, so this is the broadband ACD of a jetted AGN, and this jetted AGN comes under 2 classes of flat spectrum quasars and VLS. So in the case of flat spectrum quasar, they have a strong disk, they are efficient accretors, they are in photon-rich environment, and they have emission lines in the spectrum, which is shown in the bottom panel of 3C454.3. If you talk of BLX, they have an inefficient accretion, they are low density environment, and they have a featureless spectrum. So that is what is shown on the top panel of Mercurian 41. If you look into the broadband ACD, so they have a typical 2-hump structure, and the low energy hump is understood due to synchrotron process, whereas the origin of the high energy hump is highly debated. There is a debate between whether it is leptonic origin or whether it is hadronic origin. This is what is the current trend. So then, here I show some example of a source called 3C279. The broadband ACD is shown here. It was published by Vaidai in 2 papers. So what is shown in red is the broadband ACD of 3C279 during a flaring state in 2014 April. And what is shown in blue is the same ACD in 2013 December. And if you see the high energy hump, the red thing in 20 April nicely curves down, whereas the blue thing in 2013 December, the spectrum is highly harder than the gamma ray band. So which clearly says the high energy component has something additional to leptonic process, which can be either hadronic or it can be a combination of both, or it can be multi-zone model. So the inference is that a single source is also found to behave differently at different times, and therefore the high energy emission in this kind of sources is still not understood. So what is the way out? One possibility people thought is, if the optical photons are from synchrotron and the GeV photons are basically inverse component scattered particles, then there must be a close correlation between optical variation and GeV variations. If this correlation is found, then one can favor a electronic scenario. If this correlation is not found, then alternative models you have to think of it. So here this was done long back by Rithavan. So here I show an example of a source not 208-512 published by Rithavan in 2013. So you can see 3 flares. The first flare is 2009. So if you see, the gamma ray flare is correlated with the optical brightness and IR brightness. In the second epoch, the optical brightness is same as the 2009 epoch, but the gamma ray brightness is not there. So there is definitely there's no correlation between the optical and gamma ray brightness. So we took this further. So what we did, we went into Fermi archives, tried to look into all FSRQs and VLX. And the whole idea of this exercise is to see if there is a correlated variation between GeV and optical, because we want to test whether it's leptonic or hadronic. This is the idea of the exercise. So we got series of 3-4 papers there. So I am showing one example here. So here we have the gamma ray.
This thing, under the assumption that it is just a one zone.
Yes.
That is
yes. So here, so I showed the top panel is the gamma ray, the second panel is the X-ray, third panel is the UV from Swift, the fourth panel is the optical from Stewart, fifth panel is the smart infrared from Stewart, the bottom panel is the polarization. The message from all these exercises is that we found that the optical and GeV variation is highly complicated. We found instances when optical and gamma ray are correlated. We found instances when there's an optical flare without a gamma ray counterpart, and we found case where there's a gamma ray flare without an optical counterpart. So the inference from all these exercises is that just by using a correlated variation between optical and GeV, we will not be able to put a constraint that the high energy emission is because of leptonic or hadronic. So this is another example. So then from flux variation we cannot do. So what we thought we can try to do, we can try to explore another property of laser, which is a polarization variability. So what is shown here is some observations done by a small telescope in Kabul. So this is the flux variation done by Swan in 2017. So these observations are done for OJ287 done from the 13th telescope in Kabul. It's a small telescope. It's nice to do these things. The idea was we have a small telescope 13th and the polarimeter mounted on the 1 meter telescope. So the idea was to observe it in 13th as well as the 1 meter simultaneously. So this was tried some time back. And here also we found these sources are showing polarization variations, but the correlation between polarization and total flux is also complex. We found cases where they are positively correlated. There is no correlation between total flux and polarized flux. Similarly, there is a negative correlation also. So this is about the optical polarization. And this is again we did for a lot of sources, and we found the same pattern persisting for most of the places. So now what is the way out? From optical GeV and gamma ray variation, we cannot rule out leptonic and hadronic. There are two possibilities. One is we can look for neutrinos. The other thing is we can look for X-ray polarization. And X-ray polarization is now possible because of IXPE, and it was launched in 2011. And the XPOSAT will be launched, and we do not know how many places can be observed using this XPOSAT. But measuring X-ray polarization is really a difficult exercise. In the words of the PA of IXPE, he says, measuring X-ray polarization is not easy. You have to collect a lot of light, and the unpolarized light will act like a background noise. It can take a while to detect polarization. So detecting polarization X-rays is not an easy job. So first I'll lightly touch upon neutrinos. So what happened? People recently are associating neutrinos with blazars. This is one source we found. It was in the highest brightness state in 2021, December. This is the light curve. We generated the light curves. We identified three epochs. One is the quiescent epoch here. Then we have moderately flaring epoch, and we have the brightest epoch, the last panel. This was the epoch when neutrino was also detected. So what we did, we selected three epochs. We generated broadband SED. So this is how the broadband SED looks like. And in the broadband SED, we tried to fit only one zone leptonic model. And what we found, the first panel is in the quiescent phase. In the quiescent phase, the one zone leptonic model is not able to fit properly. We have one odd point sitting in the high energy part. Whereas in the moderate flaring state and in the high flaring state, during the epoch of neutrino detection, the SED is nicely fit by the leptonic model. So having done this, we tried to add this photon interaction. And when that was added, we are able to fit it nicely here. So the conclusion from this is, from SED modeling of the moderate and flaring state, the absorbed gamma rays can be inverse confidence scattering of IR photons. Leptonic model is not able to fit the quiescent state SED, that's the first SED. Addition of a photon meson component, which gives a better fit. So therefore, what we conclude is that this source PKS 0735 has a non-negligible hadronic component during the quiescent state. But during the flaring state, leptonic process dominates the hadronic process. So this is under review in MRIs.
Extra point. No, that's not funny. What?
Oh, good point. Oh, so now, from that PKS 0735, okay, we'll move to the hadronic, move to the X-ray polarization. So X-ray polarization can also give some handle about leptonic and hadronic scenario. So in the case of the leptonic model, in the case of flat spectrum quasar, the X-rays are also synchrotron self-content dominated, and the gamma rays will be EC dominated, therefore polarization will be negligible. In X-rays, we can detect polarization. So this I will skip then. So then coming to X-ray polarization of jetted AGN. So by measuring X-ray polarization, one thing we can tell about leptonic hadronic scenario. The other thing we can also tell about the acceleration process, whether it is shock acceleration or whether it is reconnection process. So in the case of reconnection process, the polarization of the order of 20%. In the case of shocks, it will be of the order of 50%. So what we did, we again went to IXPE, tried to look for any source which is not published. So we found IXPE has observed 10 sources, 9 sources are already published. So there was one source left for us. So one source left for us because no, we did some exercise. These four sources we did analysis. Result was ready. By the time we are making the table, this will publish the paper. So it's same results. So then we thought, okay, we'll do something quick. And this is one source which was not published. It was having 4 epochs of observation. And we did the model independent analysis as well as the model spectral fitting analysis. And we found that only on 2 epochs, this 28th October and 14th August 2023, the source was detected in polarization. And it was large of the order of 14 to 15%. And these are the results. So we have significant detection of polarization in 2 epochs. And then what we did, we compared this X-ray polarization with optical polarization. The observations are not simultaneous. However, we have optical observation for 10 years, 2008 to 2018. The polarization range between 2 to 6%. Whereas the X-ray polarization is much larger than the optical polarization. So and this is first result. Second result, we also found energy dependent polarization. There's a difference in the polarization between energies. So what we infer is that the medium is stratified. X-ray is coming close to the shock front, and optical polarization is lower, so it is coming much larger, much further away from the shock front. So here the conclusion on this paper is that based on polarization measurements, the electrons are getting accelerated at the shock front. So this is what is the conclusion, and this was just submitted today morning only submitted because we don't want to lose this paper again. So the summary is that we start with X-ray polarimetry. We try to answer 2 questions. What is the geometry of the corona? But does corona change with time? The inference is only few observations exist. More observations are needed to answer these questions. Coming to X-ray polarimetry, regarding the origin of high energy component, there is no consensus yet. Regarding nature of the particle acceleration, polarimetry favors acceleration by shocks. The way forward is basically improvements in theoretical modeling. At least for a few sources, we need to have targeted observations. When IXP is observing, we need to have observation in optical polarization, X-ray, UV, etc., so that a broadband study can be done. So I summarize here, but then there's one thought whether there is a hope for observation using exposure. So what I did, I have no idea about the sensitivity limitations, etc. So what I did, I went into the hard X-ray catalog, try to pick sources which are brighter than 1 e⁻⁻10 from the Swift Bat catalog. I could find 5 candidates. In the case of blazars, they are Mercurian 421, 373, Semi, and 455.3. In the case of radio non-jetted sources, I could find 25 candidates. So possibly, and this is how the candidates are distributed. If at least some of these sources flares, increasing brightness, and if they are at the level of detection of exposure, maybe some of the sources can be tried for similar kind of analysis. So I stop here.
Thank you, Stalin, for an amazing talk. Now, I am sure there are many questions. Cool. Yes.
Because this is about, I'm a bit confused. You talked about the neutrino candidate, right? I mean, so there you argued that in the flaring state it was leptonic. We were expecting that to be hadronic,
Yes,
right?
So,
is that very interesting? So, how do you explain that?
So actually, how we are arguing is that in the quiescent state, where it has to go by electronic scenario, we found one point which is not able to fit with the electronic model. So that we added a put on this one. It fit. So now how we are arguing, possibly both the process may be there. In the quiescent state, hadronic component is dominating. In the flaring state, though hadronic component may be present, it's subdominant.
Okay.
That's what we are arguing, because more things we could not do there.
Yeah.
Yeah,
I just have a question. I have 2 questions. Let me answer this the first one. One is regarding the first one, where you were showing the change in coronal temperature. So I was wondering whether you would expect a change in the coronal expansion, I mean, basically a coronal expansion or a contraction, and maybe some lag studies or something has been done.
So
that's
lag,
good.
the lag studies we have not done, just to see whether the corona is moving away from the black hole or close to the
Or
black hole.
it's entirely expanding.
Yeah, so
There were some recent reports.
Yes, there is a recent report which tends to favor an outflowing corona. So at some brightness state, the corona is close to the system. And at a brighter stage, the corona is farther from the system. So these kind of things will be able to explain the correlation between temperature of the corona and the X-ray.
But just the volume on its own, it's not just the temperature, but just the volume.
Yes, it's volume, it's the outflow, the shape itself is
Okay.
changing.
Okay, that's related to the KP.
Yes.
Okay. Okay.
Yeah, go ahead.
Okay. One small second question is when we are talking about the different geometries and for the corresponding expected polarization with respect to that, I was just wondering whether this kind of coronal temperatures or the expansion or the contraction of the corona will change the expected polarization degrees or not. It's not just the configuration, but also the.
Yes, no, that is not done. So only for these three fixed geometries, they ran this simulation and they gave these numbers. So if the geometry changes and it goes, it outflows, so that kind of number is not there.
But there may be some degeneracies in the.
I'm not sure how they do all this.
Okay, thank you.
Okay, so in your first IXP results, so you showed like the angle varies with energy. At least in the last bill, 5 to 8 kV maybe, it is significantly decreasing, 21 or something.
Okay.
So as of now, I mean, IXP observed the sources which shows like a constant angle with energy. So in your case, I mean, what could be the reason of this change in angle?
This.
So the first result.
The change in angle, at least for the jetted region, what people have done. So when for a couple of sources, they have simultaneous VLB observations.
Okay.
So they find that the change in the position angle for X-ray, they are tying to the change in the position angle of the radio position, jet position angle. Okay. So that for a couple of sources, they have simultaneous VLBA and ISP observations. So this change could be tied up to the change in the position angle of the jet.
Okay, thank you.
Great job, Professor. So my question is that for NDC 4151, you found that slab geometry of corona is preferred, right?
That is from some other people.
Oh, okay. So my question is that so in a typical Seyfert spectrum, there is a reflection constant harm. There is the broad iron line. So for that, the hard X-ray source must be at some height, very extended, at some effective height above the this, right? For the reflection features.
Yes.
So in a slab-like geometry, can that happen?
So okay, then it cannot happen because the iron line and the reflection from cannot happen. But I do not know at that point of time what is the reflection, what is the reflection from, how strong it is, how it is ignored. It's just from the
because Professor Chris Dunn and Ayako Boda, they actually published an expect model, AGN Slim. For Slim, this where they consider this slab-like corona geometry. So I was just.
But this, you see, that this reflection hump also changes with time. Okay, so at this particular epoch of
it may be
ISP observation, which is data is reported, I have not looked at the paper to see whether there is any reflection feature there. So I just, for the completeness, I just took the numbers and put it in the table. So I am not sure what is the state of the X-ray spectrum at that epoch.
Amit, then.
So, my question is to pose the question extension about this neutrino. So as you're claiming in the paper that during the low state you are seeing this neutrino. And probably
under the brightness state you are seeing the neutrino emission. In the highest brightness state.
So that is contradictory. When it is electronic dominated, you are seeing neutrino. When it is electronic dominated, you are not.
Yes.
So you are seeing the emission during the high state.
Yes.
Yeah,
neutrino was related to the maximum brightness state of the source.
So why it should be electronic?
So in the data, whatever the notion is that in the brightness state, the neutrino is there, possibly dominated by hadronic process.
So the whole idea telling that it's electronic is based on SED model.
Yes.
और तो कुछ बोलो.
I don't have anything after that.
Okay,
Because
Indranil and then
that's
Pradeep.
kind of
Last one is Pradeep. Indranil.
Yeah, Stalin, first of all, very good talk. Secondly, is there are many questions I will not ask for.
There are many.
So the first thing I would like to say is that the corona may not be. I mean, you see, if you have a subcapillary flow, you get this power loss. Okay, you don't need to have somewhere something you put a blob somewhere. You don't need that. Okay, if you have a subcapillary flow, you get it. Okay, whether there is a shock or not doesn't matter. You will get it. Okay, that's number one. And that curvature, what we call this reflection hump, that comes naturally only from inverse componentization. That she can, I mean, vouch for. So that's number two. So the whole, I mean, the accretion process, you need not have to have all those, those cartoons. Okay. Okay, that's number one. Number two is that how do you, I mean, these people who have given you this Urini or somebody, right? Ursini. That how do they decide that this is the geometry, like slab?
So that I don't know what is their motivation? I don't know because
No, they do it from the geometrical this thing. If I remember. Yes. Simulation and get this thing. So they get the reflection.
There is an observational result. We need to explain it. Let's try this model. This slide.
There's no dynamics by the way.
Dynamics. There's no dynamics.
It's actually static. No dynamics.
Okay, we'll have the last question before we. Pradeep.
So I want to come back to your TK07.
Okay. No, the thing is, the first thing one you should look into is that this PK0735 is located 2.2 degrees away from the neutrino one. So the association that it may or may not be associated with this source that will be in question.
yes, that I agree.
Okay, so that's the first point. So that's a caveat.
But one point, okay, I agree with that. That's a caveat. But this was not only from ice cube, it was also found from other two.
So
that is
it's a very interesting event, but whether it is really associated or not,
that I also not.
One has to do. But the other thing about the modeling is that you may have probably seen a paper which written by Hess, Veritas, using Swift, Fermi, and New Star data, where they kind of reasonably showed a leptohydronic model fit. Reasonably well fitted leptohydronic model during the neutrino emission event, even though it requires, they say it requires very large jet power. So maybe you should look into that paper, and because I'm a little surprised by this, because if this really becomes true that you're during a flare, that it is subdominant, that changes the whole scenario of how you create target of opportunity programs for neutrino counterparts of neutrino. It makes it even more intriguing. Okay, so
So I mean, it was seen during the neutrino flare happened when it was non-jetted, right? I mean, jet power was low.
It was highly flaring state.
Highly flaring state neutrino happened, and they are fitting with lepton. That's an interesting.
Is it just
Okay.
again the conventional?
I think we can have more chances to discuss this with Stalin during the tea break. Now let's go to the last talk of this session, Shivangi. So let's thank Stalin once again. Thank you. And now we have Shivangi Pandey. She would be talking about deciphering the mass measurement odyssey of intermediate mass black hole NGC 4395, the Enigma Unveiled. With the drive. In Google Slides, right? Yeah, you will see it in the right. Yeah, this one. Yeah. Just slideshow, just slideshow.
Okay.
Then some right.
Am I audible? Okay, so good morning everyone. I'm Shivangi. I'm a PhD student here at ARIES and I work with Dr. Shrinidhi Rakshit. So my work basically revolves around understanding the co-evolution of the host galaxy with its central engine counterpart in the active galactic nuclei. And in order to do that, we try to estimate various properties. One such thing is mass measurement. And we try to do it by this technique called reverberation mapping. And so this particular work is a study of this very famous candidate intermediate mass black hole, NGC 4395. And so let's begin. So this is a very old model based on Udi and Padovani of AGN. I'm just showing this so that I could reflect upon what my basic nature of work here. So broadline region is one of the most important components. And we try to understand its response with respect to the continuum variation coming from the central engine. So one of the most important question is why would we like to measure the black hole mass? So the first thing is obviously we would like to understand the evolution and growth history of the host galaxy linked with its black hole present almost at the center. And then the problem with this is that the micro-arcsecond resolution requirement, which is very difficult with current technology, and also the majority of agents are present at the high redshift. So obviously, because of that, the core will outshine the host galaxy and making it difficult to observe. So what we do is obviously spatial resolution will be out of the picture. So what we try to do is replace it with time resolution, and hence reverberation mapping is one such technique to do that. What is reverberation mapping? It basically tracks the response of the emission lines to the continuum variation coming from the central engine, and then eventually it gives the size and structure of the concerned region. For me, it's broadline region. People also do it for accretion disk and torus. So suppose you have this central engine and at the center, and then you have this broadline region gas clouds revolving around. The continuum variation will come out in all directions from the central path, and the moment it hits the nearby broadline region gas clouds, it will photoionize them and gives out the emission line. So for the observer, there will be a continuum light curve and the emission line light curve with a possible lag. This lag is basically just the light traveling time from the continuum to the broadline region. So we estimate this lag by using various lag methods. And then by the virial theorem, we can estimate the black hole mass. So it requires like 3 parameters mostly. First is the broadline region size that comes from the lag by just associating it with the speed of light. And then we have delta V, which is the line width. That is the measurement of line width of the emission line, concerned emission line in the spectrum of that particular source. And then the virial factor, that is F, which actually depends on the geometry and inclination of the AGN. So in all, it gives the black hole mass. Now about the main work, which is the measuring the black hole mass of this low luminous AGN MGC 4395. So it's nearby. You can see that it's an extended one, and its core is the intermediate mass black hole. So it's a nearby galaxy, and it is characterized as a Seyfert-1 galaxy, and its volumetric luminosity is around 16 in V band. Just the luminosity is 16 in V band by Filipenko 1989, and it harbors a candidate intermediate mass black hole. What's so interesting about it is that obviously it's the least luminous broadline AGN known to date, with a volumetric luminosity lower than 10 to the power 41 per second. And the reason why, and that is the particular reason why its mass measurement is in conflict, because obviously the contamination from the host galaxy and the constraint and the difficulty in constraining the variation of the source. So from previous studies, the mass range is for this source is provided. So there are various studies right from UVRL program from Peterson et al. 2005, then so many other things, photonization modeling, then constraining the mass from empirical relations, and then so many other things. But all of these studies are very inconclusive in understanding the mass of this particular source. And then following to that, this is a plot from Cho et al. 2020. This is between the H beta lag versus the quantum luminosity at 5100 angstrom. And you can see there are a lot number of sources here. And on all of these sources, like around hundreds of sources, the reverberation mapping has been done, and their H beta lag has been estimated, and hence the mass measurement. The one peculiar thing about all of these sources is that they are fall in the supermassive black hole range. So and this line is fitted by Benz et al. 2013. So we are trying to see. You can see that our source lies at the very extreme end of this relation. So we try to see that whether this particular source can be or also like whether these low luminous AGNs can also follow these RL relation, that is for the supermassive black hole, and hence whether it would be extended for the lowest luminosity end or not. So starting this MGC 4395 could be a unique testbed for investigating various properties and correlation of AGN in the lowest luminosity range. And then obviously one of the most important thing is that if we study the intermediate mass black hole, they are also kind of act as a black hole seed in the early universe, and black hole seeds for the supermassive black hole that they eventually evolve and grow in the throughout the time course of the universe. So we can understand that also. And obviously I told you about the objective earlier also, like I would like to estimate the mass measurement, and obviously like to estimate the BLR size based on H alpha or H beta optical range emission lines. And then I would also like to verify the same BLR size luminosity that I have shown for supermassive black hole, whether they could be extended for the lowest luminosity end of the plot or not. So for that, what we have done is we have used ARIES facilities. The telescopes here, like 1.3 meter Davison fast optical telescope, which uses Endor 2K CCD. We have used this telescope for photometric measurements, And then we have for spectroscopic measurement, we have used a 3.6 meter Raman optical telescope. And the instrument that we have used here, which is onboard dot, is ADFOS, uses 4K CCD. So what we did is we tried to observe the source for 2 days continuously from both of these telescopes simultaneously. And this is basically the table for the number of epochs of observation in the different filters. So for photometric observations, we took 1.3 meter default, and we observed the source in V band, and then narrow filters such as H alpha and S2. And then these are just the number of epochs of observation for 3.6 meter dot that we did for spectroscopy. Now for the construction of light curve and the spectroscopic light curve and also the spectroscopic reduction, what we did is so this plot, so this image at the left, you can see that it's a V band image of this NCC 4395 taken from 1.3 meter default. And what we did is for construction of the light curve, we did differential photometry. So this agent, which is supposedly at the core, and we took these 3 standard stars, and we reduced it by using Python module SEP and also from Darfort. And so here you can see this is the light curve for the source. And here on the y-axis, you can see this is the differential instrumental magnitude versus the time in MJD. And this is for both of the days. So in the first 3 panels, you can see that it's basically the differential magnitude of the source with respect to the standard star. And just for the sake of the integrity of this variation coming from the source, what we did is we also tried to plot in the last 3 panels the differential magnitude with respect of the standard stars also. You can see that the variation of the standard stars along the course of the time is almost constant. So we can say that the variation that is coming is profoundly from the source only.
Shivani, the thing is that there is ambient starlight around the AGN, right?
Yeah,
so
yeah.
you need to probably subtract some of the galaxy contribution.
Yeah. So so that's also one of the problem with the source, is that it is contaminated with the whole galaxy light also. So yeah, we try to look into it. And then okay. So for spectroscopy, initially for observation, what we did is obviously we need a better flux calibration because of the problem in constraining its variability. So what we did is we kept the slit like this, so we can observe the standard star and the core simultaneously. So we recorded the spectrum of both the core and the standard star simultaneously, and then we reduced all the spectra with ARIES software. So this is one of the spectroscopic spectrum of single epoch spectrum of this source. And you can see that there are various prominent emission lines here, including the H beta.
3 minutes.
Okay, including the H beta, H alpha, and obviously the narrow emission lines like O3, S2, and N2. So we did. So obviously it's a CFOT one, so it will have a broad and a narrow emission line component. So we decompose it these emission line components using PyQSFIT module. And we took care of the broad H alpha emission line. So for spectroscopic light curve, what we did is we just for continuum luminosity at 5100 angstrom, around 5100 angstrom, we just integrated that region, and we have the flux here. So we have the flux at each time sample, and hence constructed a light curve. Now for H alpha, what we did is we modeled this line, and then we integrated this particular region, and again we got the H alpha emission line light curve. So this is the light curve. So obviously the first panel I have shown you, this is the photometric V band light curve. And then for spectroscopy, these second and third panels are there. So this second panel is the continuum at 5100 angstrom. That is that is there for both of the days. And the third panel is the H alpha line light curve. So obviously you can see that there are gaps. So for particular days, there were gaps because of the technical difficulty in the telescope. So what we did is we just distributed the light curves in part 1, part 2 of the 10th March and part 1 and part 2 of the 11th March. So now that we have the light curve for lag estimation, we used different lag estimation methods. First is the interpolated cross correlation method. It just uses cross correlation technique. And then for javelin, it just models the continuum light curve. And the initial light curve will just be the shift scale and smoothed version of the continuum light curve. Now for the lag results, just because of the gaps in the light curve, what we did is we took the lag limit to be 200 minutes. And then we estimated the lag between the V band versus the H alpha line light curve. So this is the CCF results. You can see that the peak is little bit inconclusive. So Javelin rescue is it. So what is you can see is here is that the light curves are constrained very well here along with the error. And there is a very defined peak here at 56 minutes. So we say that our BLR size is 56 light minutes. Now that we have the BLR size for line width calculation, I have constructed this mean spectrum from all the around 100 of spectra available to us by dot. And then use this particular H alpha line for the line width calculation such as FWHM or sigma. I've used sigma for line width, and then for video factor we took 4.47 from Wu et al. 2019, and then from all these three parameters we have this black hole mass as 1.73 into 10 to the 4 times the solar mass, which is basically under the range that is given from previous studies. And the continuum luminosity we got is 10 to the power 40 ergs per second. Lastly, for plotting the source in the radius luminosity from our own results, you can see that our source is lying over there, and it follows the extension of this RL relationship of the supermassive black hole. So just to summarize and give you a little bit of future perspective. So the black hole mass we estimated as this based on H alpha. And then since we have also monitored the source in the S2 and H alpha filters, so we also like to confirm our study by using photometric reverberation mapping. And then also since you see that this source follows this radius luminosity relation of supermassive black holes, so we would also like to extend our study by studying more intermediate mass black hole AGNs and who's having luminosity less than 10 to the 41 erg per second, and just check the relation whether they also follow or not. So yeah, thank you.
Thank you, Shivangi. Now the floor is open for questions. Jatubal.
So as you showed that many other authors have measured the black hole mass for this object. So what did you do here that is different from the previous work?
So first of all, for observation perspective, what we did is I've shown. The problem with this source is the flux calibration issue. So what we did is we tried to observe the standard star along with the AGN, and hence that could just predict the exact variability. We can refine our variability from that.
Other questions?
Nice one, Shivangi. So since the lag is very short in this AGN, I think this will be very nice because you are cross correlating H alpha with V band, right?
Yeah.
V band is a proxy for this, right?
Yeah.
So people who are doing disk reverberation mapping, they are finding that the lags they find for reprocessing in V band is larger than expected, and they think that there may be some kind of contamination from the VLR in the V band itself.
Yeah.
So when you are cross correlating with V band, so there is some contribution of the VLR, not just in H alpha, but in V band also.
Yeah.
So it may be nice to look at it from
Yeah.
some cloudy or some other modeling.
Yeah.
Amit?
Very good work. In your some of the light curves I observed, there are very fast variation was observed. So my first question is, are they real? And if yes, then how you interpret them? Like this,
Okay.
you see somewhere around the second part, there is a very rapid flux change.
Yeah.
And in another light curve, there are a lot of this kind of fluctuations working. So I can understand that it's very rapid fluctuation because they constrain a lot of emission sizes and mechanisms by which the variability is reduced.
So, yeah, so
that's
when we
my-
add, so this is basically the observations and the experience.
So when
So,
the-
but they do not interfere in the lag estimation.
The
much.
one
No,
possible
I'm not interpreting.
we cannot just say that it is spurious. The one thing would be you plot also the FWHM variation.
No, that,
Seeing variation in the night, you see whether this has something to see.
that is done, that's done. So those points, one point on either, right? So that one, it doesn't affect the lag estimation and mass estimation.
But we can just say that it is
Yeah.
In next plot, hopefully next plot,
suddenly it increase.
go to next plot.
The one which you have flux calibrated.
Lot of
The spectroscopic
Yeah.
light, yes.
Yeah, spectroscopic.
Going the
wrong way.
Yes, so if you see here,
The trend is there.
like if you see that in third one, something is going down and suddenly 2 points goes up. So if that is true, then we are seeing some very rapid change in the flux, and that can constrain lot of things. So that's my whole point. Means if it is true, then probably it's worth looking into the things.
Yeah.
Can I just get a quick question from?
Yeah, last one, yeah.
So it seems that the error bars in the 5100 angstrom flux, sorry. Yeah, the error bar in the 5100 angstrom flux and the H alpha, they are of the same size, but you would expect the spectroscopic data to have larger error bar. Can you comment on that?
I mean, there were fluctuations in the spectrum also, so it was noisy. So maybe because of that also added up in the error.
Okay. Fine. If there are no further questions, let's thank Shivangi and all the speakers in this session. It was a wonderful first AGN session. Now, I think we for tea, and we gather at first the group photo, and then we gather at 11:25.
Was this session till 11? Was 11 the sketching time? 10:50. So my promise.
No, I have a Google.
I believe if you don't have movies, then you can just give the PDF.
Like to.
तो आप लोग या मैं
Google भी, right? Must not be. So I will open it for. No, I don't want to edit. Okay, so you don't want to log in. But you, I simply the link and it can open with anyone with that. Okay. So can you send me an email? No, you just send me. Okay. My email is
GOPE PS in Paris, Goku dot PIFR it's data instrument, yeah, at gmail.com. I just replied to this email. Okay. Yeah, that's me. Yeah.
Okay, I just sent my.
Yeah, sure. So I will send the link to you so that, yeah, thank you.
Easy. Just please email login कर दोगे सर कैसे बात है या फिर ऐसा करेंगे तो चाय के बाद में कर दूंगा ठीक है
I think, the return.
अरे HDMI नहीं चल रहा है क्या?
इसलिए भी चल रहा है, बट उसमें प्रॉब्लम ये है कि जो जूम पार्टिसिपेंट है उनको अपने स्क्रीन चाहिए।
अच्छा
अच्छा, तो यू हैव यूएसबी कनेक्टर, यूएसबी नहीं हो तो मेरे पास है, मैं लेके आया हूँ, जस्ट वांटेड टू इश्यू दैट। नो ओके ठीक है, आपकी थी वो अरे वही चलो उनसे अभी अच्छा, तो प्रोजेक्टर से कैसे कनेक्ट करेंगे? आपकी पहली टॉक किसकी?
ये सेकंड है, पहले
सुवेंदु की है, फर्स्ट सुवेंदु सबकी। अच्छा, सुवेंदु का मैच है ना, तो ठीक है, अच्छा दोनों का जस्ट सेकंड ना, एक एक्चुअली मेरे गूगल लिंक शेयर किया है, मैं उस लॉगिन करूंगा अपने उसको।
इसमें तो बहुत सारे ये बटन है, यूज करेंगे
तो या तो आप मेरे को मेल कर दीजिए,
मैंने तो कॉपी कर दिया। एक बार इसको आज करके देख लेना, ठीक है, बिजनेस कॉपी कर देंगे।
पासवर्ड इज 14 डॉट्स। बाबू को नोटिफिकेशन जा रहा है,
वही
वो टू स्टेप नोटिफिकेशन हो गया।
ये वाले सिस्टम में डाल दूं क्या ये?
हाँ मैं ट्राई कर दूंगा सर, जस्ट सेकंड हो गया। इसके बाद जो है ना, एक ने मेरे को मेल की है, तो मैं देख सकता हूँ कुछ आगे
ठीक,
ऑडिटोरियम में साइज बढ़ गया है,
ऑडिटोरियम भी एक्सपेंड किया ना उधर वाला।
एक्सपेंड किया,
हाँ, ऊपर में
दीवार तोड़ा गया,
क्लोजर से ये है ना,
दीवार तोड़ा गया।
हाँ दीवार पीछे ये वाला
पहले
थोड़ा
तो यही था, ये जो पिलर है इधर तक ही था ना।
हाँ ठीक ठीक।
दिस वाज डन बिफोर यंग लास्ट ईयर, राइट?
यस, जस्ट बिफोर दैट। इसको स्टालिन का है, वो तो ये ऑलरेडी
छोड़ो ना, वो तो हो गया है।
तुम्हारा अभी आया नहीं शायद, तुमने भेजे होंगे।
मैंने आई हैव कीनोट सर का सर भेजा नहीं है मेरे को, आई हैव कीनोट।
अच्छा,
शुड आई ईमेल इट टू यू? आई आल्सो हां, अगर ईमेल करो ज्यादा अच्छा। व्हाट ईमेल? मैं यू टाइपिंग kumar.suraj.
is it Paul in this and ये सुवेंदु के जो लिखा है ना, उसको ओपन करना, देखता हूँ कि खुल रहा है कि नहीं। और नेक्स्ट ये कभी चेंज तो नहीं हो जा रहा है पैटर्न?
1 सेकंड, अभी पॉइंटर लगा नहीं है।
हाँ, इसमें जा रहा है। शाबाश,
स्लाइड है बाबा, काउंट करो नंबर,
ज्यादा नहीं है ना, 18
ठीक है, तब ठीक है, ठीक है, तो मैं इसको डाउनलोड कॉपी मार के आप मेरे को मेल करिए, मेरे को क्या करूँ? आपका क्या है? कीनोट है, आईपैड। तो तुम्हारा ये कनेक्टर बैक कनेक्टर है, मेरे को जूम लॉगिन करना है, तो है आप जूम पार्टिसिपेट में स्क्रीनशॉट होगा, यूज करना है, मैं शेयर कर रहा हूं, बट ये डायरेक्टली कनेक्ट है, जो भी आपकी स्क्रीन है अब आपके लिए यूज करना आप ठीक है, मेरे को कीमत फंक्शन बताओ, लेकिन लॉगिन when people can hear me from, like you will be normal. नहीं माइक माइक इसमें आई विल कीप myself in mute तो इको नहीं करेगा 4 5 6 9 3
It is already.
For small letter ARIES 1 2 3. Is connected in what? To the screen. What is this? I'm sharing my screen with Zoom. The people who are joining via Zoom, they will see my screen. Let me see. हाँ वही बोल रहा हूँ ना क्योंकि मुझे लगता है बड़ी प्रॉब्लम नहीं प्रॉब्लम यहाँ पे ये जीमेल तो कहाँ से कौन सा प्लेटफॉर्म मेरा ये आपने को जीमेल कर दिया स्लाइड पे
क्या है
आई हैव 3 नोट my point is that since if the screen is already showing some other screen, why don't you first close that? Then it will show. तो अगर एक प्रोजेक्टर पे आप दो जैसे कनेक्ट करोगे तो वो सही रहेगा ना कैसे कनेक्ट करोगे? जैसे सर नहीं मैं आपको आपकी ये वाली प्रोजेक्ट पर हाँ अब नो सिग्नल है ना नो दैट्स तो हियर See again? Another point I will go here. Okay. Sometimes only post you have to allow me to share the content. You the permission. ठीक है ना all participants you share allow करो what ये also लॉग इन नहीं उसके लिए सिक्योरिटी कौन सिक्योरिटी ठीक है शेयर अभी आप देखिए शेयर हो रहा है आपसे शेयर अब आप हाँ अपना उसको या आ गया देखो आया ठीक है छोटा स्क्रीन है अरे बाबा तो फुल स्क्रीन कर लेता हूँ ठीक है अच्छा एक सेकंड रुकिए मैं अपना जूम पे देखता हूँ वहाँ क्या थोड़ा ठीक है ठीक है बाबा ठीक है आ गया ना
Okay, let's start the second session. We have 4 talks, and first by Shivendra Rashid. Before I begin, a kind request to all the participants: if you have questions, please hold on to your questions and ask at the end. Otherwise, it becomes a bit difficult. Also, it breaks the flow of thought of the speaker as well. If you have burning emergency questions or something's on fire, please shout. Otherwise, please hold on to your questions. Okay. All right. The next first talk, Shivendra Rashid on supermassive black holes in highly luminous AGN. I'll give you a warning at 20 minutes.
So, very good morning, everyone. So I'll talk about supermassive black holes in high luminous AGNs. So these are basically on the perspective of observations and what are the current observations are and what are the limitations or difficulties. So we know that every massive galaxy hosts a supermassive black hole at the center. And if you see, the black hole mass is strongly correlated with the stellar velocity dispersion. So here we have black hole mass starting from 10 to the 6 to 10 to the 10 solar mass. So these are also supermassive black holes. And this is correlated with the stellar velocity dispersion. This is true for AGN and also normal galaxy, right? And this is remarkable, and this suggests that the black holes which are sitting at the center are affecting the galaxy and they evolve together. Now, if you see the distribution of masses across the universe, the plot looks like this. And here you have the black hole masses on x-axis, y-axis, and the x-axis is the redshift of this. So this plot contains 0.5 million quasars that was observed by SDSS. This is from our catalog, SDSS DR14 quasar catalog. So as you know, the black hole masses are estimated by different emission lines. So, for example, at low redshift, we have the H beta emission lines, which are in the optical wavelength coverage of SDSS. If you go to the higher redshift, the line will be redshifted, and so you will get the MG2 lines. If you go further out, then you will see C4 emission lines, which are coming into your optical spectral coverage in the optical domain, right? So anyway, and so what this plot is actually showing, the lower limit, as you know, that this is a flux limited sample, SDSS, Malam-Coase bias. And on the top panel, it is showing that there are no massive black holes with ultra massive, like 10 to the power 10 solar mass or beyond. And this curve is almost going from redshift 0 to redshift 4 or beyond, right? So if you find a hypermassive black holes, it's difficult to explain how they form and how they evolve to that one massive, right? So the main thing is that all the masses that we are showing here are estimated based on the simple scaling relation, and it looks like just this, right? You have continuum luminosity measured in the optical wavelengths, let's say 5001 angstrom or other line-free region, and the width of the emission lines, the broadening of the emission line, considering this is doubler broadening. Now, recently, JWST started their observations and newer results are coming. So if you see that recent JWST observations, so this is the very broad line quasars at redshift 8.5. Okay, when the universe was only 0.5. This is very broad line quasars. We see that H beta emission lines redshifted to the 4.6 to somewhere around 4.8 micrometer region. And here you have the strong H beta emission lines, and we have O3 emission lines also present. The broadening is around 3000 kilometers per second. Now, so this implies, similar based on the scaling relation, this implies a black hole mass of the order of 10 to the power 8 around. So if you plot all the JWST results, at black hole mass as a function of redshift, these are recent results that are coming from JWST. This one, and all these objects are JWST results. So here, the main thing is that how you explain the formation of these seed black holes. This is now it's known that if you just have a 100 solar mass black hole and it is accreting at the Eddington limit, you get this lower curve. This is enough to explain these objects. But if you go to the higher redshift, that is the broad line AGN that was found in this part, there you need another mechanism. People thought that this is DCBH, direct black hole, with mass 10⁴ solar mass and accreting at the Eddington limit. So now, if you have this black hole mass and the stellar mass relation, these objects actually, the high redshift objects are actually deviating strongly. So in the local AGNs, you see these black hole masses are only 0.1% of the stellar mass. However, higher redshift, they are located around 0.3, something 30% of the stellar mass. But so the fundamental correlation that I showed earlier, this M sigma relation, however, they do follow a little bit on the M sigma relation. Some slight offsets are there depending on the masses that are estimated. Here, in dynamical masses, because stellar masses are not enough to explain, so you need the gas and other things. So dynamical masses, they do follow the black hole mass and dynamical mass relation. Now, again, these are based on the scaling relation. So only you have this simple continuum luminosity and the line broadening, and you are estimating masses. So, and the method that are used to derive the scaling relations are the simple reverberation mapping relation. Siddhangi in the last talk talked about the reverberation mapping relation in detail. So just to give you an idea, in short, you have a continuum variation coming somewhere close to the black hole. This is the optical continuum we're talking about. So here, this is optical in UV. So this continuum flux is changing over the time, and if you monitor significantly, you will see the variations there. The UV and optical photons will ionize the emission line clouds, which are further out. So you will see the emission line variations also, but there is a slight delay, and this delay corresponds to light travel time from this to this. But we are talking about the average size of the BLR. So then you combine with the mass of the spectra. Spectra gives you the FWHM, and you get a simple relation, virial relation. Black hole mass you measured F RBLR sigma square G. Now the problem with the F is that it's an unknown factor. So this introduces scatter around 44 decks, that is 44% in the black hole mass measurement. And so how we constant so far is that we consider the M sigma relation for normal galaxy is valid for M sigma relation for AGN also, and they follow the same relation. So we just make a scale this thing. Eventually, the goal of these programs is to estimate the structure and geometry and the kinematics of the central engine, so that it can be constant also. So, what? So, the relation that was also shown, this was back in 2013, and this is a very nice correlations. We see that BLR size is strongly correlated with the luminosity. The slope is around 0.546, which is also agrees with the photoionization modeling, and the scatter is also 0.13x, not that much high. So now, what this is in the H beta region. What happened in the MG2 lines? People did reverberation mapping also, and we have also reverberation mapping in the MG2 lines. So we also see the same correlations exist in the case of MG2 lines. So the size of the BLR is correlated with the 3000 Armstrong continuum luminosity. The problem with the MG2 reverberation mapping is that you have a very less number of objects, because you need to get the MG2 lines in our optical survey, because we are mostly doing the optical domain, right? So, and this dynamical range is very small. Then these are the green points are basically the SDS's recent observations, which actually is survey mode doing observations, and it's introduced a large amount of scatter. In the case of C4 also, we have the scaling relation, because as I said that in the C4 masses, we also need to measure based on the high resolution object. So this is C4 line size versus continuum luminosity at 1350 Armstrong. we see that scatter is again very large in C4. The problem with the C4 is that you have a strong wind component because its ionization potential is close to the black hole. So its ionization potential, and also you have a narrow non-varying pore component. So it's very difficult to model and extract the FWHM of the C4 emission lines, which are Doppler burden. So we also did some people did some dynamical modeling. We also attempted some dynamical modeling for those objects which have a very high quality reverberation mapping data, because note that you need spectroscopic monitoring, you need spectra for a large duration of few years, and the spectra has to have a very high SN, right? And so here are some examples. This has been done for only 10 objects so far, and all of them are intermediate, little bit lower side of the luminosity range, because they are easy to monitor. You can do few months of monitoring, and then you can get a decent quality of data. So the thing is that this is data, and here's the model. The model is just a simple geometrical toy model. You have a large number of line emitting clouds. So clouds are basically orbiting around the black hole. It has a different kind of velocity profile. And then you try to explain all the spectra that was observed and all the continuum variation that was seen during the monitoring. So here I'm showing the 3 examples of the geometry of let's say PG 1310, 1511, and 4593. What we see is that for different objects, the velocity profile is very different. We see the signature of the Keplerian motion, but we have the significant component of inflow and outflow. So here, as you see, that outflow is this blue color. This object is completely showing the outflow with and this object is showing the inflow signature. So now the inference is that we found that BLR geometry is basically thick. It has a particle thickness. It's basically viewed close to phase on with a inclination angle typically around 20 to 30 degree, and it's a Keplerian motion dominated, but with having inflow outflow signature. And these dynamical models allows us to estimate the scale factor that was sitting at the real mass estimates, and this turned out to be 10 to the power. So it's 0.57 log in 0.57. Now, the scale factor also found to be dependent on the inclination angle. So if you estimate the inclination angle based on this modeling, you see that the A factor changes as you go to the higher and higher. So phase 1 to close to phase 1 to H1. So now these estimates are very difficult to do. You see the error bars on the measurements are very high. For example, consider these objects goes from 30 degree to 70 degree inclination errors. So these are very difficult measurements. So people still using a fixed scale factor around 5.5 and now we see that the BLR also breathe. What we mean trying to say by breathing is that if the continuum flux increases, then we see the line emitting clouds also who are emitting for, let's say, H beta or H alpha lines, they are coming away. And if they're coming away, then delta V, which is dominated by gravity, so it's lower. So flux is increases, line with it decreasing. So this is called the breathing of the BLR. And this also suggests our real assumptions was correct. Now, back in 2013, this plot I already showed. This is a sweet spot of the seismic relation. Now, people started including more and more different type of samples, because these are all normal type 1 AGNs have very less different kind of properties. So people included very high accreting AGNs, and then the plots looks ugly, and it's becoming uglier and uglier. So here you have much more deviations from the normal size limit relation, and people also gave some justification for this. These are basically found to be the high accreting AGNs. So this relation may not be directly only depends on the size, this luminosity of the objects, but also the Eddington ratio or AP2 strength. So here is see, so these are nearlines about one object. So this is if you consider the AP2 strength into account, then the dispersion scatter reduces a lot. So Now, low luminosity end, you need to, if you want to use these relations as a benchmark to estimate black hole masses for all the AGNs. So for that purpose, you need to increase the dynamical range of the luminosity, right? So in the low luminosity range, that's Sivangi showed one example of NGC 4395. There are very less number of objects that you can do such monitoring, because simply the low luminosity objects do not show any variations. Variation is so low that you will not be able to detect. So many people have tried. We have tried also other cases. NGC 4395 is actually usually showing good amount of variations. For the high luminosity end, we need to explore more, because high luminosity range is the where JWST is also measuring the black hole masses, because these objects are very faint, right? So we need to see that how high luminosity range is behaving. Is it the same correlation we can apply, or is it somehow the masses are underestimated or overestimated? So for this purpose, I'm just going to give an overview of what our observations are suggesting. These are recent observations. So, for example, so we have started a monitoring of high luminous AGNs, and the problem with that high luminous AGN monitoring is that you need to monitor for a long durations, and this is not be possible within a duration of a PhD thesis or something. So this is not a thesis topic of anyone. So we have started 100 quasars from a mini quasar catalog. These are carefully chosen. We have done a lot of simulation to see that what would be the possible outcome for this kind of campaign. And initially, first year we have monitored the 100 AGNs, and we found that most of the agents are not showing any variations. Only 32 are showing good amount of variations. Only the variation is stochastic, so you don't know when they will vary. These are simple non-radio detected agents. Okay, so you have so first two objects were published in our earlier paper in 2019. That time stream monitoring was going on, so this was only 1 or 2 years of data that were used. So this is a distribution of luminosity and redshift for our objects. These reds are our object, and other objects are from different survey. Let's say SE, MBH, SDSS, RM, and LAMP. LAMP is the agent monitoring program. And so redshift range is around 0.2 to 0.4. So H beta is present there in our objects. Now, what facilities? Because to start with such a large campaign, you need different facilities to observe. So we need spectroscopy as well as photometry monitoring. Few facilities we have been using. This is the LIC 3-meter telescope and MDM 2.4-meter telescope. These are for spectroscopic measurement. And for photometry is MDM 1.3 meter, LOAO, MDM 2.4 meter, LCOGT. Photometry you can do with very less time, and it's very easy to do. So we usually try to do have more cadence in photometry compared to the spectroscopy. So as I said, the duration of these programs are very large. So this is the monitoring duration was 6 years. It was started in 2015 and it's ended at the end of 2021. And the photometric cadence was once per week. So we observed all the targets once per week. And for spectroscopy, we did 3 weeks of monitoring. Like every 3 weeks, we have one spectra for all these targets. So to show you some of the spectra. So these are basically mainly the mean spectrum. So you get 100 spectrum for one object. And then you can take the mean of these objects and you get a very high signal to noise ratio spectrum, which is this one here. You from the first instant, if you see the line profile, their profile is very different. So this is another object EG0026, and this one is completely opposite of, let's say, this one. And there's another one which has no visible nano component. You can also do the calculate the RMS spectrum, because what we essentially need is to measure the variable components, because that's a central engine is responding for broadline cloud. So the variable components you can find out just taking the RMS spectrum. So you can take all the spectrum and take the RMS of these. And RMS spectrum will isolate the narrow components of those So you will not see the O3 components are, so O3 have gone here. So only the broad components are present in these objects. Now, once you have the spectrum, an AGN spectrum is very difficult to measure the line width. You cannot just simply apply this delta V like Gaussian profile because they are not non-Gaussian. So here, what we do is we have to remove the underlying AP2 emissions, which are seen in AGN spectrum. So this is the AP2 bump here, this both sides of the H beta line. You have the lines are broad, so it's blended with O3 lines also. So we have to remove this component also. So we have multiple components modeling of spectra, just power law, AP2, then host template. Host galaxy also contributes. So we apply host templates of different stellar mass and age. So then we have narrow and broad components. And the broad components is the one which we are interested in. So this broad component gives us the estimates of the line width and other things. So now if you see the light curves, so just to give you some example light curves, here's two light curves are shown. So one is, this is the optical B band continuum flux variation. So this is the source is varying significantly. The telescopes, different color indicates different telescope that we have been using here. The lower panels are showing the spectroscopic light curve. Here the red one is the leak and the blue one is the MDM data points. And the background one I will talk about it later. So another object is shown here. Yes. Another object is shown here. This one is also showing. If you look at just this two light curves, you see some kind of offset delay in time, right? So this delay can be estimated. Size can be estimated just using different technique like cross correlation analysis or Javelin or Pyro or other thing. A different way to estimate that. So this we estimated the delay of these light curves, and for example, this one, look at it. Both the method Javelin and the CCF are showing the lag around 150 days. So that means the BLR size is allocated around 150 days from this H beta emitting line region. So and if we shift one light curve with respect to other, we see that they are matching. So here you see we shifted the light curve, the continual light curve is shifted toward this, and they are closely matching each other. Now we have since these are multiple objects were observed, and we need to check the reliability of our estimates. So first thing, we compare different methods, the lag estimators, if they are correlated or not, if they are giving the similar consistent result or not. If they are not giving the consistent result, we have to discard them and check what's going on there. Is it we have to check other things. For example, the maximum correlation coefficient, is it greater than 0.6, or the correlation is significant or not. Then we also check if there is a fake light curve. If you generate the fake light curve for a given object, you can generate 10,000 light curve and see that those fake light curve can generate similar correlation or not. If the fake light curve produces similar correlation, then your correlation analysis is not good, right? So we have done various simulations to reliable estimation of lag, and there are 25 AGNs with reliable lag. Here is the final size luminosity relations using the lamp. This is SAM targets are red in here. This is BLR size luminosity relation. As I said, that this plots has been now there are multiple objects have been added. This is HDS revolution mapping, which makes which are objects are much below. Some of the objects are above also. So we this different kind of fitting of these linear regressions. So if we include only the good quality measurements which are coming from the LAMP observations and our SAM target, we found the slope goes like 0.44, which is much slower than the previously slope that was 0.56 was used. Now we also have some H alpha initial line light curve, so we can also measure the H alpha lag, and we find that H beta and H alpha lag is correlating and they're consistent. So we can plot this volumetric luminosity, which is just measured from the monochromatic luminosity at 5,100 angstrom, just scaled in that. and with the function of black hole mass here. The SAM target is located here. They are mostly accreting around 10% to close to Eddington limit. There are other objects which are high accreting objects. Agent monitoring has been done. They are even beyond this limit. So this is the Eddington ratio distribution of all the objects that we have. So now this deviation that we said the slope is shallower. Is it because of the any other parameters like accretion rate is the main parameter that is creating the deviation? To investigate this, we plotted the Wheeler size as a function of Eddington ratio. What we find is that there is a correlation, but we think that this correlation could be introduced by self-correlation. What I mean by self-correlation, if you see the Eddington ratio, that is just the ratio of bolometric by Eddington luminosity. And bolometric luminosity is based on continuum luminosity. So size is based on continuum luminosity also. And the black hole mass is also depends on the luminosity, scale with luminosity. So it just maybe self-correlation and the zone of avoidance. What do we mean by zone of avoidance? For a given luminosity, let's say 10 to the 45 arc per second, there are almost no type 1 AGNs having FWHM lower than 1,000 kilometers per second, right? So this is true because we define the type 1 AGN as a more than 1,000 kilometers per second having right? So so Eddington ratio is as we said, that is maybe self-correlated, but we can do some estimates based on other parameters like its strength, and we found that there is a correlation, but the correlation is very weak. The error bars are huge here. Okay, so we currently do not know what is the exact mechanism that are affecting for these deviations. Maybe the ionizing ACD, because we use here the continuum luminosity at 5100 Angstrom, and it may not be proper to use that. Maybe the UV luminosity would be a better proxy, but for that we need to much more. Usually it shows strong correlation, UV and optical luminosity at 3000 and 5000, but it's not always. So we need to check this. So I'll just summarize the talks. We get shorter life for high luminous AGNs, which means that the black hole masses are actually overestimated if you use the canonical relations of size relation. So the black hole mass should be slightly lower for the high luminosity range. Then dynamical modeling would be interesting because this would allow us to understand what are the scale factor actually, because we have used a scale factor here, and that can be done for our targets because they are very high quality data sets that we obtained. Way forward, what would be the best is to increase the dynamical range of this relation, because you see the luminosity is still around, there are very low number of objects in the high luminosity end. So we would like to expand this, but we think that SDSS black hole mapper program, which is this 2.5 meter telescope, you have a black hole mapper program as a part of SDSS 5. So this will spectroscopically monitor around 10,000 quasars, and for over the period of few years. And it will be repeatedly carry out spectroscopy. So maybe for given objects, 100 or more than 100 spectra will be obtained. The luminosity range here planned is 45 to 47, and its redshift range is 0.41 to 4.5. Then we might have the answer if the relation is exact, how much shallow or what is the exact thing. So I will finish here and.
Thank you, Shubhendu, for the nice talk. A few questions. CJ?
Very interesting talk. I had a question on one of the slides in the earlier part of the talk, where you had shown the black hole masses as a function of redshift.
Yes.
So one was a curiosity question and one was a follow-up question. The curiosity question is that suppose here the assumption is that the black hole, you have a single supermassive black hole in the AGN.
Yes.
If you have a binary black hole, how does the M sigma relation get affected by that? That's the curiosity question. And the question about that slide was that, again, with the assumption of single black hole, you will see a certain kind of a trend from low redshift to high redshift.
Yes.
Would that trend not be different if you assume binary black holes which are evolving with redshift? So that relation, that curve should change, assuming the hierarchical clustering evolution models of galaxy. You should have more binary black holes at a later point of time.
Yes.
So that curve should have changed.
Yes.
So these are my two curiosities.
Yeah, so from observational perspective, we have not much detection of binary black holes. So, that may affect the M sigma relation because how much is the primary mass and what is the secondary mass related to that. So here we are considering a single black hole. So it's difficult to tell what will be the exact effect of the M sigma relation by observation perspective for binary mass.
These are observational data.
These are observational data, but binary black holes observational data are.
We don't know if it is an absolute or point source. How do you know it's a binary or not?
No, that's correct. I mean, the image, possible candidates. So you can, like for example, candidates, there are candidates OJ287 or some other candidates are there. But
so one point is to
here is just you can
one way,
binary.
From observational point of view, one way to do that is to take a model in which you have only single supermassive black hole and compare the probability of this model being the true model compared to a model in which you have a mix of single and binary black hole, and do a Bayesian analysis to find out the odds factor of which one is being. So that's one way of observation. I understand that there won't be a direct signature, but can you extract this kind of?
Here, for example, we see all the emission lines that are mostly based on a single black hole because it's just some kind of outflow signature is that there's no very less number of objects as double peak emission lines, and that may be associated with also this Kepler profile. But mostly we do not know that how much fraction would be the binaries in here. So I mean, this is a nice thing to try.
that could be put as a parameter.
Yes, that's right. That's nice. We can discuss more about how to.
Okay, one more question.
No, but others.
Okay. Other hands.
Is there any consensus? Is there any discussion and consensus about the origin and the stability of these vela regions about the Kepler plan?
So there are actually few people do modeling. So let's say Bojana C is doing modeling, and there are other modeling people are doing. So there they say that this will be stable over the time scale of dynamical time scale. So the revolutionary modeling is much shorter than the dynamical time scale. So they will be stable, but there are, let's say, inflow, that you see the inflow motions are there. There are some groups who monitor these objects, let's say 10 years and again 10 years and again 10 years, and they try to model each data sets differently, and they count that the structure evolved over 10 years or depending on the luminosity of the solar.
Origin of these vela regions?
So the clouds are basically we see the wind from the dust wind from the outer accretion disk. They are going up, down, and then they exposed by the radiations that are coming from the central unit. Or then people say the tail doing models are there. So they say that the dust sublimation radius, the dust sublimation, dust will sublimate at temperature 1500 Kelvin. So that dust sublimation radius, where the dust torus is there. So there, this radiation pressure, the clouds goes up when they evaporate, get the UV photons, and then they ionized, and then they fall down. So these are basically the PLI clouds are creating. So there is a continuous part starting from the dust torus to the accretion disk. The cloud is all only because they are exposed to the continuum radiations at a certain distance. So that's
okay. One more question, Bhagat.
Yeah. So I have a question regarding the scale factor. You showed some dynamical modeling to constrain the scale factor. What do you, according to you, would be the variation of scale factor with redshifts? Because more and more quasars are getting found at higher redshifts. So would you expect the scale factor to evolve with redshifts as well?
So we think may not evolve. The main factor that is affecting the scale factor is the geometry of this thing. So geometry, if you see if I see the FWH distribution across the redshift for all the quasar, you see the FWH varies around, it stays similar. Only the luminosity which is changing in the as we go outer. Right? So we think that across the redshift, it may not change. Mostly the luminosity and generations and the thickness of the BLR region and what is the vertical height, that will impact more. And
but don't you think that at higher redshifts there will be more covering fraction of the BLR because it will be more dense environment?
So there is dust is playing a role. This is JWST or most of the observations are deeply wooded region, right? So there we think, but to go that far, it will be.
Okay, I'll unfortunately have to stop this discussion. Thank you, Shubhendu, for the very nice talk. Okay, for the next talk, Vaidehi.
Yes.
Blazars and course.
Yeah.
Yes.
There is also a Slack channel that they have created.
Yes, you can also post your questions on Slack channel and we can follow it up at the end of the day.
Yes.
Vaidehi.
Okay. All right. So I hope you can hear me well. I don't get that. I can.
Precise.
Yeah. Okay. So hello everyone. I am going to talk about engines, and this is a Fermi blazar, and this is a center. So this is center engines of a Fermi blazar, right? So title is okay. So coming back to again the blazars, you know that some brief introduction, just refreshment, is that we know that these are active electric nuclei boosting jets, and jets are pointed towards us. Typical angle is around 10 degrees or less. And the sources that have off-axis jets, they are called radio galaxies. And we have a fully developed theory so far that what we know in our conventional understanding, that we have a plasma blob moving toward the observer, emission is boosted, then we have the Doppler factor, and then this has a profound implications on the observer CD. Okay. Now we also know that blazars are classified as flat spectrum radio quasars and BL-like objects. FSRQs are those sources that show prominent emission lines in their optical spectrum, and BL-likes are sources which show weak or no emission lines. And the criterion that have been adopted is that rest frame equivalent width is high value strong. If it is more than that, it's a FSRQ. If it is less than that, it's a BL-like. Now the point is that historically people have proposed that this BL-like don't have emission line probably because the radiation that we receive from them is so strongly jet dominated, because the continuum goes up and it completely swamps the emission lines, even if they are present. So this means BL-like also can be the same type of source like FSRQ, but in the jet boosting is much higher. But the recent observations in the last 2 decades or so, what has happened that we have detected several gamma ray detected BL-like objects where the emission from the host galaxies found to be very dominant, like the one I am showing here. You can see there are several absorption features arising from the stellar population. So in this case, the jet emission is not down, but still here we do not see any emission lines. So this gives the idea probably emission lines in BL-like objects are intrinsically weak. However, there are some cases where our classical understanding means in some cases we do see that the source which does not show any broad emission line in a high activity state, it reveals broad emission line in the low jet activity. So what to conclude here? The point we can conclude here is that a classification based on equivalence is not physically intuitive. It is based on just observations, and it does not tell us about the physics of the source. We have to come up with some other classification. So people have proposed in another method something called where if you try to measure the accretion rate in Eddington units, and then flat spectrum radio quasars are those sources that have this accretion rate or say accretion luminosity in Eddington units 1% of Eddington luminosity, more than that. In other words, they have like a radiatively efficient accretion. So since the accretion disk is luminous, corresponding it will illuminate the BLR clouds and BLR will produce strong emission lines. That's what we detect from FSRs. In BLX, what happened that the accretion process is relatively inefficient. So in that case, is that bulb is already dim. So BLR, what radiation it will receive, so what emission line it will produce. So that's why we don't detect broad emission line in BLR case. Now the problem here is that in the case of flat spectrum radio quasars, that is the sources that have broad emission lines, we can calculate both black hole mass and the accretion disk luminosity right from the optical spectrum. In the standard relation, Suvendu also showed some results. The point is that we know that these BLR clouds are orbiting around the black hole, so the width of the emission lines is directly correlated with the mass of the black hole. Fine. And since these emission lines are produced by the BLR clouds, so following standards like we know that Lyman alpha, H beta, H gamma, etc. other lines. So if we know the line luminosity, we can get an idea about the BLR luminosity. And since BLR is illuminated by the accretion disk, so assuming that suppose 10% of the accretion disk luminosity is reprocessed by the BLR, we can get an idea about the accretion disk luminosity. So from the optical spectrum, we can calculate both quantity. So we can derive L accretion divided by the L Paddington. But what will you do for BLX? Which show a featureless optical spectrum. We cannot determine real black hole mass or accretion disk luminosity from the optical spectrum. So this classification scheme, like based on the accretion rate, is physically intuitive. But we cannot use this technique on BLX because they simply don't show anything in the optical spectrum. So what we have to do, we have to identify a parameter which is free from selection biases, because whenever we talk about lasers, immediately people jump and people start telling that Doppler boosting and all these effects are there, so this correlation is valid, not valid, etc. So we have to find a parameter which is probably free from these selection biases, and somehow if that parameter is connected with the accretion disk luminosity, adding that. So to do that, this was the time when we were in our home during lockdown period. That was in the COVID time. So what I was doing that I took this catalog of the Fermi lasers, gamma resources, and then I searched for their availability of optical spectra. So more than 50% of the sample I found from the SGSS. But then I also went to the literature where I was searching, like if the source has a redshift, definitely some spectrum must have been taken at some point of time. So I started digging the literature, going to the paper where in 1917, 18, 19, when the spectrum was published. Whenever I got the spectrum, I took the screenshot, digitized that image, and so that we have the data. In this way, I was able to collect optical spectra of 1077 lasers, which includes both emission line sources as well as there are wavelets which show absorption features in their spectra. One example I showed earlier. And then I analyzed these optical spectra using a couple of softwares, PyQSOFIT for the emission line sources, and this PPX, which is the analyzed pixel fitting software for the absorption line sources, and then determine the spectral parameters, so the FWH of the line, stellar velocity dispersion, and all. So you know that for FSRQ, we have the case of broad emission line sources. This is the spectrum of 3C273. So using the emission line FWH and luminosity, and presuming that the BLR is realized, that means we can use the single epoch black hole mass calculation technique. So by knowing the continuum luminosity, depending on the wavelength line we are using and the FWH of the line, we can get an idea about the black hole mass. And since once we know the line luminosity, we can derive the BLR luminosity, and from that we can get an idea about the accretion disk luminosity. So this means we can derive both L accretion as well as L Eddington in broad emission lines. If we talk about the absorption line systems, so one thing, let us go at one by one. So by applying the PPX software, what it does basically, it has a library of different types of stellar spectra. So we have a template. And this contains a range of, like, say, metallicity of the different types of stars and the different ages of stars and all. And then you apply this software on the data, and it will do the iterative fitting. And then ultimately it will tell you, it will give very useful parameters: the age of the stellar population, whose optical spectra we are seeing, and stellar velocity dispersion, its metallicity, and all. And using now the well-known MC-MER relation, then we can derive the corresponding black hole mass. Now we have got the black hole mass in these kind of sources. Now question comes, how to determine the accretion disk luminosity? Lines are not seen. But what we can do, we can always determine the 3 sigma upper limit. Okay, so this means we know the spectrum. So then we say, then let us try to fit the Gaussian function. If the line would be there, its luminosity should be greater than something. Since the line is not there, so the line luminosity must be less than something. That's what was done here. This was using following chi-square approach. you fit a Gaussian function is assuming certain WHM value and keep changing its luminosity till your chi-square becomes poorer than the 3 sigma limit. At that time, you say this is my 3 sigma limit, so my line luminosity should be somewhere lower than this. It cannot be more than that. So in this way, now we have a 3 sigma limit on the numerator, and then we were able to calculate the denominator. So we are able to get a 3 sigma upper limit in this quantity. Okay. Now we have to identify the second parameter. So we found L equation by L integral. Now the other parameter. So one such parameter could be something called competent dominance. Here what I saw, this is a broad band spectral energy distribution or a CD of blazar. You can see typical double hump structure that these objects show. So the competent dominance is the ratio of the second peak, which is the high energy peak, or you can say inverse competent peak, and the ratio of the other one is the synchrotron peak, low energy peak. And this is the competent dominance. So simply, since this quantity is the ratio of two peak luminosities, this quantity is free from redshift effects. Okay, and it can be derived just from the broadband SED. The usefulness of this I will discuss a bit later. Now the point is that this kind of thing I was doing during the COVID, sitting at home and fitting the one. All sources 1077. Okay, so what it leads to? So now we have two quantities, both accretion disk luminosity and Eddington units, and we got the competent. So let's plot them. So then when we plot it, we got this relation. You can see there is a strong positive correlation between these two competent dominance and the accretion disk luminosity. And the red data points are where these are the emission line sources, where we were able to get the definitive value of the both black hole mass as well as the disk luminosity. And the blue arrows are where we had the 3 sigma upper limit in the accretion luminosity. You can see there is positive correlation, which was statistically significant. So what this equation, what this tells us? This tells us that competent dominance, because on the x-axis we have accretion disk luminosity in Eddington units. We have normalized for the black hole mass. So this tells us that accretion activity is somehow connected with the competent dominance. So this means even if we don't have optical spectrum, if we can determine the competent dominance of a source, we can get an idea about the accretion state of the source. So when I was in ARIES 2 years ago, so during one of the observing cycle, I submitted a proposal. What I did, I took the ANDA Fermi catalog and then I selected a few sources which are probably blazar, but due to lack of optical spectrum, we could not classify them. So that these sources are called Fermi blazar candidates. And then measuring competent dominance is relatively easy. I will show you also how. Because we are just seeing the overall data. We just need the overall SED. So I picked some sources that have competent dominance greater than 1. This means in this diagram, I am going towards the higher competent dominance value. So if this observation holds, so this means these sources are expected to have a higher accretion disk luminosity. Correspondingly, their optical spectra should show broad emission lines. Right? And that's what was done. And these are the that I got. Several of these sources, you can see there are broad carbon 4 line, magnesium, and we got up to redshift 2.55. Very high redshift layers also we found. Just by doing this exercise. So this tells us, one more thing here is that if there is a talk on blazars, it is not completed unless we talk about blazar sequence. How? So rather than talking about the people who do not know blazar sequence, basically it is the ratio of the synchrotron peak luminosity versus synchrotron peak frequency, and we see a strong anti-correlation. But that's why people have supposed it's like due to Doppler boosting effects and all. So now here what I'm plotting the accretion disk luminosity on y-axis, and on x-axis we have synchrotron peak frequency. So a strong anti-correlation we can see here, and this sequence is free from Doppler boosting effects. Okay, we are directly calculating value from the optical spectrum. So this means this sequence has a physical origin. Now looking toward the future, measuring competent dominance is much easier compared to getting the optical spectrum. Why we have seen in the radio band, we have several ongoing and as well as upcoming radio survey, VLASS, which is the very largest sky survey, LOFAR, which covers the megahertz frequency of the emissions. Then RAX, which is being conducted in Southern Hemisphere in Australia, and the square kilometer array, which is the upcoming one. You can see there are lots of ongoing also surveys in the optical band also, covering the entire sky, going for the very deep sensitivity. In the X-ray also, we now have the E, rho, theta and all. So the point is that these wide field all sky surveys will provide, or they are already providing, broadband coverage of the whole sky. So this means we can generate this kind of spectral energy distribution for a very large sample of lasers. So we can quickly calculate their competent dominance, and that can immediately give us an idea about the accretion state in that object, without worrying about getting the optical spectrum. Okay. So this brings me to my summary. And that. Good. Competent dominance, this can be used as a proxy to understand the state of accretion in lasers. And this classification scheme using competent dominance, it is physically motivated. It directly connects with the accretion activity. And it can be used, competent dominance based classification can be used to pick best candidates to do a number of sciences. One of them is finding FSRDs. Okay, if you are interested, this catalog of 1077 black hole masses, this luminosity, inverse competent, synchrotron peak, flux, frequency, etc. All this catalog is you can download from here. And I was very happy when I saw that Raman used this catalog and the result wonderfully explained. So basically, you can this talk was like a prequel of what you have done. Keep it that up. All right. Okay.
Thank you. You should have informed us. Will we?
No, but prequels nowadays come after the movie.
So thanks, Vaidhi, for the wonderful talk and giving us a lot of time for discussions, lots of hands.
Very nice talk. So I wanted to understand a little bit about the competent dominance work that you did. So it was model independent completely.
Yeah.
It is just fitting
the
polynomial function. So I wanted to understand in how many of these cases where your chi-square very good, or you were making a kind of a chi-square fit or something like that. How many cases were there with all the data that you had were very good?
Chi-square,
or what were you doing basically for that?
I was doing a polynomial fitting.
Just fitting, okay. And then you.
But I rarely bothered about chi-square.
You really.
Yes.
Okay.
Yeah, because you see the kind of data we have. It's like getting truly simultaneous observation across from radio to gamma ray is very challenging. Then the source we may not even get 107 sources. Okay, so I just presume that we also understand so by now that the most valuable sources are blazar, but even those sources they spend more than 90% of their time in the low state. So I presume that whatever the data I am collecting, they are mostly taken from the during average activity state.
Okay.
Okay. But still, then there are some data randomly they are fluctuating here and there. So the chi-square is bound to be is very poor.
Okay.
Thank you.
So this competent dominance is dependent on the Doppler factor.
Yeah. Okay. Fine.
Okay. So that's what is the competent dominance is gamma ray, ratio of the gamma ray and the sort of the high and low energy peak. So why would, do you have any insight into why would that be related to accretion?
Observational result I just showed you. You see, this is just observation. Competent dominance is directly related with the accretion activity.
But physically motivated.
Yes, physics. See, physically I can. It's very simple. Right? You suppose if the accretion disk is luminous, right? So corresponding the photon field surrounding the jet is very luminous. You have a dense photon field surrounding the jet. So the primary mode of gamma ray and high energy production will be your external component. So the second peak is expected to be very dominant.
Yeah. But it depends on basically how you are seeing how the photon field is distributed.
Yeah. So, but whatever see, when we consider anisotropic distribution also, in that also it will be easily dominated.
Okay, next question. No, you have it first.
Very nice talk. So this is about you are using M sigma relation, which are usually done locally in a way. That's what I will. But you can, since many of these guys are in quiescent states, people can do kind of bulge luminosity, there's a
Yeah.
possibility, and
Yeah, yeah.
are there any correlation? Then of course you have corresponding correlation about the luminosity, virtual luminosity, black hole mass. This has been tested for some of this just to see whether
For blazars, no. I'm looking for a good student. No, because see, I gave you an example. Now we are getting good quality optical imaging also from a dark energy survey and all, where we can resolve this, we can do this calculate modeling to get this.
We have done something similar. We have done something similar. So but there will be lots of scattered problems and all that, but it's we can be pushed to the higher masses.
Yeah, so I have a question regarding your measurement of Compton dominance. Now, you basically measure based on just the peak luminosity. Now, you must be seeing in your all the 1077 sources that the spectrum broadening, both in the low energy and the high energy harm, will be different. So, would you try doing the same plot by measuring the area under the curve of the high energy and the low energy spectrum, and then take the ratio? Instead of the peak luminosity, measure the area under the curve of each of these high energy and low energy, and then define the Compton dominance by area rather than the peak luminosity. Would then the curve be different?
Curve.
Would then the correlation be different?
I have not tried that, one thing. See, the point is, the problem here is that whatever you are doing, the calculation, the area under the curve, it is more sensitive to the availability of data.
But you are sitting anyways.
One second. Very quickly, I will show you one photo where I will show you the example of this. This one. Like you see the right side plot. Okay. We are like I did not tell you about it. This kind of SEDs were fitted with the polynomial. In this kind of SED, we cannot apply polynomial fitting because we don't have data points in the falling part. How will you fit the polynomial? There is no data to fit. Okay. Then we apply the physical model, synchrotron SSC model. Okay. But here, as you can see, there is no data point here. So then calculation of the area under the curve, etc., extremely like uncertainty will be very, very large in that case. But it can be tried. The next question,
So, first of all, nice talk. Now, again, about Compton dominance. So, you took the ratio of these two peaks, right? So, one is the synchrotron, other is the assumed to be the inverse Compton. Okay. Now, and you have probably assumed that this synchrotron emission is coming from the jet itself.
Yeah. Pure jet only.
So now the question is then, how do you infer anything about the disk limits? If that is the case, if that is the premise. Okay. My point is different, that part of this synchrotron emission, this spectra, will also be contaminated, not only from jet, will also be contaminated from the disk itself. Okay. But that is a different matter. That is my conjecture. But what I'm trying to ask is that when you take these two ratios of the jet itself, how does it, intelligently talk about the...
because these two processes, they are connected with the accretion disk.
No, that's fine. We know everything is connected, but how it is connected, we don't know, right?
Via this external component process. That's what
that's all. It's all about the jet, right?
So yeah. But what are this inverse Compton? We need seed photons, and these seed photons are provided by the disk.
So that is the synchrotron you are providing, right?
No, for synchrotron, I'm talking about the inverse Compton. The higher high energy.
It comes from the photons of the disk. So that's why radiatively efficient disks are FSRQs.
Yes, that's all. That's the idea.
Yeah,
we can talk. We can question. Sure.
My question is also related. So the first peak is coming from the jet directly. The second peak, according to you, or what is assumed, is inverse Compton of this photons.
No. Yeah, inverse Compton of this photon by the jet electron.
Yes, of course.
So it is again from the jet only.
So rather than finding the ratio and comparing with the disk luminosity, why not just compare the luminosity of the second peak with the disk luminosity?
You can do that, but you are totally in the model dependent regime. Whatever result I am showing is totally observations. What you are telling that if you know the inverse Compton peak luminosity, and then knowing that it is this seed photons are provided by the accretion disk, right? Then you are telling that if you know the peak luminosity corresponding, you can derive the luminosity of the surrounding photon field. That can give us idea about the disk luminosity. We can get an idea of disk luminosity. That is fine. But you know that in this case, like when we calculate external competence, so there are several components. Here the BLR photons also contribute, torus photons also contribute, disk photons also contribute into that. And then may not be up to gamma ray band, but somewhere between X-ray up to hard X-ray, we have synchrotron self-compton also. So you see, there are so many mechanisms in between. So it's not a 100% pure accretion disk photon. We cannot get it direct.
Okay, next question.
Yeah, so regarding that synchrotron and synchrotron self-compton, this formalism is partly true. If your electron distribution is basically for synchrotron and self-compton are same, then it's partly true.
Yes.
But otherwise, what will happen? It will have a different electron distribution. Totally different.
Yeah. Then, but
you cannot apply.
Yeah, this is true. I didn't talk much about the variability and all. Okay, but not 100%, but more than 80% of the time we do see correlated variability. Okay, so that gives an idea that usually the dominant blob of plasma from which we are receiving the radiation is the one plasma is dominates. So, and that is the electron population emitting radiation both from radio to gamma. That's the basic one zone emittent. Electron
so in that assumption,
this is fine. If you go from multi-zone and all that, of course, this kind of like component dominance calculation you can do as an activity dependent state. High state what happens, low state what happens. But these are the PhD thesis problems.
Okay, we have time for one more question if there is any hands left. If not, let's thank Vaidehi for the wonderful work and using its COVID times very usefully. The next speaker, ARIES sir, and you have 15 minutes talk. I'll give you a warning at 10 minutes. Finish at 12.
You have mic? No? No, I'll give you one. Sorry, yeah, same, yeah. Hello. Hello. Okay. So, do I get a point?
Pointer is there. By the email.
No, I give you.
Okay, this one pointer and this one. Okay. Good afternoon, everyone. Yeah, so what I'm going to talk about is UV and X-ray variability and interband time delay in a particular separate galaxy marker in 493, and our attempts at modeling this variability and time delay. So this work has been done with Professor Raman Chatterjee and Professor Gulab Dev Angan. Yeah. So I probably don't need to show this slide anymore because this audience doesn't need any more AGN introduction. But I'll briefly mention that there are actively activating supermassive black holes in few galaxies, and as a result, they release enormous amounts of energy. Sometimes there are jets. So what I'll be talking about is mostly non-jetted AGN separate galaxies. So one way that people study the interplay between the corona and the accretion disk in AGNs is by studying AGN light curve, right? So when we look at AGN light curves, what we see, so this is from NGC 5548, a very classic separate one galaxy. You see the light curve almost looks like some random walk like thing. It's a aperiodic stochastic, it shows aperiodic stochastic variability at all observable wavelengths. And when we go to the Fourier space of this light curves, we see that the nature of this noisy light curve is red noise. In white noise, the power is stays constant across all frequencies, right? In red noise, what happens is that the power is higher at lower frequencies. That is a larger time scale, right? And normally shorter wavelengths show faster variability than and higher amplitude than longer wavelengths. So, and what we see is that when we look at light curves at multiple wave bands, we find that they are correlated. So again, this is the NGC 5548 light curves. The top one is X-ray and the bottom one is UV. at least on a longer time scale, you can see that both the light curves look similar, right? And on short time scales, at least, the X-ray light curves are more variable. You can see the shorter time scale fluctuations in the X-ray light curve are definitely much more variable than the UV light curve. And when we do cross correlation analysis, like Shivangi and Professor Rakshit showed, we find that X-rays lead UV. So any fluctuations that appear in the X-ray light curve will show up after some time in the UV light curve, right? So this is normally explained as reprocessing. So what is reprocessing? As Professor Stalin showed this same slide, right? So that there is a hot corona close to the central black hole, and that shines down X-rays, hard X-rays, onto the disk, and that causes thermal fluctuations in the disk, and we see those fluctuations in the UV and the optical emission, right? But the thing is that when people try to do this kind of reprocessing modeling, they start with some observed X-ray light curve and do this reprocessing on a passive disk. What they find is that the variability they get from reprocessing is not enough to explain the observed optical variability. That means some kind of intrinsic disk variability is required in the disk, right? So here comes Mercurian 493. It's a very unique agent. It is a relatively smaller black hole mass and high accretion rate. So the thing about this is that in 2019, Adigoke et al., what they did was that they studied some XM Newton light curves, and they showed that this sort shows departure from reprocessing scenario. In reprocessing, X-ray leads UV, right? In this case, what we find is that UV leads X-rays. X-ray lags UV by about 7 kiloseconds, right? And what I've done is that I've plotted the UV and X-ray light curves. They've normalized them and plotted them on the same plot to show the difference in variability. You can clearly see that the X-ray is much more variable, right? It's almost 7 times variable. So two natural questions come up. What causes the X-ray lag of UV? And the other one is that, can this disk variability, 3% disk variability, drive a 20% variability in the corona? So the conclusions they drew was that the Dobbin process must be inverse Compton of scattering of UV disk photons to X-rays. That's why there is the time lag between UV and X-ray, right? And can the 3% variability drive a 21% variability? Probably not. There must be some significant variability intrinsic to the corona itself in the inverse Comptonization process. And all the conclusions they drew were based on general formularist calculations that people have derived in many papers. So what we did that we simulated this system to simulate UV and X-ray light curve and try to see what we find. We find what they found, or do we find any departure? So we start with a simple accretion disk, right? And then there is the hot corona at some height hx above the central black hole, and emission from different annuli on the accretion disk travel to the corona with different light travel times, right? And what we do to simulate this red noise variability in the disk light curve is we use the propagating accretion fluctuation model, right? So this is the standard disk temperature profile that we use. So the propagating accretion fluctuations model is a very elegant model. It was proposed by Lubarki in 1997, and a numerical prescription was given by Adigal and Utley in 2006. So what they say is that at any point on the accretion disk, at any point in space and time, so the local accretion rate can be thought of as an average accretion rate m dot naught plus a very small time varying component. And this time varying component, they say, is that it is related to the local viscous frequency, that is the accretion frequency, right? And what happens is that this m dot r at any radius, it propagates inwards with the local drift velocity, and then modulates the inner accretion rate thing. So at any point on the accretion disk, the accretion rate is actually an iteratively modulated thing. So, and the viscous frequency decreases as you move forward, move away from the central black hole. It is so the fluctuations are faster closer to the black hole, right? And this results in the 1 over f is shape, that is the red noise variability. So So the distance from the corona to any point on the accretion disk is, we take it to be standard Rx, that is R squared, where R is the radius, and plus the root over of R squared plus Hx squared, right? And the total time delay must be the light travel time, Rx over C, plus some quantization delay in the corona. And the main thing to note is that the farther you are from the black hole, the flux entering the corona will be reduced by this factor, 1 over 2 pi Rx, right? So only the corona will intercept photons mainly from the innermost region of the accretion disk. So when we plot the disk emission profile and we apply this 1 over 2 pi Rx squared thing, so we see that the same disk profile appears very steep to the corona, right? And so what we did is that in a steady state disk, we introduced some thermal fluctuation, Gaussian thermal fluctuations in the disk once close to the black hole. So see, the blue is UV. This is the one that we introduced, and in the X-ray, that is it gets amplified. But when we introduce it away from the black hole, at the corona, it gets smoothed out. So variations produced farther away get smoothed out. Variations produced closer to the black hole in the disk, they get amplified. So then actually we simulated these light curves, and you can see that they look very similar to the observed light curves. Again, these are normalized light curves. This is for corona height of 10 Rg. And we find that for approximately 3% UV variability, we are able to get almost 18% variability in the X-rays, right? So we are getting pretty close to the observed value. And the lag structure is also similar. We found that X-ray lags UV by around 4 kiloseconds. And most of the lag, this I should mention that Adegoke et al. They concluded that the time lag is mostly due to the light travel time from the disk to the corona. But we find that the most of the time delay is actually due to the propagating accretion fluctuations in the accretion disk, plus some quantization time, and the least amount is contributed by the light travel time. Okay, so this is the main result, I would say. So what we did is that we varied the corona height, and we defined some parameter, A bar, the amplification parameter, which essentially is the ratio of the X-ray variability divided by the UV variability. So how much is the amplification happening from UV to X-ray? And we find that as we increase the corona height, it sort of decreases exponentially. So remember, these are stochastic processes. So I had to simulate at every corona height for 10, 20 times to get this curve, right? Okay. Yeah. And so we took the minimum possible corona height just above the event horizon, around 3 Rg, and we see that at least for Evanke 493, we can get almost 19% variability just from this geometric and probabilistic fluctuation argument. And so the inverse confidence process in the accretion in the corona probably contributes very little actually to the observed X-ray variability. Okay, so our conclusions: we created an accretion disk corona model of a safer galaxy. We applied it to Markarian 493, and then we found that amplification of UV to X-ray is mostly due to the geometry and propagating accretion fluctuations. Height of the corona must be small if we are to get a high UV to X-ray variability amplification, and the variability intrinsic to the corona is small, but we cannot strongly say that. Of course, it doesn't exist, right? It must be non-zero. And most of the time delay again is contributed mostly by the propagating accretion fluctuations. Yeah. So a few acknowledgements are in due. Of course, first I would like to thank the organizers for organizing this great conference and giving me an opportunity to speak. I would like to thank ISRO for support under the AstroSat Archival Data Utilization Program. And of course, thanks to Dr. Adegoke for graciously providing the Markarian 493 light curves. Thank you.
Thank you, Auditi, for this nice talk. Questions? Moronita first.
Great talk, Ajit. I have just two questions. One is, even for looking at the lag spectrum, because the fluctuation propagation model that you
Yeah.
conclude have very strict predictions about how the lag
Right.
spectrum would look like, which is very different from the geometric delay kind of scenario.
Right. So I have not looked at that right now. So basically, I'm trying to introduce. I'm also currently actually working on another reprocessing model. The idea would be do this disk to corona photon going, and then it's coming back as a reprocessing. So a complete model. That's what I'm doing. So once I'm done that, I'll have to look at these things, right? Yeah. So
one more question. Okay. Sorry, I just wanted to understand how are you doing the transfer from the UV to the X-ray? Are you constructing any transfer function or is just
no. I'm just so essentially what I'm doing is that I'm calculating all the time for every hour. There is a fixed time delay to the corona, right? So I calculate an array of that, and at the corona I gather all the fluxes from all the hours present at any time. They may have originated at different times in the disk, but at given time t, let me show something. I actually have a backup slide. So yeah, so basically there is, you can see it's some sort of like a retarded time like thing, t minus tau r, where tau r is the time delay.
And the disk geometry is also going in.
Yeah.
Okay.
Sure.
You consider any geometry for the corona? Is it
No.
point?
Yes, that's the thing. So people who start with reprocessing, that is, they have a light curve, X-ray light curve, they do reprocessing in the disk. What they have shown, Professor Chris Dunn essentially, their group has shown that even if the corona is somewhat extended but compact, we can approximate it as a point light source. So that's why I did this. I am currently looking at some other geometries like a truncated accretion disk with a hot inner flow spherical corona, essentially that kind of stuff. There we have to calculate the exact solid angle that.
Yeah. So my questions to first question was regarding the solid angle of the incoming photon. But even more, important question is how do you estimate your quantum time scale?
Right. I have another better slide. Yeah. So the thing is that it's a very simplistic calculation. Professor Rau's paper has this thing. So essentially, you calculate a mean-free path of the photon in the corona, and then divided it by c, you get a single scattering time taken for single scattering step, right?
Then you have to give the size of the corona, right?
Right. That I have kept. That is I did not mention here. That I have kept at some 5 RT, very small, compact like structure. That will actually affect the time delay.
Yeah,
that is important, right? It is of course important, but the main goal was to show that the time delay is actually due to propagating accretion fluctuations, not due to light travel time. So that was the main thing. And I should mention, let me just explain this while it's up. So essentially, it will take some, let's say, n scattering steps for the total quantization time delay, right? So if you have average seed photon energy is E0 and average X-ray photon energy is En, you will need some and it gets amplified by a factor A in each scattering step. So after A to the power n thing, it will get amplified, right? And the amplification factor is essentially with the scattering with the Klein-Dischner correction.
So then you give the temperature of corona also.
Right. That has been taken for this one standard temperature 100 kV and 0.5 optical.
Okay, we can discuss further. Any quick questions before we go to the next speaker? If not, let's thank Abhijit once again for his nice talk. So the next talk is by Habib.
Oh, okay. Yeah.
So this is again a 15-minute talk. I'll give you a warning at 10 minutes.
I am audible.
This.
No, that is the one.
Yeah, this one. It's fine. Yes, sure.
Hi everyone. So first of all, thanks to the organizers for giving me an opportunity to speak here. So today I will be talking about the multi-wavelength study of one of the extreme HBLs. One is 2344 plus 514. So I work with Professor Pratik Majumdar, and this talk will be on behalf of the MAGIC collaboration and our multi-wavelength partners. Okay. So first, a brief introduction about the MAGIC telescope. So it is a stereoscopic imaging atmospheric Cherenkov telescope system consisting of two 70-meter diameter mirrors, which is located at the Roque de los Muchachos Observatory in the Canary Islands of La Palma in Spain. So for low zenith angle observations, the telescope system has a standard trigger threshold of around 50 GeV. And the integral sensitivity for point light sources, which has a crab nebula-like spectrum above 200 GeV, is around 0.7% of the crab nebula flux in 50 hours of observations. Regarding the angular resolution, it is defined as the sigma of the two-dimensional Gaussian distribution, and at these energies, that means above 220 GeV, this angular resolution is around 0.07 degrees, while the energy resolution is around 16%. So as Professor Chatterjee and Professor Palia has already introduced blazars, I just want to add only one comment, is that they are variable at all wavelengths and all time scales, and we are really interested into that. Also, the classification of the blazars between the FSRQs and BLRs, that has already been introduced, so I will not go through it, but I will go through the further subclassification of BLRs, which is there are three subclasses, namely the low frequency peak BLR objects, the intermediate frequency peak BLR object, and the high frequency peak BLR objects. So the high frequency peak BLR objects are those objects where the synchrotron peak frequency lies above 10 to the power 15 Hz. Okay, now among these high frequency peak BLR objects, there are certain objects which are we call as extreme high frequency peak BLR objects. So the meaning is that they can show the synchrotron peak frequency to be above 10 to the power 17 Hz. And subsequently, the inverse Compton peak, that means the peak of the second hump, they can go deeper into the very high energy gamma ray band. So essentially, our whole spectral energy distribution, they have a shift to the high energy. Now, among these extreme HBLs, there are few candidates who show the extreme behavior in all time scales. So by all time scales, I mean irrespective of their flux state. So they are consistent EHBLs, and there are some candidates who show this extreme behavior only on temporal basis, mainly during flares. So my source is this one is 2344. So it's a nearby HBL at a redshift of 0.04. So it was discovered in the very high energy regime by Whipple in 1995, and the typical the flux of the source during its inactive state is around 5% of the crab nebula unit, and it shows extreme natures during flares, so which means the synchrotron peak is above 1 keV. So there have been a flare from this source in 2016, and subsequently MAGIC has observed this source, and we already had a paper on this flare, but in that paper we lacked in good multi-wavelength coverage, because that was the first time the source was being observed in this with MAGIC. So now we are really interested to do a multi-wavelength coverage of the source, and to get a better understanding of the source of the EHBL nature of the source, and also do the variability and the correlation of the study of the sources in the context of multi-wavelength studies. So for this project, we had data sets from MAGIC. So we had a total of data from 2.5 years of data, and we also had some simultaneous dedicated
X-ray observations along with the magic observations. We also have data with Fermi-Lab, and also we have and we also have some data from UV, optical, and radio as well. So yeah, the paper has already been accepted for publication in Astronomy and Astrophysics. So here I show the multi-wavelength light curve of the source from December 2020, 2018 to January 2022. So here you on the top panel, I show the magic light curve. The magic flux is computed above 300 GeV. So this dotted line, it shows the average flux of the source during its quiescent state, and there are 3 vertical lines which are marked by these 3 colors. So this one, it indicates a flare which happened in 2019, and the other two in this one we had simultaneous observations in X-ray from X-ray Newton and New Star, and in this one we had simultaneous observations from X-ray Newton and Astrosat. So the magic light curve, they are pinned daily, and these 2 pink markers, the 3 pink markers, they are the yearly pinning light curves. In the second one, we have the Fermi-Lab light curve, so they are monthly pinned, but around the flare we had a pinning of 2 days. And in the next panels we have the light curves from Swift XRT and the optical and the radio light curves. Okay, so we did the variability analysis of the source. So we computed the fractional variability in all the different wavebands. So the fractional variability curve, it shows a 2-hump structure. So it monotonically increases from radio to optical, and then again it increases from Fermi-Lab to magic. So such a 2-hump structure, 2-peak structure is very typical in HBLs. Now, next we did we wanted to see the correlation between the very high energy gamma rays and the X-rays. So in the left panel, it is the so this is the correlation study between the Swift XRT of 0.3 to 2 keV band, and the right one is the Swift XRT 2 to 10 keV flux, and in the y-axis we have the magic flux. So we see that in the 0.3 to 2 keV band, we do not see a significant correlation, but in the 2 to 10 keV, there is a hint of correlation. So these are the values of the Pearson correlations and the correlation obtained from the discrete correlation function method. Okay. We also did to find out the correlation between the radio and the high energy band. So as the earlier literature, several studies have showed that there is a correlation among the radio and the high energy band, but the radio band generally lags behind the high energy band. So we use this discrete correlation function between these 2 bands, and we see that for a time lag of 90 days, we see a positive correlation between the 2 bands, which indicates that the radio band is lagging behind the high energy band. Now we did also study the spectral evolution, and also to study the intermittent extreme HBL nature of the source. So harder and brighter, it is a typical behavior of HBLs. So for 0.2 to 3 keV band, there is no hint of correlation with the flux. So sorry. So in this plot, the y-axis is the gamma index, and in the x-axis we have the flux of the Swift in the 2 wave bands. So for 0.3 to 2, we do not see a harder and brighter trend, but for the high energy band, we see a hint of this harder and brighter trend. So this may be because the 2 to 10 keV band, there is larger variability in the source. Also, it is important to note that a significant fraction of the measurements show a gamma factor which is less than 2. So we suggest that we have the synchrotron peak frequency above 1 keV. So the source indeed shows the EHBL nature. There are two interesting points in these plots. So one is this, this one. So this is a soft X-ray flare. So it is among the highest X-ray fluxes measured for this source in this campaign. But though it has it had a very soft spectrum. And another most interesting thing is this green marker. So where we had a hard low state. So this point, it is among the it had among the lowest fluxes of this campaign, but it had a very hard spectrum around 0.7. So this thing that we do not see a correlation in the 0.2 to 3 keV band, but we see a correlation between 2 to 3 keV band. So this can be explained by assuming by two means. So one explanation can be that we assume that there is the acceleration acceleration efficiency is increased while the electroluminosity is not changed. But and the alternate solution is that there is a variation of the magnetic field itself, and we see the acceleration efficiency constant. Now we also so for these hard low state that was pointed by a green marker, we see we see some UV excess from the source. So these green points, they are from the hard low state, and so if we extrapolate it from the X-ray to the UV. So you see that the UV there is an excess in the UV. So this could not be explained with the host galaxy contribution. So this indicated that indeed there are two emission regions in the source. Okay, next we did a multi-wavelength broadband modeling of the source. So we take the spectra. The magic spectra are already corrected for the EVL absorption, and here we consider a leptonic synchrotron self-Compton model, and with a two component. So there are two spherical regions which are homogeneously filled with electrons, and they are spatially separated and non-interacting, and they are embedded in a homogeneous magnetic field. So we talk them to be as the variable region. One is the variable region, and that is the core region. So this core region, it dominates emission in the radio, but it has subsequent contribution to infrared and also in UV. And the variable region, it dominates emission from the optical to the very high energy gamma rays. So these are the broadband ACDs. So the left one is from the July 23 to 2022, when we had simultaneous observations with new star and XMM Newton, and the right one is from August 6, 2021, when we had simultaneous observations with XMM Newton and AstroSat. So this two-component model, it can well describe our data. The excess in the UV is also solved. So here I must share that these dark blue line, it is the emission from the core region, and this violet one, this is from the variable region, and the solid blue line, it is the sum of the two components. Okay, so to summarize, here we present the longest and the most extensive simultaneous multi-wavelength campaign for this source. So we had dedicated X-ray observations from SWIT, XMM Newton, New Star, and also our own satellite AstroSat. Our results, they confirm the usual harder when brighter trend, but interestingly, the source also behaved hard even during one of its low states. We also had a hint of an UV excess, and these two things they forced us to do a multi-zone modeling. That's all. Yeah, it has also already been published, and I'm thankful to our multi-wavelength partners and our collaborators. Thank you, Habib, for the nice talk. Questions? Stalin?
Just for curiosity, so you have
UV80 observations also for the same source. Is there any specific reason for not including that in this work? Because you are included only accelerometer, optical monitor, and shift UV only, right? Astrocyte UV is used or not?
So can I answer that?
Is used.
Okay, do you want to answer this question? By the way? Can you please repeat?
So UV data you did not use for the SED. UV.
UVIT. UVIT. No.
He is asking why it was not.
I don't think we had UV. We had no, he's asking why you did not use the UVIT data.
He doesn't know whether
Why did you use that data?
Okay.
Just for curiosity, I just want to know.
I think then Professor Chatterjee will be better. Okay, then Aritaban.
So for this source, when we did, it was soon after observation. So the UV data were not available at the time. And since there were many other data and optical to X-ray coverage was good, so we did not, put too much effort into it. But we can go back and look into it. So we should go back and check if the UV data is.
Data is available.
No, for this particular.
Okay, now we can have the discussion later. Any other question, Amit? Just 1 second.
Thank you.
Definition of EHPLs are like if the synchrotron peak is above 1 kV, is that correct? Yes. But that is very conservative. Generally, we believed earlier it was above 10 kV. Then we have called them, probably it might have evolved. The other thing is, I don't see the magic points going up. So basically, they're going down, right? Even after the EBL corrections. So, do you know which kind of EBL models were used to correct them? Because generally, EHPLs show harder X-ray spectrum as well as hard EBL corrected TV spectrum. But that I don't see in your SEB. So,
We considered the model from government.
What exactly it is a high UV, if you know any background of that EBL. There are several EBL models, more than 20-30 models.
Maybe we can have this discussion later.
Sure.
Engineer, okay, Pratik wants to respond to that.
I don't remember exactly the coming age model, but the fact that you say that the spectrum is going down, what we would see is that the spectrum cannot be harder than 1.5. Because if that happens, that means it's not the shock acceleration mechanism anymore, or some kind of different shock acceleration mechanism is splitting. The fact that you see it's kind of not harder than 1.5 is it says that the standard shock acceleration mechanisms are at work. So that's
Yes. So I have a clarification for this plot, two plots. On the left-hand side, that is July 23rd, 2020. So I see that the formula is formula is this one, right? Yeah, that one, not this one. That one, right?
No, the formula is pink, magenta.
So that's new star. What was that? That plot just above the magic, just above the magic.
This one?
Yes.
This is upper limit, but that's an upper limit.
Oh, okay. So what I'm trying to say is that the formula has a upward trend, okay, and magic has a downward trend in the 2020 observation, but then in the 2021 observation, the formula is going down, right? And it is off than the estimate you have, the model fitting you have. So any idea what is going on there? So what I mean to say is, if that bump is a little lower, I think it would have been a better peak.
Yeah,
but that's an upper limit.
That is way up. I'm not talking about that.
It can go down as well. So did you understand the question, Habib?
Yeah.
Just about it is about 24 Earth. So you see that you have 2 points, right?
You are asking about these two.
Yes.
This is going down, and here that is going up.
There actually consistent with the errors. Yeah, absolutely. You do not want, you do not expect to have data points on a very difficult to.
No, but I regarding these points, I think
Habib, let me let Habib respond.
so for these point in Fermi, the exposure is pretty less, and also for magic, we did not have significant signal from the source because the activity of the source was pretty low. It was even below the quiescent state of the source. It was around 2% of gradient. So I do not think it will be fair to compare these two nights.
Okay, thank you. Any other quick questions before we break? If not, let's thank Habib once again and all the speakers for sticking to the time. Organizers, any announcements?
Oh, yeah. It's lunchtime, fine, but the point is that the 2 buses have been arranged for the dinner. Okay, so it will leave around 5:30 from the guest room.
Oh, sure.
Exactly. I want to play that because maybe some yeah, can you? I need to check that. It's down the line. It's I don't want to play it loud. That's what I'm saying.
Maybe the sound.
Okay, so when I come back, we can just try. Okay, go down. Go down. Yeah, that's a movie. Yes. Here. Can you play that? No, just play. Whether I can get a voice. Yeah.
6 থেকে 7 ঘন্টা লাগে ঠিক আছে 7 ঘন্টা লাগবে কিন্তু একই জায়গায় দুবার বদলি পাস খাওয়া হয়েছে নো
Okay, very good. Thank you. That's the reason I want to play it. Thank you.
না ঠিক আছে দেখছি দাঁড়ান এখানে ছিল একটা প্রোগ্রাম প্রিন্ট আউট
अच्छा आपसे 11টা ये सुविधा सिस्टम सुविधा नहीं इस पे हाँ आप ये क्वेरी नहीं है
আমারটা হচ্ছে 3 পে 1 পে এখান থেকে তোমাকে একটু
খানা খাকে আ যাও
I'm giving a talk.
Hi, Dipankar.
Hi, Balchan.
Yeah, you can hear us loud and clear?
I can hear you. I can't see you, but I can hear you.
Okay, no, that's fine. Okay, so people are, we went for lunch a little late. So
Okay.
we'll start 5 to 10 minutes later.
Okay.
But your presentation and everything is checked, right?
Nothing has been checked. Shall I
So
share?
Yeah, can you just share?
Do you see my presentation?
Yes, we can see it.
Okay, let me see if slide change works. It works?
Yes, it works. It works. So it's all okay. Yeah.
Okay,
so we are all
thanks.
set up.
And you can hear me as well properly?
Yes, very
Okay.
loud and clear.
Okay, good.
So let's just wait for people to arrive. In the meantime, next session, my talk is first. So how do I give it? Can I directly connect to it or laptop? HDMI? No, so I have to do through Zoom. Yes. There's no HDMI.
HDMI there, but US play out how the participation that.
तो दूसरा क्या कर सकते हैं?
अच्छा आपका टॉप के लिए
I'm just waiting for people to arrive. So
That's right.
I just told him 5 minutes because we went a little late. So let's see if we can start with you people. Okay. We went 10 minutes late. So Raj, we are ending our video. थोड़ा इधर उधर हो चलता है. चलता है ना?
हाँ चलता है.
All ideas चलता है.
Now, so this is your idea. This is
Right, okay, the next section. After each, बाकी आ गए ना दोनों पास विश्वास नहीं है I'm good.
Oh, yes, please, taking this asking me, right?
Is Ankur Krishna?
Just one second.
Did you load your?
Yeah, I got it.
Okay, you have loaded the.
Yeah, yes, master. And Ankur has it loaded?
Yeah.
Just ready to
Enough stress if you do
Just see if there are any.
लोगों को मटन खिला के गलत कर दिया.
I was telling Pratik that.
But I am here.
Not everyone is as strong as you.
Exactly.
শিল্পা আমি কি ওই ছবিগুলো ট্রান্সফার করে নিয়েছি তোমার এখনো আছে তোমার একটা
Okay, good afternoon, everyone. We start with the next session in the afternoon, which is about X-ray polarimetry. And the first, so we start the next session, which is mostly on X-ray polarimetry. We have 3 talks in this session, and we begin with a review from Deepankar, and again, like in the morning session, as Deepanjan was saying, unless you have a very urgent question, please save your question till the end of the talk. If you have a very urgent question, yes, please go ahead. Okay, so we start with this. So Deepankar, it's all yours. I don't know how I will tell you 5 minutes before, but I'll try
you have to speak into the mic. Yeah.
So I'll probably 5 minutes. Okay, so please take it away. Okay.
So thank you very much. And, I envy all you guys who are sitting there in Nainital and enjoying this meeting. I'm very much surrounded by extremely high pollution, air pollution. But unfortunately, I can't get away because of teaching. This talk is actually sandwiched between 2 sets of classes. So apologies for not being there, and wish you all a very wonderful meeting. So I thought, as Indranil asked me, to give a
very quick starter, I think, to this session, describing why we are talking about X-ray polarimetry suddenly, which we haven't done for decades before. Because as you will see, we're at the cusp of entering a new era where X-ray polarimetry and gamma ray polarimetry are going to become more common and hopefully almost as ubiquitous as other X-ray and gamma ray observations. So let's begin. So why do X-ray or gamma ray polarimetry at all? What causes polarization to be generated at these high energies? Now, the source of polarization is nothing magical. I mean, it's the same kind of processes that you would have encountered at other wavelengths too. One of the most ubiquitous is scattering. Sunlight from the limb of the sun is polarized because it undergoes Thomson scattering. And this is the same process which can give rise to X-ray and gamma ray polarization as well, and can contribute to very high polarization depending on geometry. For example, on the left side here, the figure shows that if you have an incident radiation on an electron, and let's say the incident electric field is as shown by this red arrow, then the electron is set in motion by that electric field, and then electron will radiate. And depending on where you're viewing the electron from, you're going to see the different amounts of electric field, the radiation electric field, and the corresponding polarization. So if you see from this direction, along this blue line, then you don't see the electron moving at all, so you'll get no radiation. On the other hand, if you see at an angle which is perpendicular to the plane of the picture, then you will see the full motion of the electron and you will get the maximum radiation. Now, consider the incident radiation being composed of this polarization and a polarization which is perpendicular to it, which means it is perpendicular to the plane of the picture. So if I now view this electron perpendicular to the plane of the picture, I see the full emission corresponding to this part of the incoming polarization vector. I see no radiation corresponding to the perpendicular part of the polarization vector. So what I will see is 100% polarized light, although the incident light could have been completely unpolarized. So scattering can be a very important source of generation of polarization. And as you go to higher and higher energies, you go to hotter and hotter media, and you are likely to get more and more of ionized medium, so more free electrons, and hence larger ability to generate polarization by scattering. And if the incident intensity is at a significantly high energy, then you'll not have Thomson scattering, as is shown in this diagram, but you will have Compton scattering, where some of the energy is going to be shared by the electron itself. It is going to move with some kinetic energy. The rest of it will get scattered, but the polarization property remains practically the same. Another well-known situation where polarization can be generated is when you put an electron in a magnetic field. If the electron is relatively non-relativistic, then you are going to get cyclotron resonances. So you have quantized orbits around the magnetic field, and electron can jump between these states, and you will get resonant lines, so which are known as cyclotron lines. So you can get cyclotron emission, cyclotron absorption, as you expect between any two quantum states. But these are also highly sensitive to polarization. The reason for that can be understood by looking at this in the continuum limit. If you have the magnetic field, then electron is in an orbit which is in a plane perpendicular to the magnetic field, for simplicity. So it rotates in a circular orbit over here. If you look at it from the direction of the magnetic field, which is perpendicular to the plane of the orbit, you're going to see the electron moving in a circular fashion, and you're going to get a circularly polarized light. Whereas if you look at it in the plane of the orbit, you will see the electron moving back and forth, and you will get a plane polarized light. And it is not just emission and absorption. There is also scattering, where these resonant states can be involved. So the Compton scattering that we were talking about in the previous slide, in the presence of strong magnetic field, becomes magneto-Compton scattering. And in magneto-Compton scattering, you will have cross sections which have these resonant peaks, which are corresponding to the cyclotron levels. And you can see that this dotted line here is the Thomson scattering level. So at resonant peaks, the scattering probability can rise to much, much higher than the Thomson scattering level, which is in here. You can see it goes all the way up to tens of millions. And away from this, the scattering probability can be considerably lower, even lower than the Thomson scattering. And going from one polarization state to another polarization state have different probabilities. And these different curves here are scattering probabilities between different sets of polarization states. And since they are all different, the scattered light from this electron, which is in a strong magnetic field, is going to be very strongly polarized. If the electron becomes relativistic, then you are, of course, all familiar with synchrotron radiation. And synchrotron radiation from a single electron can be strongly polarized up to 75% or so. And when you have a typical power law energy distribution of relativistic particles with a power law index of -p, then the net polarization generated by these bunch of particles also tends to be polarized. And this degree of polarization in an ordered magnetic field is dependent on the power law index. And here, this curve shows what is the expected degree of polarization as a function of the power law index. Most often, you will find the electron energy distributions in the range of power law index of 1.5 to 2.5, which gives you roughly a median polarization of about 70%. So if you have synchrotron radiation originating in an ordered magnetic field, you can expect polarized radiation up to about 70%. And synchrotron radiation, as you know, can be very broadband, can go from radio waves all the way up to gamma rays. And so therefore, in X-rays and gamma rays, many places you do see strong synchrotron radiation, and it tends to be polarized. The compact stars are some of the brightest sources of X-ray and gamma ray emission. And the high energy emission from compact stars can originate in broadly two different classes of emission mechanisms. One is magnetospheric emission, like in the pulsar, you have the magnetic field rotating around the spin axis, and that generates particles in the magnetosphere which radiate in the strong magnetic field, and you get the pulsar emission. Pulsar emission at all wavelengths are strongly polarized, and X-rays and gamma rays are no exception. So depending on where in the magnetosphere the X-ray or gamma ray emission is coming from, you will see a corresponding pattern in the pulse profile as seen in polarized emission. Now, accretion powered emission is the other common way of generating X-rays and high energy emission from compact objects, where you have a donor star which supplies material which comes through an accretion disk, then falls into the compact object. And this material gets very hot because of strong or rather deep gravitational potential of the compact object. And this hot material radiates. So this is largely thermal radiation. And thermal radiation by itself tends to be not strongly polarized because you are talking about particles moving in all directions in a near isotropic fashion. And that averages out the instantaneous polarization generated by radiation mechanism of any particle. But emission from such systems can also contain significant degree of polarization because of the scattering, because it's although the source of the radiation is thermal, the thermal radiation before it reaches us comes through a sort of layer, optically thin layer, which scatters this radiation, and that impinges on the radiation a polarization signature. So we'll come to that in a moment. The magnetospheric emission, as I said, is generated by, let's say, in pulsars, pairs being created in the magnetosphere. What we understand today is general relativity has a major role to play in making possible the sustenance of electron-positron pairs in the magnetosphere. And these electron-positron pairs then move along the magnetic field and radiate in the magnetic field. They go even beyond the light cylinder and then create a region around the light cylinder, which is called the wind zone, and the radiation continues to happen over that region. In high energies, like X-rays and gamma rays, the radiation that we receive is typically incoherent synchrotron emission, whereas in radio, you are more likely to see a coherent curvature radiation. But we're talking about high energies now, and the primary mechanism of emission there is incoherent synchrotron emission by electron-positron pairs. But they are in strongly ordered magnetic fields, and hence you do get high polarization degree in the radiation that we see. And in accreting systems, as I said, the source of radiation could be thermal radiation from the inner part of the accretion disk, which is hot, but then the radiation scatters in the outer skin of the disk, and this would be Thomson scattering or even Compton scattering, depending on the wavelength we are looking at, and that will have some polarization depending on the view geometry. Some of the radiation can also scatter from a hot corona, which can exist around the compact object in addition to the accretion disk. And Compton scattering in the corona will also have its own polarization character imprinted on the radiation that we see. Many of these sources also have jets. In the jet, relatively far away from the compact object, you can get synchrotron emission, and you can get strong polarization via synchrotron emission or even Compton drag, which is Compton scattering from fast moving particles. The base of the jet can produce emission, and this emission can scatter off the disk and come to us. So this is called the lighthouse model, which has become quite popular in characterizing the radiation from some of these systems. So this radiation, because of the scattering, will also have polarization. So depending on which component is radiating, you would expect different types of polarization, different degrees of polarization, and by observing polarization from such objects, one can characterize many of these things. accretion onto strongly magnetized neutron stars tends to interrupt the accretion disk pretty far away from the star. And then the material moves along the magnetic field and you get what is called polar cap accretion. And this is true in accreting X-ray pulsars, most of which are high mass X-ray binaries. Magnetic field is strong, of the order of teragauss. And as the material falls, it then accumulates at the polar cap. So creates a mound, and this mound produces continuum, and this continuum then goes through this outer skin of the mound, which is optically thin, but in the presence of extremely strong ordered magnetic field, and you get cyclotron scattering. And as I have mentioned before, cyclotron scattering can produce very strong polarization. So you expect strongly polarized emission of the X-rays that you will receive from this region. So it's not just the skin of this, but also the column above it can cause scattering and produce polarized emission. So studying polarized emission from such objects can tell us several things about the compact object and the accretion process. For example, if you look at the expected spectrum of emission from an accretion powered pulsar, you will see resonant lines which correspond to the cyclotron energies. And what is shown here are the ordinary and extraordinary components of the radiation, the spectra of those. So ordinary being radiation propagating across the magnetic field with polarization across the magnetic field, and extraordinary radiation propagating across the magnetic field with polarization along the magnetic field. So as you can see, these two have rather different spectra. So therefore, when you see the total emission, adding up these two, you will have a fairly strong polarization. It's almost a factor of 10 difference in the two components of the emission. So therefore, the polarization is almost going to be 90% when you look at energies which are at the resonant lines. So all this has been predicted before, and of course, in reality, the neutron star is going to emit not just from one spot, but over a distributed area, and radiation from all these different directions will be subjected to gravitational bending of light because of the gravity of this, and then they will come to us. So you have to integrate over the desired emission region, and when you integrate, you will expect emission profile, which is sort of average over magnetic fields at different locations and different orientations of the radiation being emitted from the surface. So the predictions for polarization, we'll have to take all of that into account. There are some things which also depend on the characteristic of the neutron star itself. For example, if you look at the polarized pulse profile that you expect from such an object, the shape of the pulse profile is actually dependent on the compactness of the star because of the amount of light bending. And if one is at some point able to look at the polarized pulse profile with sufficient detail, one should be able to also put constraints on mass radius relations. Another place where we are measuring polarization at fairly commonly is in gamma ray bursts. So you have a gamma ray burst where you have a jetted emission with a large Lorentz factor, and if the magnetic field in this region from where we see synchrotron emission happens to be ordered field, then you would expect a certain degree of polarization. Here it's the expected polarization is plotted with respect to the viewing angle with from the center of the jet. So as you go to higher values here, your viewing angle is more off axis. So you can see that in ordered field, you expect a strong polarization all through, and then outside of the jet it will drop. If it is random field, of course, the polarization will cancel out here. But if you're looking at it from the edge of the cone, then the radiation there is anisotropic, so it doesn't get fully averaged out. So you will get some amount of polarization, and then as you go away from that, it's going to drop. Similar profile can be expected also from Compton drag, where you have a existing bath of photons which are not polarized, but Compton scattering from the fast moving flow then causes the photons to get directed, and those directed photons come to us. And as we said that you can get pretty strong polarization from Compton scattering, you can also get pretty strong polarization in this Compton drag, depending on the direction at which you are looking. So all this has been known and has been predicted for quite a while, but measurements is what have been scanty. The very first X-ray polarimetry mission was launched in 1975. It is NASA's OS-08, which carried a Bragg polarimeter, and it could detect polarization from two sources, Crab Nebula and the black hole X-ray binary Cygnus X1. And it put upper limits on polarization from several other sources. And because it was a Bragg polarimeter, it made the measurement at two specific X-ray energies, 2.6 and 5.32. So this is where the measurement stood since 1975. For no other polarimetry mission actually materialized for nearly 30 years after that. And now there is a revival of this field because of multiple new instruments becoming available. There are some dedicated missions, like the Chinese polar mission, which was dedicated for GRB polarization. It unfortunately survived only for a few months. It was launched in 2016. Then there are balloon flights with this POGO mission. It gets periodically launched. It is launched in 2011, 2013, 2016 at Antarctica, and then makes observations for a few days. And currently, the dedicated X-ray polarimetry mission that is operating is IXP, which was launched in December 2021. It's a mission, it's a NASA mission which operates in the range 2 to 8 kilo electron volts. And there are a couple of other capable missions for polarimetry, but they are not dedicated for polarimetry. They're launched for other reasons, but they also have some polarimetry capability. One is Integral, which is a gamma ray mission, which is launched in 2002, and it is still operating. And India's own Astrosat, which was launched in 2015, and currently still operating. And then there are some planned and proposed missions. The first being X-ray polarization satellite ExpoSat, which is hopefully going to get launched very soon, within a month or two. It's almost ready to be launched. So that's an ISRO mission with a polarization payload called POLIX, it's built by Raman Research Institute, and it also has a spectrometry payload called Expect, which was built at UR Space Center. So this is going to go very soon. Then in the future, there is EXTP. There is also Polar 2, successor of Polar, which is planned, which might go pretty soon as well. And also another Indian mission which is being discussed now, that is Daksha. You'll probably hear about Daksha in other contexts. So coming for, because this is going to be our own mission almost ready to be launched, let me spend a moment as to how this works. It's a Thomson scattering polarimeter. So you have a scatterer at the center surrounded by detectors, and you have incident radiation, and the incident radiation is going to be scattered by the scatterer, and the probability of scattering as a function of azimuthal angle depends on the polarization of the incoming. So the polarization of the scattering is maximum in the plane which contains the electric field of the incoming radiation. So therefore, if you look at the azimuthal distribution of the scattered radiation, you can then reconstruct the both the degree and angle of the incoming polarization. So that's what we have here. You have a scatterer at the center surrounded by proportional counter detectors on all four sides. And this is going to rotate on its axis and then make measurements, long measurements on expected sources of polarization. So let's see what kind of results that are coming up. A very quick example of some interesting results from IXP, which is at 2 to 8 keV. So IXP has been mapping bright supernova remnants, which are strong X-ray emitters. This is one such map of CASE. The underlying continuum map here is from Chandra, and these vectors are the contribution of IXP. So these are these demonstrate the direction of inferred magnetic field in the supernova remnant. And as you can see, it looks like the magnetic field is almost radial. So it's been drawn out by the expanding material, which is propagating from the explosion center out into the shock wave. So the outer shock wave happens to be here.
You can cut 5 minutes.
Okay, thank you. So another interesting result from IXP is for the Blazar Mercurian 501. And this is a measurement of polarization with IXP and optical and radio all put together. And this progression of degree of polarization and the fact that polarization angle is aligned with jet at all bands can be used to infer that what you have is a shock wave. Particles are getting accelerated at the shock wave. Immediately after acceleration, they emit X-rays, and as they lose energy and go further downstream, they emit optical, and even further down in radio. And the magnetic field, which is very ordered at the shock wave, keeps getting gradually disordered as you go away. Astrosat has one instrument called cadmium zinc telluride imager, which uses Compton polarimetry to detect polarization. So if you have one pixel, and let's say radiation strikes this pixel, and the radiation can get Compton scattered and can detected also in other neighboring pixels. This distribution, azimuthal distribution, also depends on the electric field direction of the incoming radiation. So if it is polarized, then you will expect more radiation in the plane in which the initial polarization was there. And that's what we end up detecting in CZTI, and we use that to measure polarizations. You have azimuthal modulation like this, which tells you both the degree and angle of the polarization. One of the sources that we have observed is the crab, and we find that the polarization is practically aligned with the spin axis of the crab, and that tells us something about how where the polarization is originating, and it's most likely just outside the light cylinder, as is also expected from the numerical models of magnetosphere that are now being computed. In the first 5 years, we also had about 20 GRBs for which we could check for polarization, and 5 of them have been detected. Others we put upper limits, and the 5 detections have fairly strong polarization going all the way up to 80% or so. Then recently, we have just announced this result of polarized emission from black hole extrabinary Cygnus X1, where astrosat measurements fall in between IXP measurements and OS08 measurements, which are in sync. So this is low energy measurement. This is at astrosat energies of 100 keV and above, and there are these integral measurements. So you can see a progression of the degree of polarization as you go to higher energies, rather similar to the IXP and optical and radio polarization of the blazar that we saw in the previous picture. So this is also very interesting. It tells us something about the way this polarization is being generated. So to summarize, polarimetry at X-ray gamma ray bands is now seeing a revival with multiple new missions spanning a wide energy range. Simultaneous multiband polarimetry is crucial in deciphering some of the underlying physical processes. And India has a strong presence in this area, with Astrosat contributing several important results, and the XPOSat mission about to be launched, and the Daksha mission is in planning. And there are other multiband X-ray polarimeters which are also being discussed and may follow. Thank you very much.
Thank you, Dipankar. Very thought-provoking and interesting talk. We have time for a few questions.
Dipankar, the Indra here.
Yes, go ahead.
A very naive question. See,
yes, please.
We understand that there will be polarization when photon, a light wave goes and hits a electron.
Yes.
Now, if that electron is thermalized, for example, we have it in corona. So, what should be the degree of polarization which we should be expecting from such a thermalized medium?
Right. So the medium is thermalized, which means each electron is moving in an arbitrary direction, and the velocity distribution is isotropic, right?
Yes, yes.
So that's what you mean by thermalized.
Yes, yes.
The interesting thing is that even if you have a thermalized medium, when you look at the optically thin edge of the medium, you have an asymmetry there. So there is so the medium is not volume filling, right? So there is an edge to the medium.
Yes, yes.
So the averaging will not work completely. So one side you will have more emission, other side you will not, and that will give you a residual polarization. So this is exactly like the limb darkening in the sun. So at the limb of the sun, you get Thomson scattering, and you get polarization. So this is what you would expect from corona as well.
Hello.
Yeah.
I'm Samir here. So
yes.
The Cygnus X1 result and the other result that you have shown, the polarization is strongly energy dependent.
Yes.
So what could be the physical process which is responsible to produce such effects?
Yeah, so this is still debated as to what is the physical process. For example, the IXP result that I showed, they are interpreting it as there being a shock which accelerates particles. Close to the shock, you get X-rays, but the stream which crosses the shock is very ordered. At the point of the shock, it has got the maximum order, and then as it propagates away from the shock, the flow becomes more disordered. So the magnetic field becomes more disordered. So the radiation that comes further downstream from the shock, let's say optical, sees a more disordered magnetic field, so therefore degree of polarization is lower. And as you go to radio, it is even further disordered, so the degree of polarization is even lower. So that's the interpretation of that result. Whereas in the Cygnus X1, we cannot exactly interpret it that way because of other reasons which I don't have time to go into in this talk. But what we think is that the Cygnus X1 emission at higher energies is coming from the base of the jet, whereas what you're seeing at the lower energies is coming from scattering from the accretion disk. So there are two different regions contributing to polarization.
Okay, thank you.
Very nice talk, Dipankar. I'm Arun here.
Hi.
I had a question regarding X-ray pulsars and IXP observations of X-ray pulsars showing very lower degree of polarization as opposed to expected from theoretical models. So what are your thoughts on that? Is it like energy dependence because IXP energy base is 2 to 8 kV, or is it like something is missing in the theoretical models?
Well, it's, I think, a bit of both. The theoretical models but predict that the maximum degree of polarization that you may see is near the cyclotron resonance. IXP does not reach the cyclotron resonance. So we need to have POLIX to actually probe that region. But even at lower energies, simple theoretical models will end up predicting more polarization than IXP is seeing. And the reason we don't see it obviously has to do with the idealizations we make in the model, right? We say that it's a pure dipole magnetic field. There are no other components of the magnetic field. It's all very symmetric, isotropic. Obviously, most of those assumptions are not realized in reality. So once you begin to relax that, you will average things out and you can get things down to the IXP level.
Thank you.
One last question. So, hello, this is Raman.
Hi.
So, like you showed in the IXP observation of the laser, the polarization degrees, compared with the optical and the radio polarization. Is there a similar comparison in the direction of polarization? Or
They're all lined up. So I actually mentioned that in the slide. Maybe I went too quickly. Just a minute. Yeah. So polarization is aligned with the jet at all bands.
So you mean the axis of the jet?
Yes. So the diagram shows something like that. So let's say this is the axis of the jet. Flow is going from left to right. Here is a shock, and X-rays are coming from here, optical from there, and radio from there. And the flow is very ordered here, and then begins to get disordered. And that's what. This is the picture that this paper advances.
Okay. I mean, I'm asking because sometimes it's said that this polarization decreases not just because away from the shock it's getting disordered, but just in radio emission is coming from a larger volume, and in the larger volume the various direction of magnetic fields are getting a little bit averaged out. But in that,
which is also true.
Yeah.
It just depends on which component of the emission you're seeing. But that is also true.
In that case, I'm not sure if the alignment will still remain, but maybe that's okay. That's interesting.
Yeah. So the fact that the alignment remains here in this particular source,
yes,
or in this set of observations, tells you that these particular pieces that are being compared, are probably all coming from the jet.
Right. Thank you.
Okay, so if no further questions, let's thank Dipankar and we can move on to the next one.
Thank you very much.
Thanks, Dipankar.
Bye-bye.
Okay. Next talk is by Ankur.
Talk is 20 minutes. 12 minutes and we will say wrap up in the next 3 to 4 minutes. We will be assigned a question.
So, thank you all the organizers for inviting me. Okay, so let me begin with thanking all the organizers for inviting me to this conference and also organizing this. It's been very useful for me in the last 2-3 days what we had. So my topic is polarized emission from black holes. In last few days of this workshop, we heard a lot of accretion dynamics, disk dynamics, spectral states of black hole, other observations, and so many simulations about black hole. The one last thing which is remaining in this is the polarization from these spectral states and in these sources. So I'll speak about these, and these are the collaborators I've worked with. First one is Anil Tanvi. He's actually my supervisor, and rest of them are my collaborators. And Seshadri is here, and Shantala is also here, Professor Das from IT department. All right, so let me move on. Okay, so already I've been given less time, only 12 minutes for the talk. So
we have 17 minutes. I'll give you a warning after 10 minutes.
Fine, fine.
You have 5 more minutes after.
Fine, so
the full time.
I'll try to go as quick as possible, explaining very important things that we must look at. So here's the outline of the talk. I'll start the topic with some background, and in the last 50 years, how the subject has evolved. And then based on those physics and mathematics that people have worked on, there are various models that predict the polarization in these sources. And then in the recent times when we had IXP operating and polarization measurements have been done and all these results have started to come. So I will also discuss on that. And towards the end, the spectropolarimetry that we have been working on, I'll discuss and close and talk with that. All right, so we have no argument on that we have a disk around the black hole sources. So it all started very back in 1946 when Chandra already assumed a slab-like geometry, and he calculated through the radiative transfer solutions that if you have a disk like or a slab like this, and there's a source embedded inside the disk, and you start radiative transfer solution or the transfer the intensity out of it, you have these numbers coming out. And this, the first row that you see, so this is the table what Chandrasekhar paper had in his paper. So the first column which you see is the angle, which is defined as mu, which is nothing but cos I here. It is also known as cos theta, but we all very familiar with the inclination of the disk, so I have used I here. And the last column, which is so the last column is the degree of polarization. It's in the fraction, and you have to multiply percent if you want to do it in percent. So if you see at the very edge of the disk, which is 0, cos theta, which is if you're looking at the disk, which is edge on, so you have almost 11% polarization right there. And if you're looking at the disk, which is 0, which is about 0.1%, it's very, very less polarized. So starting from this model itself, we can say that a disk should give you a decent amount of polarization, which is 11%, which is considered very high polarization for these sources. But it's all based on the geometry and the location of the observer with respect to the disk and the system. And then Angel in 1969 did a very small simulation. He considered a spheroid with a optical density of 2, optical depth of 2. And in this, he just randomly created photons and associated angles to start with, polarization angle and the electric field angle to start with. And after multiple scattering, the photon comes out because the medium is finite. And once you look at the or the integrate over this volume, you have this polarization with as a function of angle again. And the solid angle is Chandrasekhar solution. And now you can see that it very closely mimics the solution of Chandrasekhar already back in 1969. All right, so this was the time when SCO-X1 was also discovered. And the polarization measurement, the very first balloon experiment which they conducted, Angel and people, the collaboration people. So they had a few observations on SCO-X1, and it was already hinting that the polarization should be there in such sources. All right, then. So once we move on further, Cygnus X1 was discovered in 1971. And by that time, and after a few years, these people, Stark and Cunard, they have started working on very simple relativistic spec into the classical models, which produce a very constant polarization depending on this energy. So if you look at this 1 to 10 kV or 200 kV, it's almost constant if you just consider Newtonian potential. But when you add these GR effects into it, when I said GR effects, is mostly the light bending, and which also rotates the polarization angle associated with any photon. So that gets all mixed up near the black hole. I will elaborate more in the coming slides. So that's what start to cause depolarization, and we see a reduction in the polarization from the classical when we introduce the GR into it. So these were the very beginning papers. These two initial papers were Nature papers, and they were very small one-page papers there, but they have a lot of information in these papers. And then Cunningham started further working on it. In 1980, he added a very important concept into it. It's called the returning radiation, and we'll discuss about that also. So in 1980, he introduced this returning radiation that further changed this profile into something that we today observe. Yeah, one last thing. By this time, already Kerr metric was there. Now disk was already model was out. Relativistic, this anti-Novikon Thorn disk was also there. Also 8, which was observing polarization from solar, has also observed Cygnus X1, and the polarization numbers were out. So it was about 3% what they gave back in those days. So that motivated all these work, and further in the coming, as Deepankar also pointed out, in the few 30 or 20 years, there was a big gap in which not much progress was done. But then a group of people, mostly European, they started working, and before that there was only few papers were there, but a major paper came when Bose in 2008 considered all these parameters. So the main parameters which we look at are the spin, the inclination, and the optical depth in a system. So these are three main parameters which he considered in his work, and he gave out, gave a very precise and accurate model. And then further, Schnittmann and colleague, they started working on different states, and their model is also very precise. These are almost they came at the same time, and they have worked on thermal state, specifically in the coronal emission, as Indonilla was asking about the coronal emission. So if you look at this paper, you'll find out how the corona changes the polarization signatures from a black hole in a hard state. And then, and the last one, just 2020, they introduced optical depth, which is, as Deepankar was talking about, the skin of the disk. You have variable or different kind of optical depth that you can consider to reflect or to scatter off the photon which are generated in the disk. So all these model, they work on very, not very simple, but it's very straightforward, and we obviously know all this physics. So it starts with a source which lies or embedded on a disk, and on top of it, which is shown as blue, is a medium which scatters the just scattering medium, or it can be a corona also, which you can consider with some different temperature. All right, so all these things that we have put in this model, they have optical depth defined for this, and your source can be a black body, which can be a multi-disk temperature, or if you want to do it for what we call thorn disk, you can take their temperature profile and put into this. Once you create these photons, you scatter them in this medium, and radiative transfer equations will come, and all these distributions along these axes and your reference, all these distribution will be there. Once you have the photon distribution, you start picking those photons one by one, and then you just ray trace them, and you calculate geodesic around a curved black hole, or if you want to do it for a stationary black hole, you have to use those metric. And once you do that, all those effects are taken care of. And if you have a detector, you sort of integrate over the disk of all these effects, and the photons which are already in geodesic, they are integrated in a solid angle, and so altogether this gives you a measure of polarization, and also it gives you the spectrum what will come out of from this system. So once we do all that, so before going to giving actual model predictions, I'll just quickly discuss about the inclination effects. So suppose we have two similar black hole systems. They have similar masses. Mass is just a scaling. It doesn't do the scaling in the geometry, but if you have the similar masses and similar spin parameters for these two systems, and if you have an observer looking at two different inclination, so the observer which is at a high inclination angle will see a higher polarization, as Deepankar also pointed out in his talk. So it's all the location of the observer, because the Thomson scattering is the angular dependency is there. So that is the effect of inclination, and then you have more severe effects of in the polarization degree and associated electric field. So here I have shown two black hole systems, one with a higher spin So these two arrows shows the system has a higher spin and this one has a lower spin. And we are observing it at same angle here. So angle is fixed here. And now if we have the spin parameter is higher on this system, the last radius to which the disk can approach to the compact object will be nearer when we compare the system which has a lower spin. So that creates a very interesting effect. What it does is we have photon generated here in this region. They can cross the compact object and they can fall on the other side of the disk. So this side of the disk is called the far side of the disk, and this side of the disk is the near side of the disk. So photon traveling from the far side of the disk, they go to the near side of the disk and they scatter off from there. Okay, so blue are the ones which are bend gravitational lensing. Because of the gravitational lensing, they're bending and they are scattering off from the surface, and the amount of radiation which is scattered off will be higher in this system when it's compared with the one which has a smaller or a lesser spin parameter. The reason being that, I mean, as close as you are, you have more probability of ending, I mean, a photon ending up on the other side. While in this system, a photon can bend, but it will not reach surface, or neither the surface nor the observer. While you can expect these two direct radiation in both the systems. So the effect of all these are mixed up when you integrate or observing a system. And one important thing here is the reflected radiation, which is here, is polarized in perpendicular direction to the which is direct radiation. So the blue one is the plane of the disk, while the red one is in the parallel to the axis of the spin, or if it is aligned with the spin axis. All right, so this is one of the model which is very successful, and here you see the map of all these polarization vectors. The lines are the line. I mean, the orientation gives you the angle with respect to the axis right here, and the length of the line gives you a measure of the degree of the polarization. So the longer the length is, more polarized the light is from there. So if you look at these two regions, left and the right, so observer is, I mean, you are the observer for this disk, and on the left and the right, this returning radiation is very much prominent, and you have this 90-degree rotation in the electric field. So this is a very resolved map. If you observe such a system, all these angles and all these flux will be integrated into one, and all these would reflect into such a profile. So here what you see is this angle is the direct radiation angle, and once you have more radiation coming from closer rings which are in high energy, that gets more scattered off, and hence you have polarization switch. The angle of the electric field is switching towards the high energy. And similarly, the scattered radiation, which is coming from the left and right, which is 100% polarized. Even if the fraction is very small, which crosses this black hole to the other side, but once it scatters off, it's 100% polarized. So that's what affects this profile here. As the energy goes higher, you see more polarization, and these different colors are for different spin parameters. So a very maximally rotating black hole will give you a very high polarization in the higher side of the energy. All right, so all these were models and theory. Now that IXP is observing these sources, we have about 5 or 6 sources so far that IXP has observed from black hole. X-ray binaries. And before going to that, I'll just briefly tell about it, XP also. So it contains 3 optical X-ray optic modules in here, which focus all these X-rays to gas sensitive detectors, which are sensitive to polarization. And these are the parameters of these instrument. And the gas depth is about 10 mm, so it only works till 8 keV. So the result or the output of these event from these observation is the Stokes parameter of the radiation. So we only have 3 Stokes parameter out of 4, I, Q, and U. And V is 0 because all these scattering, Thomson scattering and Compton scattering, they do not produce circularly polarized lights. So V is 0 and we only have linear polarization. And in terms of observables that IXP gives you, the first thing that it gives you normalized Stokes parameter, and you can quickly look at the Stokes diagram, which tells you the angular variation. So once you have these relations, you can derive polarization degree and the angular associated angle or electric field angle with that. So once you do that, you can put into this kind of plot. So on which you can see the axial lines or the radial lines. They are the angle of the electric field, and the concentric rings that you see are the polarization percent. So this 1357 is into the percent. So once you suppose you look at one of these contours, if I'm looking at the red one, it's about roughly 3% polarized at an angle of -45. So IXP generate these kind of polarization plots for you, and along with that, it gives you the spectra in I, Q, and U. All right. So the red one, which is the intensity spectra, and Q and U are the other 2 Stokes parameter spectra that it generates. And then this is the summary of all the X-ray binaries so far observed. So the first 4 are observed in high soft state. The first one is the 4U1630, which went into outburst, and it gave about 8.3%, which is roughly 8%, which is very high polarization when we consider a black hole source. And then there was LMCX1, which did not show any polarization, or it was probably below MDP, which is minimum detectable polarization. So for LMCX1, it was 1.1%. So it was further below maybe 1.1%, which LMCX1 generates or produces. And then LMCX3, which gave about 3% polarization. And then, so LMCX1 is a slow rotating black hole. It's about 0.3 or 0.4 spin parameter. While this source 4U1957 is a highly rotating, maximally rotating black hole, and it gives you a polarization about 2%. So these 2 sources, they're excellent sources to verify your model, and they're kind of consistent with the model predictions, while 1630 does not agree with all the measurements, all the prediction that we had. And towards the end, we have Cygnus X1. It was very much popular and very talked about and discussed in so many, I mean, great details. In the low Hart state, it gives about 4% polarization, which is also higher what we expect. And in soft state, it gives about 2.5%, and the angle remains same. So these angles you can relate once you have a large structure associated with the system, which could be a jet in this case. And once you have this jet on the sky plane, you can relate these 2 angles. So sorry. Yes. So this angle you can relate whether it's aligning with the jet or it is 90 degree with the jet. So that kind of gives you a probe whether this polarized light is from the corona, or it is from the returning radiation. It's close from the disk, or it's outer edge of the disk. So So these angles gives you a measure of, probe into geometry. And I will probably skip all these results. Towards the end, I will, from all these high soft state, measurement of these three sources. So the black one, which you see is LMCX3, and the purple one is 4U1957. So these are, as expected, they are very consistent values, depending on their inclination, spin of the system, and this 4U1630, which is not consistent, it's very highly polarized light as well. The spectrum is highly polarized. And this is energy resolved. So you see an energy dependency also. So it increases with energy in all these cases. That's what models also predict. And in the last one, which is Cygnus X1. So in this paper, what they have given you, what they worked out is different geometry of the system. And from this different geometry, they produce or reproduce the observational results. So the one which matches with the observation result, they consider it as the mostly related to the system, which could not be the case. Various papers after these observation came, and they suggest different ideas into that. Some of them are a bulk motion of a cognizing medium, which can be moving at very relativity speeds. So based on these geometries, you see that all these signatures are unique. So once you have these measurements done, you can break the degeneracy and can talk about whether the corona is wedge-shaped or the slab shape or it is the lamp post and so on.
So Ankur, can you come to your conclusion?
Yeah, I'm done.
Well beyond your time.
Right. Thank you so much.
Since we are running out of time, there is only time for one quick question and one quick answer, if anyone has. If not, let's thank Ankur and move to the next. So the next talk is by Ritika Chatterjee, producing the physics of neutron stars using X-ray polarimetry. Hopefully I read it correctly. Yes,
I think that's the last one in this paper. That's the right answer. Oh my God.
The next one.
But we are probably pressing the wrong button.
No, you're pressing the right
It's okay now.
Correct.
No.
This is. Okay.
Yes.
Okay. Okay. Good afternoon. Am I audible? Not on.
It's on.
Hello?
Good afternoon. I'm Ritika Chatterjee from URSC. First of all, I would like to thank Indranil sir for giving me this opportunity. So I'm going to talk about the extrapolarimetry of neutron stars. So as we all know, the field of X-ray astronomy is very old, many decades old. And up till a few years ago, we have been mainly concerned with spectroscopy, timing, and imaging. In recent years, again, this extrapolarimetry has taken shape, as Deepankar sir also mentioned. So extrapolarimetry adds two more observables to our parameter space, which is the polarization degree and polarization angle. So what advantages do we have if we have polarization information? So as we know, neutron stars have pretty strong magnetic fields, and so when there is emission in magnetic fields, we have polarized emission. And moreover, as the emission propagates through a magnetosphere, the polarization properties may get modified and changed. And also, due to the aspheric nature of matter distribution, for example, the accretion disk, we expect some significant polarization from these sources. So, if we have polarization information, we can have some clues as to what is the accretion geometry in these systems, what is the magnetic field structure, strength, and the QED effects, which were predicted long back. We can finally test them with actual observations. So in this talk, I'm mainly going to focus on the prospects for these neutron stars, these kinds of systems, low mass extrabinaries, which are sort of weakly magnetized, creating pulsars and magnetars. Okay, so first coming to neutron star low mass extrabinary systems, they have magnetic fields of the order of 10⁸ to 10 Gauss. And usually they're classified into these two kinds of sources, the Z and atoll sources, based on their property, the shape that they trace in the color diagrams. Then further, these sources can also be divided into the, depending on the accretion rate, they can be in high soft state or low hard state. So the spectrum from these kind of systems usually consists of two components, a thermal component and a non-thermal component. The thermal component is thought to be originated from either the surface of the neutron star or the boundary layer here, or from the multicolored blackbody emission from the disk. And on the other hand, it is expected that there is a corona which counterizes this emission. And so there are two popular models for describing the spectrum. One is the Eastern model, where we observe the thermal emission from the disk directly, and the corona is sort of around the neutron star, and then that gives rise to the counterized component. And in the Western model, we observe the central object directly, and the corona is in the form of a slab or sandwich. So there are many such sources where the spectroscopy is actually degenerate. So both these kind of spectral models fit equally well, and you can always get the physical parameters of the corona, such as its temperature and optical depth, but you do not actually know what are the what is the origin of the corona, where is it located, and what is the geometry. So these are some schematic representations of possible types of corona geometries. So recently, Narini et al. In 2022, they used the Monk codes, which are very well known in the community, which is Monte Carlo ray tracing codes, and they adapted it for neutron star low mass extrabinary systems, and then they actually calculated what are the expected polarization properties, which is the polarization. So polarization angle and polarization degree. Yeah. So for different kinds of geometries, such as the for a slab kind of corona in the high soft state as well as low hard state, what are the polarization degrees and angles which can be expected for different viewing geometries, and similarly for the shell kind of geometry. So given we have sensitive enough measurements of polarization, the different models can be distinguished based on these models. So coming to accretion powered pulsars, we know that because of the strong magnetic field, the accreted material actually forms a kind of accretion column and that flows along the magnetic field lines. And depending on whether the accretion is subcritical or supercritical, the emission coming from the accretion column can either have fan or pencil beam kind of pattern. So their properties, their polarization properties are kind of different. And here, as you can see, so this is a relation of the optical depth of the ordinary and extraordinary mode of emission. So EC is the cyclotron energy. So if we observe emission at energies below the cyclotron energy, we'll see that the opacities of these two modes are very different. So that's why we can expect a significant amount of polarization from these modes. So what else? For example, geometrical parameters of the system, the inclination, the magnetic obliquity, which is the angle between the spin axis and the magnetic field, using extrapolarimetry. So yeah, this is the schematic of the fan beam and pencil beam. And on the right, you can see these simulations which were done by Mezaros et al. 1988, who predicted what are the kinds of pulse profiles and polarization parameters which you can expect for both these geometries. And magnetars, so they are young, isolated, and neutron stars with extremely high magnetic fields. And for them also, you can probe the magnetic field strength and geometry, and they can actually give a platform for testing the QED effects. And also, there were some very interesting simulations done recently by Kayazo et al. 2022. So what they did was they assumed different kind of structures of the magnetar. So whether the magnetar has whether the polarized emission from the magnetar is coming from an atmosphere or from a condensed surface. And they explored many options and generated the Stokes parameters which are expected for both these cases. So now I'll come to some of the results which we have got from extrapolarimetry in recent times. Before going into IXP, so there was this technology demonstration project by China called Polar Light. So it was a very small GPT-based polarimeter, and they flew it on a CubeSat. And apart from CRAB, they could also get some decent polarization measurements for SCO-X1, which is one of the brightest X-ray spectrums. And what they found was in 2 to 4 keV, there is no polarization, whereas in 4 to 8 keV, they found a finite polarization. And based on the results, they have made some comments on what are the kind of structure. And also, the polarization angle that they found was aligned with the jet axis. So I won't go into details because Ankur has already told. So the main advantage of IXP is that it is almost 30 times more sensitive than the previous polarimeter OSO 8. And as polarization is a very photon hungry kind of technique, so this actually gives a lot of advantages here. So coming to the IXP results from neutron star low mass X-ray binaries. Till date, IXP has observed these 6 sources, and here I have just summarized all the results. So apart from this one source where they could only find upper limits, all the other 5 sources showed some finite polarization. And there were some very interesting results. For example, for this GX5-1, IXP observed it in at 2 different epochs when the Z source was in 2 different branches. And these 2 branches showed distinct polarization properties. And here, as you can see, it has given the geometry for all the sources, like we were able to infer. So I'll go into a little bit detail on 2 of the sources which we have worked on. First is this GX9+9 source, which is a et al. Source in high soft state. So IXP has observed this in 2022 October, and Astrosat has also observed it, but the observations are not simultaneous. Astrosat has observed it in 2022, but since this is a very stable source and its properties are not expected to change much, so we have used the Astrosat data as well to constrain its spectral parameters. So as you can see here, the source is in the banana state, the high soft state, and so this is the spectrum fitted by a disk BB plus NTH com, and the disk has a temperature of some 0.7 keV, and corona has a temperature around 3 keV and optically thick. So from IXP observations, here you can see in 2 to 4 keV, we find a polarization of about, it is not very highly significant, it's less than 1%. And in 4 to 8 keV, we find a higher polarization degree. So we find an increasing trend with energy, and using the spectropolarimetric fits, we could also constrain the polarization of the individual components. So the big contours that you see here is for the disk component. So that is not very well constrained, but the polarization of the Comptonized component is well constrained, about 3.5%. Next, coming to another LMXB source, XT1701. So this is a peculiar kind of LMXB which shows both Z and atoll kind of behavior. So this source was observed by IXP in 2 epochs, and during each of these epochs, there was nicer or new star observation, quasi-simultaneous. So we could do the spectropolarimetry at these 2 epochs. And what we found was, in one of the epochs, there was finite polarization. The results are shown here. And in the second epoch, what we found was the disk component. So this source was also fitted well by a disk plus Comptonization component. So we found that the disk component has become stronger and the Comptonized component has become weaker in the second epoch. And in that epoch, we do not find any signatures of polarization. So that also gives us some clues as to what are the origins of the polarization. So from our analysis and from the simulations that I showed earlier, we could infer as in, these are sort of the best fit that we can say that GX9+9 has a shell kind of corona and XT1701 has a slab corona. And in both these sources, we found that the thermal component is either not polarized or very weakly polarized, and the Comptonized component is polarized. So IXP has also observed a lot of X-ray pulsars, and here is a summary. So the main result that so one of the interesting things here for Hercules, 5 minutes. So for Hercules X1, from IXP observations, first they found the PA of the spin axis, the position angle of the spin axis, and from optical polarimetry results, they found the spin of the axis of the orbital plane, and they found that these 2 axes are not aligned. So they have some misalignment of 20 or 30 degrees. So from this, they inferred that this could be a signature of precession, which was already predicted for this system. And so some other results, for example, this LSV source, it is a transient pulsar, and this was observed during 2 luminosity regimes. One was subcritical and the other was supercritical. And they found that there are significant changes in their polarization properties in these 2 epochs. Then this plot is for Centaurus X3. So this is the pulse profile, polarization degree and polarization angle as a function of pulse phase, which was seen for Centaurus X3. So here you can see this C1 and C2 are the contributions from 2 poles of the pulsar. And in the second panel, you can see that this the red one is contribution from one of the poles. So you can see that the polarization degree is actually correlated with emission from one of the poles, which is also another significant part. So to summarize the results for pulsars, all these have very strong energy and phase dependent polarization. And in all these cases, the polarization is much lower than the theoretical expectations. So these authors try to explain what could be the possible reasons. For example, since we are seeing both the poles, maybe the emission from both the poles has mixed up, and then we get a lower than expected polarization. And we have also found the magnetic obliquity, inclination, and geometry of the system. And finally, coming to magnetars. So IXP has observed 4 magnetars till date, out of which 3 of these are published results. So here I am showing 2 of the results. This is for 4U0142, the first source, and this is the second source. So in this source, you can see that there is a switch in the polarization angle at around 5 kV. Whereas in the other case, there is no switch, the polarization angle remains same with energy, but the polarization degree keeps increasing. So there are many interesting implications. And Yeah. So the way ahead is, okay, we would like to do ideally broadband spectropolarimetry. Spectroscopy, because we want to constrain what is the spectral state of the source at that time and how the polarization parameters vary with energy. So in this context, upcoming mission EXPOSAT has POLIX, which is a medium energy polarimeter, and also EXPECT, which has some overlap in the energy range. EXPECT is 0.8 to 15 kV and POLIX is 8 to 30 kV. So we can get some interesting results from EXPOSAT. And also long-term observations. So for example, we can observe LMXBs at different states and different branches, which would help constrain their polarization properties. And finally, more modeling efforts are required, like self-consistent models, which will explain both the spectrum, timing, as well as polarization properties of these sources.
We have time for some questions, although we are running a bit late, but I think 5 minutes is fine. Because anyway, today there is a less session. So,
Okay.
so yeah.
Don't bank on it.
Yes. So maybe 2 to 3 questions. Yeah, please.
Okay, so I have just one query. Initially you showed two neutron stars, right? Two neutron star cases.
Yes, GX9
What?
9 and
Yes,
XC.
I forgot the name.
Yes, yes.
What are the typical surface magnetic field you got there?
Around 10 power 8.
10 to the power 8.
Mhm.
Okay. All right.
When you talk about polarization, it's all linear polarization.
Yes.
In these sources, what is the ratio of the circular polarization to the linear polarization? If you have any.
Nobody measures circular.
Circular polarization cannot be measured by IXP.
Cannot be
Or actually, it cannot be measured.
It cannot be measured.
In lasers, they try to measure. In lasers, they measure.
Optical.
Okay, not in X-rays. Okay, that was not it.
So in the epoch where the componentized component became weaker, the polarization is also not observed. So the conclusion was that componentized component is providing the but have you or others looked at it quantitatively in the sense that if you assume the entire polarization is coming from the componentized component, then by the whatever amount by which it is decreasing, and will that explain the entirely, the polarization is gone, or I mean, it's below the measuring limit? That kind of quantitative analysis have been done.
So here, what we have tried is try to find what is the polarization of the component and of the disk component. So one ratio is there, and then in the next epoch, we found that the disk has become strong by say a factor of 10, and I'm not sure how that will correlate it, but yeah, I can explain it.
Okay. So in one of the last sources you mentioned about flipping in the polarization.
Yes.
Have you or have these authors checked some sort of light curve where the flipping is associated with any flaring activity or anything of that sort? I mean, what reason they have given for flipping?
So they mentioned that so the flipping happens around 5 kV. So they say that below 5 kV, the polarization is dominated by one of the modes, the ordinary mode, and beyond 5 kV, it's the extraordinary mode. So these two modes are offset by 90 degrees. So,
which was the fourth source here?
1E2259 plus 586.
Any other questions?
Prisoners are named like that. Prisoners are named like that.
Very nice, sir. So when you're talking about the modeling the first profiles and contributions from both pulses, what you actually observe is a total light curve.
Right.
So the contribution from different poles, that is model dependent. Is that right?
Yes, that was actually modeled by Ross et al. 95, I think.
Okay.
So, yeah.
So I mean the green and the red curves, they look very different, but that is a model that is fed in.
Yes.
So you actually do not know what is the dilution because of the two poles.
Right. So we only know what is the angle of observation, and from that we are trying to infer what are the contributions of the two poles.
It's not a question, it's more like a comment and a question kind of thing. So I was wondering, in relation to Rithavan's question, that at a very high luminosity state, it can be possible that there can be radiation-driven disk warping, and that will give rise to some sort of thermal polarization contribution. So, what is your comment on that? Some of the models do talk about the warping of the disk and the polarization contribution of that. So that would be interesting to. Okay, thanks.
Any further questions? If not, then let's thank Kritika and let's also thank all the speakers of this session. We have 3 times now. When should we reconvene? 20 minutes. 20 minutes.
4 o'clock.
Oh.
We are late. Will be at 20 minutes.
We are late.
We are running late.
But then it starts at 5:30.
We start, take 10 minutes late.
Second time talk to you.
There are only 2 more talks, right?
Yes.
4 to 5. I think very late. कॉपी कर लिया ना हाँ हाँ
ले लो मैं लैपटॉप हाँ लैपटॉप पे लेकिन आपको एक बार दिखा
हाँ ठीक है फुल स्क्रीन कर दीजिए नेक्स्ट टॉपिक है नेक्स्ट ले रहेगी इसी पे रख दीजिए ठीक है ना उस पे छोड़ दीजिए हाँ ठीक है
Mean time is important. ठीक है ठीक है
Sì, poi vedete dove utilizzare.
Yeah,
Vedete dove? Addirittura come gratuite.
no.
हमारे एडवाइजर तो एक्सेप्ट कोई तो कि $1 पे नहीं बोलते हैं नहीं बोलते ठीक है তুমি কি বলছো ঠিক আছে বলছিলে পরে বসে আলোচনা করি
One second. Remote. I know iOS people are worrying about it, so I just want to. I mean, not remote, the pointer. Pointer, okay. So.
That's fine.
I think it's, you are the chair. Okay. So, yeah. That master, that's like 20, that's how you.
Good afternoon, friends. Come back to the last session of today. So in this session, we have two speakers. The first speaker will be Professor Bhalchandra Joshi, and he will be speaking on recent results and future prospects of Indo-Japanese pulsar timing array experiment.
Good afternoon, and many thanks to Hillary and the organizers here for organizing this wonderful gathering. We have very good exchanges of discussion. I can speak louder.
So the speaker should be slightly
higher. Is this better?
Yeah, sure.
Okay, so as I was saying, thanks to organizers for letting us review these recent results from pulsar timing array, including our own experiment, Indo-Japanese pulsar timing array, or the INPTA. These results are important because they have opened up an ultra-long wavelength gravitational window for investigation in relativistic astrophysics. I am presenting this on behalf of our collaboration, which is a multi-institutional Indo-Japanese collaboration with members drawn from a large number of institutes, all of which are listed here. And at the outset, I would like to acknowledge that most of the work which I am presenting was made possible by fantastic contributions by many of my colleagues, who is sitting here, but others are not, particularly the young students and the early career researchers in our collaboration. Okay, so gravitational wave was proposed as a postscript by Albert Einstein as a postscript of general theory of relativity. And they are propagating perturbations in the matrix manifested as transverse waves with two polarizations, quadrupolar in nature. And because they are quadrupolar in nature, the frequency of the gravitational radiation from a circular binary system would be twice the orbital field. So that's something to remember for an argument later on. Depending on the dynamics of the masses involved, there can be broadly four different types of gravitational wave sources. Coalescing compact massive binaries produce short duration, intense transient gravitational waves, and so do supernova explosions. But if you have a gravitational radiation dominated in spiral of compact binaries, you can get continuous gravitational waves. And a superposition of a large number of such compact continuous gravitational waves produces stochastic gravitational wave pattern. The gravitational wave spectrum is likely to encompass about 22 orders of magnitude in frequency from attohertz to few kilohertz, as is shown here. While the LIGO discovered the transient sources between 10 to 500 hertz in this high frequency band, the low frequency gravitational waves here were as yet undiscovered till this year. The most promising waveband here is the ultra long wavelength waveband, or equivalently nanohertz frequency range. And the most likely source here is the stochastic gravitational wave background formed by incoherent sum of a large number of supermassive black hole binary systems. So these supermassive black hole binary systems formed by mergers of galaxies. So the dynamic friction in a merger of galaxies would drive their central black holes to form the supermassive black hole binary systems, which we are talking about. And in the late stage of the evolution of these binary systems, you will have a gravitational radiation dominated evolution, which would span several millions of years, with the gravitational wave frequency increasing as the orbital period shrinks due to gravitational radiation. Now, the gravitational wave from an individual supermassive black hole binary system is below the detection sensitivity of the detectors, which I'll talk about a little later. However, you can detect a stochastic gravitational wave background, which is formed by an incoherent sum of isotropically distributed supermassive black hole binaries of all types throughout the universe with different frequencies. Now here one should realize that the long orbital period binaries will last relatively longer compared to short orbital period binaries. This difference in the residence time leads to an increase in the number density of these binary systems in a large orbital period bin, or equivalently in the low frequency bin. And that endows the stochastic gravitational wave background with a characteristic spectrum of the type which is shown here by this dotted line. Now, there can be other models which are there in this particular plot, which if somebody is interested, I'll talk about it later on. But that is what you expect. And if you say that I want to discover gravitational waves from stochastic gravitational wave background, one of the criteria is to actually detect this spectrum. Now, to detect this spectrum, you need to have a detector which will measure the variation of the proper distance between two different points in the space. And given that the wavelengths which we are talking about are of the order of parsecs, you need a galactic size detector. And the propagation of the electromagnetic signals from compact massive stars, neutron stars, the radio pulsars, provide a very precise way for doing such measurements. As I'll elaborate later on, for some different reasons, what is done is that we use a collection of widely separated pulsars, which are distributed uniformly across the sky, to form such a detector, which is called as pulsar timing array. Now, I will quickly, all of you know about this, I will not say much about that, except saying that the large rotational kinetic energy reservoir of these neutron stars make their rotation very stable. So by definition, they are very stable clocks. And amongst the 3,500 clocks known as of today, the shortest period pulsars, or the pulsars with the smallest magnetic fields, also known as millisecond pulsars, are the best galactic clocks for doing any gravity experiment, including gravitational waves. So that is the main reason why these stars are used. And you form the detector by timing the pulses from the radio pulsars, and that technique of pulsar timing effectively compares the prediction of pulse time of arrival from an assumed rotational model of the star with the observed time of arrival, keeping track of the number of rotations of the star. And the model involves a large number of parameters, the rotational parameters, the astrometric parameters, the line of sight propagation parameters, and different Keplerian as well as post-Keplerian binary parameters. And if your model is good, the difference between the observed and the predicted time of arrival, which is also known as timing residuals, should have a white noise spectrum. On the other hand, unmodeled effects in your timing model would come out as systematics, and then you will have to add additional parameters to sort of refine your model. So that's the essence of this particular technique. Now, as far as the gravitational wave is concerned, the apparent frequency of the pulsar clock will vary because of the perturbation in metric by the passing gravitational wave. And here I'm talking of gravitational wave in the vicinity of the Earth. So that makes the gravitational wave signal appear as a systematic effect in timing residuals. It appears like a time correlated red noise signal. And I'll use this red noise again and again later on. As I'll show later on, this is not the only red noise signal which we see in timing residuals. We also see red noise in different individual pulsars separately, which could be because of rotational rate variation of that individual pulsar or variations in the propagation effect towards the individual line of sight to this pulsar. So for this reason, a single pulsar is not used as a gravitational wave detector. Instead, one employs large number of pairs of pulsars. And the reason there is that these nuisance red noises, the rotational rate variations and the propagation variations, they are uncorrelated across a pair of pulsars. On the other hand, the gravitational waves red noise is correlated across pairs of pulsars, and the correlation is given by a characteristic form, which is sort of shown here in this particular plot, which is also known as Helling's endowment. So, in summary, if you want to discover a gravitational wave, you need two different conditions to be met. First, you should be able to detect a common red noise across pairs of pulsars with a power law spectra and a spectral index of 2/3 if you are in the characteristic strain domain, or 13/3 if you are looking at the timing residuals. And secondly, the PTA should be able to establish a spatial correlation in the form of HD correlations. And that is what I think all the PTA experiments are doing. So there are 4 major regional PTA experiments currently in operation: the European Pulsar Timing Array, the Indian Pulsar Timing Array, the North American Nanohertz Gravitational Wave Observatory, and the Parkes Pulsar Timing Array, with data spans ranging from about 7 to 25 years, and the sample of pulsars being used ranging from about 20 millisecond pulsars to about 67 millisecond pulsars and so on. And there are 2 emerging PTA experiments also. This year in June, all the 4 major experiments made the latest, the release of their latest data, and which also included the EPTA and INPTA. It so happens that the EPTA and INPTA data set complement each other very well in time baseline and frequency coverage. So the 2 of these PTAs, that is EPTA and INPTA, decided to conduct a joint analysis of their data set instead of doing a separate analysis. The other 2 PTA experiments did it separately. Finally, all the PTAs, they contribute and pull their data together into what is known as International Pulsar Timing Array to form the most sensitive PTA data set for any gravitational wave related experiment. So the European Pulsar Timing Array data was obtained with the 5 most sensitive telescopes in Europe listed there, and basically consisted of a sample of about 25 pulsars over 25 years, mostly covering frequency range between 1 to 8 gigahertz, and a time baseline from about 13 years to about 25 years and so on. This long time baseline was used to refine the rotational, astrometric, the propagation, and the binary parameters of all these 25 pulsars. And that led to estimation of new parameters in about 12 pulsars and improvement of parameters in the rest of the pulsars. So the long time baseline was useful in getting the systematics in the timing models out of the way. Now, much of the older data used legacy system, which has a much lower sensitivity than the current, more recent data. So therefore, it was decided by the collaborations to analyze the data in 2 parts. One was the full 25-year baseline, which is known as DR2 full, and the other was the most recent 10 years of data, which is known as DR2 neo. The Indian Pulsar Timing Array, as I said, is an Indo-Japanese collaboration of 40 scientists, which observes about 20 to 22 pulsars once every 14 days for the last 6 to 7 years. And the INPTA uses the niche capabilities of the UGMRT. The niche capabilities being the sub-array feature of the GMRT, where you can divide GMRT as 2 co-located 75-meter telescopes using the sub-array feature to conduct concurrent observations at 300 to 500 and 1260 to 1460 megahertz And this is something which is very unique to INPT experiment. No other experiment does it like this. And that endows INPT experiment with the ability to make high precision dispersion measurements and characterize the effects of interstellar medium to a large precision. And this kind of precision is not available in the PTA, in other PTA experiments. Thereby, we actually complement the other international data sets very well. So, last year in 2022, the INPTA made its first public release of the data, which is known as INPTA DR1, led by one of our postdoctoral fellows, Pradeep Kalatlar, which comprised of about 14 pulsars with a time baseline of 3.5 years. So while, and also the high precision DM time series, which was published for the very first time. Now, while the INPTA time baseline is relatively small, about 3.5 years compared to 24 years of EPTA, EPTA lacked the frequency coverage. They had only observations above 1 gigahertz. And there were 10 pulsars which overlapped between the two samples. So in that sense, the two data sets, as I said earlier, were very complementary with each other. And the two collaborations decided to jointly analyze this. And again, the data was jointly analyzed in two parts. One for the full time baseline and one for the more recent data. So the main difference in the recent analysis, which the EPTA and INPTA did from the past efforts, was the use of more advanced noise models. So I have already introduced that you have spin noise and you have ISM noise, which is covariant or which varies similarly to the gravitational wave signature. So accounting for this is very important. This was done by analyzing the timing residuals after removing all the systematics in terms of the astrometric, rotational, and propagation and other effects. And then conducting a Bayesian analysis to get time correlated noise models. And 3 different types of noise models were used here. One was achromatic spin noise, which is just giving you some idea about random variations of the spin rate of the pulsar. And time correlated chromatic DM noise with the observing frequency dependence going as -2. And a chromatic scattering frequency thing which goes as e to the power -4. The basic noise models were parameterized as power loss in spectral domain with an amplitude and a spectral index gamma. As an example, there are these 2 plots. The bottom plot here shows the computation of the noise model from the INPTA DR1 data for this pulsar J1913 plus 2134. And what is shown here is the log amplitude and the gamma for the achromatic spin model on the leftmost plot. The middle one plot shows the DM noise models, and the rightmost plot shows you the scattering model. It must be noted that these 2 models could only be computed because we have a low frequency coverage in the INPTA data set. It cannot be computed at high frequency. The top panel illustrates the constraining power of the INPTA data set in the joint data set. The gray, so what is shown here are the posteriors again for the noise models, the amplitude and gamma and so on. And the plots in the gray are the posteriors computed from the EPTA alone data, whereas the plots in the blue are the posteriors for the joint data set. And as can be seen from these plots, addition of INPTA data constrains the noise model significantly, improving the ability to actually detect the gravitational waves. So these noise models provide variation of residuals due to noise processes, and one needs to subtract these from the timing residuals to be then finally left with the systematic, which is only gravitational wave, and there are no other noise contributions there. And accurate models are very important for this purpose. So this was done, and then we did a joint gravitational wave background search analysis, and the results are here. As I mentioned earlier, you need 2 conditions to be met. One is the spatial correlation, the HD correlation, and the second is detecting a correlated red noise with a spectrum parameterized by its amplitude and the spectral index gamma. So what is shown here in the right plot is the log amplitude on the y-axis and the gamma on the x-axis. And the contours show the posteriors for the two data sets. The common red noise was detected at very, very high significance in our joint data set. What is shown on the left plot are violence representing the posterior distributions from our pairs of pulsars as a function of angle between the two pulsars. And the orange being the posteriors for the DR2 new set, and blue being the posteriors for the DR2 full set. And the expected HD correlation is plotted by this solid line. And as you can see from this plot, the analysis suggests 95% confidence limit detection for the HD correlation. Together, both these conditions suggest that detection of the stochastic gravitational wave background at something like 3.5 sigma level in the DR2 nu plus set. Interestingly, we also see something which we don't expect, that this orange, the recent data set, is just barely consistent with this 13/3, which is the expected spectral slope of the stochastic gravitational wave background spectrum. And there is a mild tension here. And these results were announced worldwide in June 2022. Now, what was done afterwards was that we compared, so the results which we got in EPTA plus in PTA were also corroborated by similar results from the other two experiments, that is nanograv and the PPTA. So while the detection significance varied from 2 in PPTA to 4 in nanograv, the results are broadly consistent. And what is shown here are the posteriors for the common red noise spectrum, where the posteriors for the different PTAs, the contours for different PTAs are plotted in different colors. And a very quick and dirty combination of data from all PTAs, the posterior for that is plotted by this solid black line. So one thing which you can see is that all the three experiments, they are giving more or less consistent results with each other. But more importantly, when you pool the data together from all the three experiments, you get a posterior which is much more narrower. And again, surprisingly, not very consistent with 13/3, which is again the dashed line there. So it means that a full combination is likely to yield a much higher significance detection of the stochastic gravitational wave background. When you add data from different PTAs one by one in a particular order, you can get an idea of the kind of signal to noise ratio which will be achieved when a full combination of the three PTA experiments will be done. And that is illustrated by these plots here. And one can see that even if you have a permutation combination of different additions, you are likely to end up at about around 5 sigma kind of a detection, with a detection of the log amplitude at about -14.6. However, a word of caution is necessary here, because the different PTAs use different noise models. The methods are very, very different. And in fact, noise models for certain pulsars in different PTAs are in tension with each other. This analysis completely ignores this. This is a quick and dirty analysis. So what is needed is a real combination of all the three PTA data, a unified noise modeling and so on, which is right now underway. And we will sort of start getting preliminary results early next year and maybe published by middle of next year. What is to be noted is that PTA members are playing leading role in this analysis. In fact, in 2 of the subgroups, the leads are our own PhD student, Raman in noise modeling from PTA, and Suvajit Danpat in Bose for gravitational, which I think Goku will talk a little later. So, so this is ongoing, and hopefully we will have some better results next year. I would like to end by just highlighting some of the very recent work that which PTA is doing. So, PTA team continues to work towards improving robust noise models. And one place where a contribution can be made is scattering. Because time variable scatterburning of pulse induces time variable DM measurements, as can be seen in this top left plot, where the green and blue are showing a bias, which is a variable bias from this magenta colors in simulated data. So one of my students, now a postdoc, Jaikhomba Singha, and the rest of the team has now worked and devised a new method which seems to work, as can be seen in this bottom left plot, where this bias is removed after applying this particular scheme. And we have recovered the DN time series, unbiased DN time series of pulsar J1643 minus 1224 using this technique, where this pulsar suffers from variable scatter broadening, as is shown in the plot here. So systematic like this, if they can be removed, you can get much higher quality, much more robust DM models, thereby increasing the number of pulsars which effectively contribute to the gravitational waves. So this is one of the ongoing pieces of work which has recently been submitted. Other work which is yet in preparation, this preliminary result is pulse jitter, which is a white noise due to pulse-shaped fluctuation, and this dominates at low frequencies where the PTA operates. The canonical wisdom is that jitter increases as you go down in frequency, which means that low frequency observations are actually not that useful for PTA experiments. But surprisingly, in this particular study, led by Tomanosuke Kikunga, who is sort of leading a team on doing this, we find just the opposite. That is, the jitter actually reduces as you go down in particular frequency, and we are checking these results. But if this result is true, that means it allows us to have a much larger sample of pulsars being observed at low frequency, and again, GMRT playing a very important role in that, to sort of not only go beyond the 5 sigma, but start doing real physics out of the gravitational waves. So there are lots of implications of these results. I will not go through all of them. Basically, it opens a new gravitational wave window, but we also have a mild tension with what we expect from the stochastic gravitational wave background. And you need new physics elements, which I hope Gopu will refer in his talk. I will not sort of go into the details of that. One of the PTA also has suggested that the gravitational wave background signal seems to change over decades. So it doesn't seem to be stationary. Now, this result has to be checked. We are not sure about it. But if it is there, it is indicating some totally different physics of the universe. And the significance is different over different PTAs. 3 PTAs are in the northern hemisphere, 1 PTA is in the southern hemisphere. So do we see an anisotropy in the stochastic gravitational wave background? So these are some of the open questions which still need to be studied with future data. So to end my talk, here is my summary. In PTA, PTA has uncovered significant evidence, 3.5 sigma evidence for spatial correlation, and similar evidence has been seen from other experiments, thereby opening a new window of gravitational wave astronomy at ultra long wavelengths, complementing the window already opened 8 years back by the advanced LIGO experiment. We see mild tension with the expected spectrum, and this has implications for new physics and also for multi-messenger astronomy, which I think Gopu is going to talk after me. But more importantly, the work is still going on. Combination of data of all these experiments is in progress and is likely to yield much higher significance in the coming years. So please keep waiting for more results. Thank you.
Thank you very much for the presentation. So there can be some questions. We'll go for some questions. Yeah.
Very naive question. So, assuming that your tension goes away and you can sort of, whatever results we are getting, you can say that this is the stochastic gravity waves for sure, let's say. So, how do you see that it's going to change our understanding of of the universe? I mean, could we sort of count the number of, we will not be because it's stochastics. We won't be able to count the number of supermassive black hole mergers. What exactly, I mean, it should usher into?
Yeah, no, I think good that you asked me a question. I didn't have time to go into it. So this gives me an opportunity to go into that. Understanding of the universe. Okay. Let me go back. Okay, so this dashed solid line is 13/3 spectrum. If you have gravitational radiation dominated in spiral of large number of supermassive black hole binary systems. The assumption is gravitational radiation dominated in spiral. What if you have other things? You have, and this is exactly what you people have been discussing, and I think Gopu asked the question on the first day about accretion disk and interaction between two black holes in the accretion disk. So if you have gas dynamics or stellar dynamics, which produces friction, which right now in this assumption, in this spectrum calculation, it is assumed that GR is the gravitational radiation is dominant. There is no dynamic friction. But if dynamic friction is there, then the slope changes. Okay. And these are, so for example, if you have a viscous disk, that is this red curve. If you have a stellar scattering, that is some other curve. And the interesting thing is that as you go to lower and lower frequency, there is a curve. Now, right now, we are somewhere here. Because by design, this experiment is such that it's like something which is slowly emerging out. So as the time baseline increases to 30, 35 years or longer, you will be exploring this and this part of the spectrum. So this turnover, there is a vague hint of it, but it's very speculative. Maybe another 5 years or 10 years of this data, you would actually be able to distinguish between all the models which are here. The model which I talked about is only the dashed line, but there are other models in this particular spectrum. So with longer observations, the short answer to your question is with longer observations, you will be able to constrain the galaxy evolution models much better. And the current spectrum is calculated from M sigma and Kormandi and Ho and those relations, which have a huge scatter. And the physics there is not very well known. So this spectrum will actually start giving an independent constraint on those models.
You mentioned about the jitter, the pulsar jitter, and you said that the low frequency data would not be more important, but you see something different. Now, what I want to ask is how critical would be meerkat and LOFAR, even going more lower frequency than JMRT to the
Not
pulsar?
meerkat. Meerkat actually the low frequency is still not very much operational. So the UHF band is hardly used there. Okay. But yes, meerkat has a very nice band which goes up to 600 megahertz. But if you really want to go down to the JMRT frequencies, you have to wait for SK phase 1. So when SK phase 1 comes, yes, this picture will change significantly. As of today, JMRT is the only instrument which can do this. There is no other instrument which can. So when I said it's contrary to popular belief, there's only one observation, which is from meerkat. That observation is from 1 gigahertz to 1.8 gigahertz. It shows exactly opposite behavior. It shows a behavior like this. So I think there is a turnover here. And I was discussing with Manonita also. This turnover has implications. So forget about PTA and gravitational wave. This turnover has good implications for the emission mechanism of the pulsars. So there are lots of things which can come out from this experiment, which are not necessarily gravitational wave, but other associated astrophysics.
Is there any other question, pressing question? Or yeah. So we thank the speaker very much for the briefing talk. Now we invite Professor A. Kumar for his talk.
Thank you. Yes. We'll give you some one. Sure. 25 minutes, right? So first of all, let me thank Indranil and his colleagues for allowing me to speak after the master. So it's very nice to be here. First time in this part of India. I'm really enjoying it. So today I'm going to talk about something, Balchandra kind of mentioned briefly about it. It's about this nanohertz gravitational astronomy, but it's what we call as persistent multi-messenger nanohertz gravitational astronomy. So I'm from TIFA, I'm part of NPTA and IPTA, and I spent some time in Korea. So I will give you an overview about something called multi-messenger astronomy. These days that actually metamorphos into multi-messenger gravitational astronomy. And I'll talk about this interesting aspects of transient messenger combined with persistent electromagnetic messengers these days, and there's lots of implications. And our hope is that we can actually do persistent multi-messenger in all messengers are persistent, and it's only possible with active galactic nuclei and with nanohertz gravitational wave. And this talk will be on that aspect. I will be very, okay. So many of you may not be around in those days. So the first multi-messenger astronomical event of humans is essentially that object called SN 1987A. That was the first supernovae of that year. Unfortunately, could not have been seen from here. It's kind of southern. And so this is a type 2 supernovae. And that's essentially the new guy hanging around there. This is a new star was born in not very far from here, large Magellanic cloud. It's 50 kiloparsec away. And the interesting aspect is that neutrinos were detected by Kamiokande and other observatories in the US, but that collaboration never realized that that observation could be used to actually bound neutrino mass. In those days, neutrino mass were not bound at all. Okay, so here what happened was these neutrinos, after traveling something like 50 kiloparsec distances, arrived with a slight time delay. Something like the 38 MeV neutrinos came, slightly earlier than the 22 million electron volt by something like 5 seconds. You can actually do special relativity and obtain the gamma factor of the lowest energy one in a very straightforward back of the envelope calculation and put a mass which turned out to be around 35 electron volt at that time. The collaboration totally missed this point. This is very interesting, and somebody actually pointed it out. We can also do this. And of course, now things are done much better. It's actually a fraction of an electron volt, but I'm just giving you the power of multi-messenger astronomy to begin with. Okay. And gravitational wave astronomy, as Balchandra mentioned, opened up this era of dark messengers. And gravitational wave are, for all practical purposes, are essentially propagating tidal interaction. That's the reason they actually deform this ring of particles in a very peculiar manner. We call this plus and cross polarization. And naturally, this actually causes travel time differences between, idealized point particles. That's essentially what LIGO does for a living. They have the interferometer, which essentially mimics those test particles. And we just look for residual light from a dark port of this observatory, and any flickering light which comes out of that dark port is equivalent to a gravitational wave signal if it follows certain path. And that's precisely what happened in this famous event now, 1509-14. That's happened, 2015, September 14. So what the observatory saw in a coordinated fashion, the output of those interferometers split for something like 200 milliseconds. And when you take a time frequency map of that, this is what they see. They just see, the frequency and time. The frequency increases rapidly from something like 30 hertz to something like 300 hertz in 200 milliseconds. That's all it is. And so this is how the strain looked like. So the important thing is that the gravitational waves actually give you amplitude. We are not doing electromagnetic astronomy by measuring the photon count and all that. So just by this, binary pulsars actually told you how the frequency will change with frequency. Frequency derivative should change with frequency. You can estimate the mass of the system. Just by looking at the amplitude, you can actually roughly figure out, if you know the mass, the distance. So this is why the single event gave you an astronomy, because the mass is provided, combination of masses, doesn't matter, and the distance. So any observatory who can do that will give you an astronomy. And that's precisely why the gravitational astronomy began at that. It just turned out to be a merger of 30 and 35 solar mass black holes happening at around 400 megaparsec. Okay, so these days, the LIGO Virgo Kagara collaboration is picking up something like 150 such transient events. But more importantly, there was a very, very special event, what we call as 170817. The signal lasted for something like 100 seconds if you really push but roughly 30 seconds. Compared to 200 milliseconds, 30 seconds. And there was a coordinated observation as usual, and turned out that Virgo did not see anything. So 3 observatories, not just 2, it gave us the position and localization of 28 degrees square out there in the sky. And then, because it was going on for something like 30 seconds, you can actually estimate the chirp mass, that mass quantity I showed very precisely. You can see the error in the digits and all that. And immediately after that, a gamma ray burst was observed, something like 2 seconds after the conclusion of that event. And that opened up so-called the multi-messenger gravitational astronomy. So this is what happened. I'm going to go very fast on that. You saw after that, within 10 hours, there was a kilonova, a star was essentially identified, which turned out to be around 40 megaparsec away. It was followed by all pieces of glass on Earth. And it turned out that this optical afterglow was actually powered by radioactive decay of heavy art processing elements. Actually, even strontium was identified. And so, it has fundamental implication for physics, astrophysics, and cosmology. You actually get a dark siren and whatnot. And this is all because we just have 100 seconds of data coming from the neighborhood. So, and then Prateek will talk about that in great detail. Just after that, I don't know why 2018 turned out to be a very useful year for everyone. So there was this multi-messenger observation of a blazar close to this community, and the neutrino was picked up. And I'll come back to that in a minute, but not now. It has interesting implication even for PTS. I'll come back to that in a minute. But these are all transient new messenger combined with persistent electromagnetic messengers. So can we imagine a scenario where all your messengers are going to be persistent or periodic at least? And that will be amazing, especially if they are cosmological in nature. And Balchandra already gave you this introduction. Pulsar timing array, this is the cartoon of that. We monitor a bunch of millisecond pulsars. And it turned out that, so this is the International Pulsar Timing Array to actually inaugurate the full era of nanohertz gravitational astronomy. It turned out that our sources are supermassive binary black holes, which is of interest to this community again. For that, you don't have to do very thorough analysis. What I plot here is frequency as a function of, the strain of that gravitational wave amplitude. So the amplitude of the gravitational wave, which goes like 1 over r in some combination of the masses. So we can actually see a self-gravitating system, omega square r cube equals gm, put r equals m because it's binary, the black holes involved. So you can actually see that the peak frequency of such self-gravitating black holes will be essentially given by 1 kilohertz times 10 solar mass divided by m. And if you put around 60, you find peak frequencies in the LIGO bandwidth. If you put 1 billion, you saw that in the nanohertz. And that's of our interest. Hence, binary black holes are the natural candidates for nanohertz gravitational wave. And if you put 1 million solar mass black hole, you find things in LISA bandwidth, which is going to happen when many of you are my age. Okay. And the pulsar timing array, I just want to, again, the point here is omega square R cube is GM is all it requires. You can actually see that if you have supermassive black hole binaries separated by something like a few hundred M total mass, and something of the, if you put them at something like a gigaparsec, 10 raised to minus 15 naturally comes, and that's what we are searching for. What we do essentially is a LIGO observatory in space, in our galaxy. Each pulsar becomes one arm of an interferometer, and we cross-correlate things, okay? And so millisecond pulsars are required, Balchandra is required, and all that, okay? Okay, so why this is exciting? So we all know the galaxies do merge, that's fine. And then there are dynamical friction, scalar scattering, all those things will be required to bring those cores together. And after that, when the separations are somewhere in the milliparsec, gravitational wave can take control of the system to merge it within the Hubble time. However, we have no idea. This is all pure speculation. There's no observational evidence for any of these things. There's something. And so we need to see that. And that's precisely where the gravitational astronomy will deliver. So you can see that this is what kind of sources we are seeing, the strain and the frequency. We see a plethora of sources here, the incoherent superposition of millions of such sources. That's one thing Balchandra mentioned about. On the top of that noise background, we will see individual events. So this is essentially CMBR kind of coming into gravitational waves scenario. And there's something called merger, which will give you something, a memory event. I will not go into the details. Please ask me if you are interested. So this is the deliverable, okay? You will be able to know many of these astrophysical aspects, which are purely theoretical for the time from the observational point of view. And then, so these are the three candidates we think. We should eventually see individual supermassive binary black holes, but the stochastic gravitational wave, that's what we call the red signal. You can see that if you take the red curve, take a frequency, take an FFT, you find the power in the low frequency, hence it's called red. Okay, so why it should give a background? So what I'm going to do is that I'm going to ask how many such binary black holes will be in a small frequency interval of PTA, which is 1 over T observed. Balchandra, so these are going to be decades. So I can rewrite that thing, and dF by dt naturally comes in, which I showed you in terms of the chirp mass. So I can rewrite that number. You can see that the number of supermassive binary black holes in a tiny frequency bin of something like 10 nanohertz will be of the order of a trillion. So you can say that I'm all wrong here, but there will be several, hence it's a battle. Okay. And so this is, and this will come as a stochastic, it's a correlated red noise. That's what I talked about. I'm going to miss that. And this is stochastic. So you have an amplitude and the frequency component. Alpha, Balchandra said 2 over 3, again related to the fact that omega square R cube is GM, circular binaries, and all that. And so this is the recent result. I'm just displaying it for a purpose. Again, the question was there. So you can see that this is the expected curve from what we see from circular binaries. At the low frequencies below that, that may be because the supermassive binary black holes are not merging along circular orbit. Something else is perturbing them, which is a possibility. And then high frequency is different. This is why all sorts of new physics papers, my theory is being confirmed by Nanograv and others, but that's something will happen on that. So this is combined results of ours. And so as Balchandra mentioned, we are combining our resources and we are going to search for the background. Hopefully we will pick it up phi sigma. That's what the 3p plus comparison is showing. And in this effort, our young kids are really driving many of these. Aman Srivastava, as Balchandra showed in the noise analysis, is one of the colleagues. Shubhajit is actually doing something called bus with memory researchers. Lankeshwar Day and Abhimanyu are actually co-leading search for individual supermassive binary black hole in the acid. This is all very important because there was a hint of evidence for an isolated supermassive binary black hole in both Nanograv and EPTA plus InPTA result. It's around 4 nanohertz. So we need to do very careful analysis of that. So that's what our kids are doing. And we are all very excited because the square kilometer array is going to change everything. What I plot here is essentially the spectral density, power spectral density. It's a version of that scaled by the energy density required to close the universe as a function of the frequency. You can see that the nanograph or EPTA, they are all here 10⁻⁻⁸. SKA, a million times improved, factor of million will be out there. And that's where things are going to happen. And it's already under construction. And so you can see that individual supermassive binary black holes becomes interesting. So this is a paper from my good friend D. Lee and a student. They actually saw that there's a source called OJ287, which seems to be above the noise level of SKA era PTA. So what is that OJ287? So that's what I work on. It's closer to the blazar community here. So it's a very unique blazar. And its light curve has been known for something like 120 years, because this is an eclectic people who are looking at it for fun, but looking for comets and finding this guy. And it has a very peculiar light curve. It's a quasi-periodic, and so there will be brightness periods like that, but superposed on them as these double periods, double flares, which happen regularly. And so naturally, this was argued because when you see something, double and periodic, put a binary. So my good friend Maury Walton and his grad student actually say that this is a scenario where you have supermassive black hole surrounded by an accretion disk and a companion, which is a highly inclined orbit. It passes through the accretion disk, twice in 12 years orbit, giving you those flares. And we can actually, and that's where I come in. I kind of play with some equations, like this is called Poisson-Newtonian equation. They are corrections to Newtonian equation based on GR. So we actually can predict those trajectories and within a bit of astrophysics and predict when these things will happen. We go very high order. This is essentially Lankeshwar Day who actually did all this detailed calculation. So back in 2018, we made a prediction that the next flare will happen July 31st, 2019. Okay. And we even predicted how the light curve looked like. And many of you work on blazars. You know that this is idiotic, right? Predicting blazar flares is like committing suicide, So we actually wrote, and turned out that OJ287 was very close to the sun. And so the referee objected, saying that this is, theoreticians' way of smuggling in theory, because you can't observe it, so what can you do about it? It turned out that Spitzer was warm and it was drifting away from Earth. So we actually wrote a proposal. You can say this is, write something like predicted Eddington flare testing black hole no-hair theorem. So, they were very amused. What kind of, this is not supposed to be for Spitzer's job anyway, but it doesn't matter. So I have this nice thing because this is, can you display that? Okay. So that's precisely what we did. I mean, we were ridiculous, right? I mean, don't do this kind of idiotic thing. Can I go to the next one, please? Okay. We don't predict players from blazars. Okay, that's as simple as that. Okay, this next one. Yes. And we actually predicted, and we actually observed OJ287 in the Spitzer telescope. They gave us time, like many folks. And then this is what happened. So we actually have because this is repeating stuff, so we actually can predict what kind of light curve was expected, because this is called a Pegastron flare and all that details. So we actually can, yes, we actually shifted that into that epoch we required. And you can see that these are the two channels of Spitzer. And we have to do a bit of subtraction of the magnitude because one was optical, this was infrared. We actually did that kind of analysis earlier just to convince the referee this is all done. And this gave us fairly confident that things are happening. So we actually have a movie on this. JPL was very happy to publicize this a lot. So I'm going to skip that because I may not have. So the paper came. So finally, we were able to get Spitzer to perform a test for GR, which is very nice. If I have time, I will play this movie at some point of time. So But this is not the first time. We have been actually doing this in 2007, 2015, and now 19. So we have a confidence that this looks like a nice candidate for a supermassive binary black hole that can be pursued by, IPTA collaboration, especially with the SKA. But now the problem is that what kind of signals are expected? Those are the jobs of theoreticians to do. That's what we do these days. And so, but naturally, before we do all that, are there any other way of constraining these things? And it turned out that we actually have a way of doing it, because big facilities like EHT and GMBA, they are actually monitoring tip of OJ287 jet, and it actually varies in time. We know how to model that using our binary black hole prescription. We actually have a prediction for how the position angle of the radio jet will move as a function of time. You can see that this is our prediction based on some earlier, very raw observation. And so they have been now, so that's the paper with Loki explaining temporal variation of OJ287 PA. So now this has been followed with GMBA. You can actually see that now interesting results are slowly emerging, but this is not my collaboration. We are consultant there. Things will happen. Let's wait for those. But we, as I showed you in that paper by D, this guy will be picked up by SKA or PTA if it's a binary black hole. I'm not going to say it's a binary black hole, it's a candidate. You want more and more ALMA time to do all these things. So then we need to model the expected pulsar timing array signal, and that's been going on with Abhimanyu, Loki, and others. So in fact, he has a package to do all this, and so this is fairly complicated, using general relativistic inputs to expect, to model what pulsar timing array consortium should see as timing residuals. It's in fact, these guys are now with Nanograv, they graduated, and so now they actually use their knowledge and to constrain an interesting candidate with Nanograv data. So they are the corresponding others. These are the complicated signals. You have to worry about both the Earth term and pulsar term, GRF evolution, and all that thing. So, but more things are coming. So Pratik will talk about this very interesting AGN tomorrow. We took this slot today, and it turned out that they looked at with GMVA this AGN. It seems that there are two jets, one old jet and a new jet, a tired jet. These neutrinos may be coming from the collision zone of that. And how can that happen? Wandering jet direction now has been actually pointed towards a binary black hole in it, because there were earlier scenarios of neutrino emission. So, and now we are getting more interested because we know how to do this slightly better than those people. So we are getting into that act too. So slowly in spiraling, massive black hole binaries will be of definite interest to not just the square kilometer array IPTA, but with NGHT, we can image OJ287, for example, with NGHT, Ice Cube generation 2, and all great observatories, because we would like to get the spectral lines from, especially when OJ287 like systems are quiescent. So we should be able to get, and M sigma relations are difficult, but bulge luminosity, black hole mass can be verified and all that. So we hopefully our NPTA colleagues will actually pursue this in the coming years, and we will have this persistent multi-messenger gravitational astronomy. And of course, we are motivated by and constantly inspired by this amazing visionary. Govind Swarup back in 91 wrote an article about GMRT, a review article, and actually pointed out that it says a large number of millisecond pulsars will be monitored in an effort to attempt to detect gravitational waves. And that's essentially what Bharchandra is doing these days. So we are trying to influence ourselves by such visionary. And so this is a very frugal indigenous collaboration with essentially no funding compared to 3,000 crore. So our effort
no
is
point in complaining here.
I'm hoping that it's someone in YouTube.
So our aim is to detect and characterize this gravitational background, and then to follow persistent multi-messenger gravitational astronomy, which will have fundamental implications because we're going to do dark sirens at cosmological distance. We only need few, we don't need thousands. And that's the game. Thank you very much. And please join us in the amazing adventure.
Thank you very much. We can take a couple of quick questions.
Can we play that movie? Just as a background? Yes. Please go ahead.
Thanks for the nice talk. Yeah, right now we do not see any evidence of sub-parsec supermassive black hole binaries, and there is one theory about the final parsec problem. So, what is your comment about that, and how, like, about the origin of this gravitational wave?
Sure. Yeah. So, if you are a hardcore theoretician, you will say that this is coming from cosmic string only. No binary black holes, cosmic strings. That we will shut down very soon. That's different. I can't tell you why. However, we are most likely seeing a supermassive binary black hole background, which means all this final parsec problem was essentially a theoretician's, creation, in the sense that you are talking about loss count is not replenished. Maybe it's true in a spherical symmetric scenario when you have axisymmetric potential, and it has been demonstrated by n-body simulation. It doesn't exist. And then circumbinary disk, if possible, they can actually make binary black holes to kind of go to the milliparsec regime. So all these are, the world out there is much more complicated than the simple argument about loss count effects, essentially stalling. And David also agrees, David Merritt also thinks that those interesting, but this will provide the actual observational evidence. And this is just the precursor, because Lisa, we're going to see many of these things in a different mass regime. So we actually can see this in billions to billions of solar mass black hole scenarios. So that's my interpretation of that.
Thanks.
We have already seen something. So how do you explain?
Very nice talk. I have a question regarding this OJ287. When this secondary black hole passes through the accretion disk, doesn't it perturb the accretion disk, and would you not basically see some warping action associated with it?
Yeah. So again, I'm part of those papers, but I don't do anything. So they ask for an interpretation. So there is a bend jet been seen, and also there are evidences for some sort of perturbed disk in this is essentially coming from radio astron because that went all the way to moon. So we can have some good resolution. Jose told me about this. But again, that's not a unique interpretation. Okay. And what we could do as a theoretician is that will it affect the dynamics, because it's friction. It turned out that that can be negligible, what we call as a pi PN effect. So I threw it out from the analysis.
OJ, what is the mass ratio of these two?
So it will be around 100 plus of it. So 100 million and a billion. So that's kind of.
Can you play the movie now?
Yeah. So this is the movie. This is for the. And please watch it so that it's 1 million views.
I have one question. Maybe nice question. Stochastic background, what you are talking about from supermassive black hole, can also be origin of cosmological in this frequency range?
Very good question. There should be something.
Because there are proposals.
Yeah, there should be something. However, so this is the next level. In SKA, we will get this frequency dependent in such a fine detail that we can actually remove this background saying it's a noise. And look below that, and that may be where the stochastic, the cosmological things kind of offer. Right now, we think, especially nobody was expecting such things for the time being. So our signal is definitely louder than earlier estimated. So it's definitely most likely due to there are other reasons. So due to supermassive binary black hole, there may be as cosmic strings and other things are all possible. So one of our colleagues are going to search for individual cosmic string effort to see whether is there in the data.
Andrea Ghez got the Nobel Prize of doing this with a star. Okay. Without an accusation.
I hope that my
Am I seeing
younger
a
colleagues.
future Nobel Prize
No,
winner?
no. My younger colleagues maybe, when they do multi-messenger, that's the reason join us. So.
Yeah, just a comment as a follow-up of that question. So phase transitions would lead to the things. Topological defects would also have a contribution to the gravitational wave background spectrum. But more importantly, so Goku talked about multi-messenger, but there is also multi-band gravitational wave astronomy. That means if you take PTA, LISA band and the LIGO band together, you will be able to even constrain primordial black holes and so on and so forth. So there are other ways by which the physics in the cosmology era would be sort of constrained. So there are, but right now it's early days. So there is a lot of theoretical interest in sort of developing these models, but I think a few more years of observation would be able to constrain some of these additional issues.
So just to follow up Sameer's argument, so you will get energy density in gravitational waves divided by that's required to close the universe. So these will be, so cosmological scenarios can give something here, here, here. So that can be, because it's multi-band. Whereas the gravitational wave from supermassive binary black holes will be here. It cannot be here. I'm talking about billion solar mass. It will be there for a million of solar mass. So, but they have a different, it will still have the 2 over 3 circular binaries and all those things. But here, that's the reason when you have the million kind of sensitivity, this will happen when you guys are my age. That time, stochastic astrophysical background is a nuisance. Remove it. I want to. So this is like Kobe, and so you still 1 part in 10 raised to minus 5 or 6, right? I mean, to remove for this to see the dipole, you have to remove and then look for anisotropy, right? So and there will be an anisotropy in gravitational wave background too. So this is it's just the beginning. It's going to be there. It's not going to go anywhere. So.
Well, I think we should stop here. So we thank Gopu for the nice talk. In fact, we should thank both the speakers of this session for the great talks. We listened to 2 great talks, but without becoming nightmare to the organizers, because both of them kept to the time. I'm afraid that our director here will become an academic dinner after these 2 talks. Okay. So thank you very much.
What are you doing? Because I invited someone. Even when
Maybe